Good morning, everyone. Organized by Center for Non-Conventional Diversity of Rights, in association with the International Association for Hydrogen Energy and the Society of India. Whether you have just joined today or have known it, I want to welcome you and hope you enjoy the day today. In continuation to that, I would like to invite our host, Professor S. Sharif, Professor of Mechanical and University of member of advisory board of directors of the International Association for Hydrogen and founding member of the board of directors of the Society of Dr. Sharif currently serves as of solar energy engineering. He is also on editorial board of 22 other thermal science journals. Dr. Sharif has 300 referred papers, 1 book, 20 bound volumes, 24 book chapters, 190 technical reports, and 2 US patents. We welcome you, sir, to deliver keynote address.
Thank you very much.
Welcome, Professor.
Can you hear me okay?
Yes, sir, we can hear you.
You know that Professor Sharif is a renowned scientist in the field of solar energy and hydrogen, other than many other fields. I am particularly very happy that I have many times that I have occasion to meet him. Professor Sharif is a brilliant scientist, and you are lucky you are lucky because at 11 o'clock at night he is ready to talk. Thank you, Professor Sharif.
Thank you very much. I hope all of you can hear me okay without any echo.
Yes, sir.
I would like to share my screen with you. So let me allow me to do that. Okay, so I hope you all can see this.
Yes, sir, the presentation is visible.
Okay, very good. Now let me put it in my presentation mode. I'm going to put it in the presentation mode here so that you can see it. I hope it's filling the screen and everything. So, so today, first of all, I would like to thank Professor Jain, and I would like to thank the organizers of the conference for inviting me to be with you today. And it's my distinct pleasure to be with all of you, and especially with Professor Jain, who is a very dear friend. I've known him for a long time, and it's a pleasure to be with him today. Today, I'm going to cover basically 2 topics. One is the latest advances in energy efficiency, and I'm going to also cover the state of the progress towards achieving net zero energy in the United States. I'm going to talk about some topics here, including the definition of energy sources versus energy carriers. We'll give you some background on energy usage in the United States, the goals established by the US Department of Energy towards achieving energy independence, and the path to getting to the net zero state. And in this process, I'm going to talk about the effort of the New Buildings Institute and other efforts that are going on at the same time. I'm going to also show you some examples of the historical first 10 zero energy buildings in the United States. And I will talk about one in particular, the one in Kapuni Village in Hawaii, and talk about the California experience. And then we'll give you some examples of some present projects funded by the US Department of Energy in terms of energy efficiency, and I'll have some conclusions for you. So the very first thing is, let us define energy carriers and energy sources, because many of us mix up those two. Energy carriers examples include gasoline, hydrogen, and electricity. And the feature that is common in all of those is that they have to be produced by primary energy sources. So the energy carriers in and of themselves do not exist unless they are produced. The energy sources are the primary sources that we can simply use, such as solar energy, nuclear energy, coal, and oil, fossil fuels, for example. This is quickly going over some of the projected energy consumption in the United States. And historically, you can look at going all the way from the 1980s all the way to 2035, and the projections in terms of the different types of energy sources, including coal and nuclear and natural gas, renewables and biofuels, and then other things such as wind and hydroelectric, for example. Now you can see that there are two things that are going on. If you look at from 1950 to 2020, you will see that the brown component, which is really the per capita energy consumption, is going down, starting from the 1980. They have been sort of trying to kind of go down, although it has gone up a little bit until 2000, maybe 2005. But now its per capita is going down. If you look at the total energy consumption, on the other hand, which is the dark blue, you will see that the total energy consumption has been steadily going up. And at the renewable part, which is the light blue at the very bottom, unfortunately, it's still very small. So it's very small relative to the dark blue. Now, if you look at the primary energy consumption by major sources, such as petroleum, natural gas, and coal, nuclear, and renewable, unfortunately, you see that the renewable part is still very small, 11%. This is from a 2017 state. Things are a little better today, but still not as much as we would like it to be. So renewable energy is only 11%, petroleum is still 37%, natural gas 29%, and even nuclear power is 9%. Now, if you go to the primary energy consumption by sector, you will see that the transportation sector is about 28%. The industrial sector is about 22%, and the residential sector is about 11%, and the electric power sector is about 37%. And you can see how much of each one of those sources each sector is actually consuming. You can connect the lines between the left bar on the left and the bar and the right bar, and you can see the interaction between the source and the sector. This is also another slide that shows the primary energy production by major sources, and you will see that the production is showing natural gas to be the biggest, the tallest bar, then followed by crude oil and coal and nuclear. So you still have the hydro and the biomass are still very small. The natural gas is also the natural gas plant liquids is also relatively small, 5% or under 5%. The current and future building consumption buildings in the US use about 40% of the primary energy and approximately 70% of the electricity in the United States. So that's for the current and the future buildings, the consumption in buildings. The commercial buildings, the primary energy consumption grew by 70% between 1980 and 2010. The Energy Information Administration project 22% growth between 2010 and 2035. And the residential building homes that are built after 2000, between 2000 and 2005, they use 14% less than the energy the homes that were built in the 1980s. So we're making progress in the sense that, you know, we're consuming less energy, we're becoming more energy efficient, and then you can see that it's those homes that were built between 2000 and 2005. They are better than the homes that were built before the 1950 by about 40%. This is a slide that shows the areas of building energy use in the commercial sector, and you can see that the pie chart is the space heating. It's about 45%, and the water heating is about 18%. Other things are relatively small. Of course, the space cooling is about 9%. So those are the three big players. Everybody else is small. Electronics and cooking and lighting and computers and all that are relatively small. The areas of building energy use in the residential sector, you can sort of have a similar pie chart. And of course, in the residential sector, the space heating is a pretty big player, and the lighting is also a big player. There are several efforts that have been done by non-governmental organizations, such as ICRE, for example. International Energy Conservation Code was introduced in 1998. That has made a dent. And the Energy Star program, which is introduced to reduce energy consumption and reduce pollution, that has also made some positive effect. And last but not least, the leadership in energy and environmental design, the so-called LEED, that they have a certification program that they assign different buildings different ratings depending on how green they are. So how much renewable is built into the home, is built into the building, and they encourage the different buildings to compete with each other. And this is a slide showing that the historical improvements that happened due to the effort of the non-governmental organizations. And you can see that, for example, the standard 90 that was introduced by ICRE has made a difference. 90.1 in about in the mid 1980s, the late 1980s, it caused 14% savings, and it continues to make a difference. The standard that was published in 2010 now is making us actually almost 50% improvement over what we used to have in 1975. The goals that are established by DOE, the Department of Energy, is to, by 2025, they want to have a maximum energy efficiency technology, achieve 75% of energy reduction. And by 2025, they want to create the technology and knowledge base for cost-effective zero energy commercial buildings, the so-called ZEBs. And they would like to be, by 2050, they would like to have complete zero energy across the whole United States. Now, I'm going to show you three different publications. One of them that was published by the National Renewable Energy Laboratory, which is the one in the middle. It talks about the cost control strategies for zero energy buildings. That's a very important report. And if you have time, you can go online and download it. There is another there is another report which is published by the U.S. Department of Energy, the Energy Efficiency and Renewable Energy component of the U.S. Department of Energy. They published a report on some definition, what they call common definitions for zero energy buildings. And if you're not familiar with the different terminologies that are used, this would be a good publication for you to have. They also have a report by NREL, the National Renewable Energy Laboratory, that talks about the communities of the future and accelerating zero energy district master planning. So they have a report on that. So you might also want to give this a try. And then the national, the New Buildings Institute, which is it's a not-for-profit organization that has one purpose in mind, and that is to achieve net zero in buildings. They publish reports occasionally. They have a 2018 report that summarizes the growth and trends from about 500 certified and verified emerging zero energy projects across the United States and Canada. They had reports in 2012 and in 2014. In 2014, they published a getting to zero type status report, and in 2012 they published a getting to zero type status report. And in the 2012 publication, they reported on 60 commercial and multifamily buildings or projects, and in 2018 they had about 500 of those verified emerging zero energy projects across the U.S. Now, according to the 2014 New Buildings Institute report, they have a database, or they created a database for about 126 buildings in the United States, and they distributed them in depending on where they are in the climatic zone. So they have 8 climatic zones in the United States, and they're classified here. You can see them in the table on the right side. You got the subarctic zone 8, that's zone 8 in Alaska, and then they have a very cold category, that's zone 7, and then they have a cold category, which are zones 5 and 6, and a mixed humid, that's zone 4A and 3A, and these are counties above the warm humid line. And then they have mixed dry, which is zone 4B, and hot humid and hot dry and marine. All of those are different categories, and as far as the climatic zones and the classification of the New Buildings Institute. And according to this classification, they published this chart that shows how many buildings there are, the ones that are verified versus they would like to call them emerging. It's a nicer name instead of saying not verified. So the emerging count is the dark blue, and then the verified, of course, is the very thin green zone there that you see. But all in all, it's about close to 500 buildings. They say that there has been a 700% increase since 2012. So there has been some progress made as far as that goes. And you can see that the progression over the years as far as how many buildings there are. Now, here is another slide that shows you the number of zero energy buildings. Again, the green is the verified, and the blue is emerging. And you're looking at a good progress being made every year. This is a zone. This is a map showing the number of buildings or projects that are located, where they are located. And what you will see is that the number of buildings or projects in California, which is the blue on the very west side of the U.S., is 214. This is as of 2018, 214 versus smaller numbers in different other states, like in In British Columbia, there's only 7. In Alberta, there is 1. In Saskatchewan, there is 0. And if you look at Washington State, you have 10. Oregon is 24. Idaho is only 1. Montana is only 1. Wyoming is only 1. You get to Florida, we had 13 here. But again, these numbers are going up, but they're not as ambitious as California. And I'll talk to you about the California experience towards the end of that presentation to show you what they have been doing, because they are really leading the country in so many good ways. This is another map showing the state in 2014, similar to the map that I just showed you for 2018, and you can see that California had only 10 at the time. Okay, so they went up by many fold, from 10 to about 214 in about 4 years. Now, this is another bar chart showing you the number of buildings and their color code is based on their where they are in the United States. They divided the United States into different zones, primarily climatic zones, and they're giving you the number of buildings in each zone. And again, here is another bar chart showing the building count within the size group. Size as in building size. So if you have a 500, less than 5,000 square foot, you're in the dark red. The orange is about 5 to 10,000 square foot. The yellow is 10 to 25,000 square foot, and the green is 25,000 to 50,000, and so forth. You got the over 100,000 square foot. So you can see the distribution for the so-called verified. These are actual verified projects versus the emerging, which have not been verified. In the 2018 report, also they give you the breakdown of the building type. That's an education facility versus multifamily facility versus public assembly facility versus warehouse or storage. They break it down also based on like the education group. They divided it into K through 12, higher education, and general education. This is the building ownership type. Sometimes it's a private nonprofit organization versus multifamily home versus a public office or public building, and public building owned by the city or by the state or by the federal government. So all of those are different classifications and giving you the percentage of each category. This is another chart showing you the building count as far as public versus private. And this is another one showing you the growth by building ownership, private versus public, public in the city, public in the state, public in the county, and private for nonprofit or private multifamily versus public federal building, and so forth. They're giving you the projections of each category. This is a map of the United States showing you the jurisdictional scores that are given. Now, these jurisdictional scores rank the states. The different states are given a rank based on their adopted energy policy. The rank of California is 51.7. That is the rank. If you go to Oregon, it's 59.5. And of course, the smaller the rank, the better. You can see that zero energy code is 0. So if you're 51.7, that means that you're that far away from 0. Okay, so so bigger is not better in this case. Okay. And this is one thing that you can do. You can actually go on the web and download the database, the Getting to Zero database or building database. And I believe this is an interactive database. Okay, so this might be of interest to you as well. And here is the database in interactive form. You can select the ones, the features on the left side, select what you want, and it will it will flash up the pockets where that apply to that particular category that you selected. You can select them all, or you can select a portion of them. You can select them by the state. You can select them by the building type. You can select them by emerging versus verified. These are all different categories that you can select. Now here is Florida Solar Energy Center. The Florida Solar Energy Center is part of the University of Central Florida in Cocoa Beach, or maybe Cocoa actually is the city of Cocoa, and then the city of Cocoa Beach is a different city, but they're very close to each other. And they have a center there where they do applied research. They developed a home energy rating system, and they came up with an index that determines the likelihood of a home performing at zero energy for a typical occupant. So, for example, a typical existing home might have a home energy rating system index of, let's say, 120 to 140. Okay, and a typical new home would have a rating, an index of about 85 to 100. So a score of 70 is projected to use 30% less energy than one at 100. So if your score is 70, if your index is 70, that means that you are using 30% less energy than a building that has a score of 100. And if you have a score of 0, that means that a net zero energy bill, that is a good thing. So 0 is your ultimate goal. That means that you are right on the money, and you're using what you are producing. You're not using any more energy than needed. This is the report that was written by several people at the Florida Solar Energy Center. They developed a comprehensive modeling of optimal paths to reach nearly zero energy buildings for new construction in Europe. This is a project that they actually were funded to do. And it, unfortunately, and I say unfortunately in a good way, because this is not happening in the United States, it's happening in Europe. So, of course, you know, the Florida Solar Energy Center is a U.S. Organization. So they were contracted to do this piece of work for the European countries. And the California experience is one thing that I wanted to talk about a little bit. There is a new lab report that outlines ways that California could reach the goal of becoming carbon neutral by 2045. And here you see a picture of the former governor of California, Jerry Brown. He and the guy that's cutting the ribbon. They're he's on the right side of the guy that's cutting the ribbon. He's holding the pair of scissors in his left hand, and he was a governor of California for actually for 4 terms. He was a governor many years ago for 2 consecutive terms, and then he became a governor again, and then he finally stepped down. Well, his 4th term ended, but this guy was very aggressive in achieving you know, carbon neutral and getting California way up and ahead of many other states in the United States. They have set a bold course to achieve statewide zero energy in the next 2 decades. All new residential construction will be zero net energy by 2020 in California, and all new commercial construction will be zero net energy by 2030, and 50% of the existing commercial buildings in California will be retrofitted to zero net energy by 2030. And here you can talk about the different climatic zones I mentioned to you before, and it's showing you the type and building energy use area. Okay, so you can see for the 8 climatic zones, you're seeing the type of building, whether it's a commercial, residential, or other type. There are 10 historic buildings that were net zero initially, and they were identified by location. And the one that we're going to discuss is the one in Hawaii in Zone 1. There's one in Minnesota, which is Zone 6, and then you have one in Ohio, which is Zone 5. and you have one in Wisconsin, which is zone 6, and Vermont, zone 6, California is zone 3. So these are all different buildings, but these are the earlier ones. These are the ones that were leading the effort. And we had essentially 6 commercial buildings, 2 campus buildings, 1 retail building, and 1 single family residential building. So if you add them all together, you will have 10, 6 plus 2 plus 1 plus 1. Now, this is one of those 10 buildings in Kopuni Village in Hawaii, and Hawaii is considered to be zone number 1. And you can see the building here, and I'm going to give you a closer. Let's see if I can go back to that slide. This building had a lot of good things in it. You can see the photovoltaic cells. You see the way the roof is built. It tries to reflect energy away from the building, and the way the carport here and all that. There's a lot of nice little things here that help made that building zero energy. This was a picture taken for students building houses powered exclusively by the sun, and they have these what they call solar decathlon. Yearly, they have competitions, and the students compete, and they build different things, and they compete with each other, and they get awards and all that. Now, I'm going to switch now to a totally different topic, which is some examples of some energy efficiency projects in the United States. And I want to make sure that I'm not over my time. I probably am over my time, but please feel free to stop me if I get too much into somebody else's time. So some of the projects that were funded by the U.S. Department of Energy include many things, such as an air source integrated heat pump, a cold climate heat pump, next generation rooftop unit, a residential absorption heat pump, a commercial integrated heat pump with thermal storage, a separate sensible and latent cooling device, a membrane-based air conditioning system, and then a novel solar absorption cooling system that reduce peak load. These are different things that have been funded. Other examples of recent energy efficiency projects include water heating. They have the absorption heat pump water heater, and the commercial absorption heat pump water heater, and the CO2 heat pump water heater, the residential absorption heat pump water heater, and the combined water heater, dehumidifier, and evaporative cooler water heater. All of those different things that are innovative. Other examples include the miniaturized air to refrigerant heat exchanger. University of Maryland is actually working on that under Professor Radermacher. The gas heat pump for building space heating, the Stone Mountain Technologies company is working on it. The highly insulating windows using smart automated shading. This is worked on by Lawrence Berkeley National Lab. It's a federal lab that belongs to DOE. Dynamic Windows program at National Renewable Energy Laboratory. Dynamically responsive infrared windows coating for Pacific Northwest National Lab. And the next generation building envelope materials by Oak Ridge National Lab. And then the building integrated heat and moisture exchangers. And I believe this is also done by the University of Maryland. This is just to give you a quick example of, I picked a couple of those to kind of walk you through. The miniaturized air to refrigerant heat exchangers by the University of Maryland. And they are made really good progress. I'm going to show you the purpose of that project is to develop the so-called next generation heat exchangers for heat pumps and air conditioners. And their target performance is to build miniaturized air to refrigerant heat exchange equipment with at least 20% less volume, 20% less material, and 20% more performance. Some of the company or organizations working on it include Oak Ridge National Lab, International Copper Association, Wieland and Heat Transfer Technologies, and Luvata. These are all partners in the project. This is what, if you look at the chart here, you will see on the horizontal axis the port hydraulic diameter, which is an indication of how small or how big the heat exchanger is. The smaller the number, the smaller the heat exchanger. And then on the vertical axis, you have the compactness, which is the ratio between the surface area of the heat exchanger divided by the volume of the heat exchanger. So what you will find is that for the small compactness, meaning that the surface area over the volume is small, and when the hydraulic diameter is large, you see that we have a lot of units. But the case when what you're trying to do is try to make the compactness high and the port hydraulic diameter small. So you want to be in the top left corner of this diagram, and you see only one dot at the 100, above the 100 mark there. And this is also another way of looking at it. This is how the heat exchanger technology is advancing, and you can see the different color codes showing you the different types of heat exchangers. Okay, so this is again showing you the colors. The redder the color, the larger the face area, and the darker the color, like blue and dark blue, would be a small face area. All right, so this is another project by the Lawrence Berkeley National Lab, which is a highly insulating windows with smart automated shading. And in the process of doing in that project, they want to create a smart window shade that opens and closes based on not you making the decision, but the algorithm making a decision based on a number of factors that include the outside conditions, the wind, and the irradiation from the sun, and a whole host of other things that make the decision whether to open the shade or to close the shade, or to partially open the shade or partially close the shade. And this is the algorithm. This is sort of the kind of a block chart showing how the window is going to act if as far as the shading is concerned, depending on whether the external temperature and internal temperature are equal or less than each other and all that. So it's a very, very nice project that Lawrence Berkeley National Lab is working on, and it has a number of integrated sensors, like interior and exterior temperature sensors. It has an exterior solar irradiance sensor, the occupancy sensor. It has a control algorithm that evaluates if the home is in heating or cooling or neutral, and it has an option to override the actions if you want to override it yourself. There's effort underway at finding a solution to the world energy problem. And the conclusions, part of the effort is directed at establishing a permanent energy system that, by looking at renewables, there is effort directed at finding better and more efficient ways of conserving the available energy. So they are working towards the renewable energy technologies, but they're also working towards improving the energy efficiency of existing systems. The U.S. is actually making steady but measured steps towards zero energy. I would like to see more of it, but I think under the Biden administration, a lot of good things are happening as far as the energy efficiency and renewable energy goes. In the area under Obama and the Obama administration, there has been some push also being achieved, and significant progress has been made in the area of environmental protection at the time. Much more needs to be done. California is leading the way. It is possible that there would be policy shifts and setback under different successive administrations, like when we went from the Obama administration to the Trump administration, there have been significant shifts in policy. So with this, I would like to end my presentation. I want to thank you for your time. And again, I want to thank the organizers for inviting me to be with you today. Thank you very much.
Thank you so much, sir, for your thinking words on latest advances in energy efficiency, energy carriers, and energy resources. Now, Dr. I.P. Jain want to thank you for you, sir.
Thank you, Professor Sharif. Very interesting speech, giving the overall status of USA. But I have two queries. So what is the definition of zero energy building by 2025 by US?
Yes, I mean, the abstract definition of zero energy building is that the building uses no more energy than the energy that it can produce. So you are totally self-sufficient. You don't need to basically be taking any energy from the grid. So if you can generate your own energy, perhaps you can have a photovoltaic system in the daytime, collect energy, generate electricity. Perhaps you would have a storage system, like a thermal storage system, where you can store some of the additional energy, maybe ice storage. In some cases, you could produce ice and then use it for air conditioning in the night. So that's the goal. Of course, it's a very touch and go type goal, because the renewables normally they're erratic. We cannot count on them 100% all the time. So there has to be some connection to the grid. And what they have tried to do is to try to pay back the customer for the electricity that they produce during the daytime. They can, if they produce more electricity than their need, they can put that additional electricity into the grid, and the utility company will pay them for that. They're not going to pay them the same rate that they charge the customers, but they pay them a prorated rate, or a lower rate than what they would have charged the customer. So, but there's still, you get some benefit from producing more than you need. And then in the nighttime, or when there is not enough sun and all that, then you will have enough credit. You can use more from the grid.
And then, can you tell me why only California leads in zero energy, not other cities?
California is a much more liberal and progressive state than many states in the United States. I would say California and New York are the two most progressive. But if I have to put one ahead of the other, I would put California as number one. They're very progressive. And then the problem, the good thing about California is that their population is large. They're about 41 million now. They have the 5th largest economy in the globe. So they are really more, the California economy is in and of itself is larger than the economies of many other countries. So one state has an economy that's too large. One thing that, for example, there was a setback, a little bit of a setback in the previous administration, where the so-called CAFE standards, which are they're standards for energy efficiency, fuel efficiency in cars and the transportation sectors. And the previous administration relaxed these CAFE standards, or sometimes eliminated them altogether. But despite that, the cars that were sold in California, the California still required them to abide by these CAFE standards, even though the federal government was no longer enforcing them. So they said to the manufacturers, the car manufacturers, if you don't abide by the CAFE standards, we will not let you sell your cars in California. And California's, the car market there is so large that any company cannot afford to lose California as a market. So they were able, even though the federal government had a different policy, California was able to force its way by saying, look, we're not going to deal with you if you don't abide by what we want. So they have the power, they have the leverage, because of it's just too large of a state to ignore.
One more query from your lecture, I got a theory that, do you agree that development of a nation is directly proportional to energy used by per person?
Yes, absolutely. Yeah.
If anybody wants to have any questions for Sir, they can ask here.
Good morning, Dr. Jain.
Good morning.
This side, Professor Khasa from DCUS Muthal. I just want to know that you're talking about the zero energy buildings. is the solar energy sufficient for this purpose?
Say the question one more time. Is what sufficient for this purpose?
Yes, I'm just saying that is the solar energy sufficient for getting a zero energy building?
Well, I believe so. I believe that solar energy is sufficient. I believe that we have the know-how. We have made, I say we as in the globe, not talking about the United States, I'm talking about all of us. We have the technology, it's already there. And the price of the solar energy has now come down to the point that it can compete with other energy sources. But the problem is that there is a push to continue to use the existing fossil fuel sources because of many reasons, including economic reasons and including political reasons and including just the momentum is still going towards the fossil fuels. There is not enough incentive because fossil fuels continue to exist, and in the mind of a capitalist economy, money, if you can make money now as opposed to money 5 years from now, you make it now. So there is that tendency to milk the system and get what you can from it now, even though in the long term it's better for everybody. So there is that mentality, not because we are bad people, but because that's just what capitalism is all about. I mean, capitalism is you wanna get more for your buck right now and worry about the other things later. So there is that. So that's why the government has a role here to play, because the government can set the policy. If you don't have the CAFE standards, for example, nobody would have abided by the CAFE standards until the federal government said, all right, you've got to do such and such and such by such and such year. Okay, so they come and they force you to do it. Now, the innovative mind among us have the ability to actually create that, make that policy work on the ground. So with all the many clever people around, they can actually make anything happen so long as there is a political will to make it happen. So if the government said, you're going to have to do this in 5 years, or else we're not gonna do, they give you the consequences if you're not abiding by that, then all of a sudden all the efforts goes into doing it, and then they can do it. So I have seen it happen so many times, and I believe that the human mind is so good that it can really do anything, but the political will has to come first.
Thank you. Thank you, Professor Steve.
Thank you.
Thank you so much, Professor S.A. Sharif. Your session definitely made an add-on to our knowledge.
Thank you so much.
Thank you, sir. Moving forward, I welcome each one of you again for joining us today. Now, champions are made from something they have deep inside them, a desire, a vision. Continuing with this note, I consider it a great opportunity to invite Dr. Ranveer Singh to the talk. Dr. Ranveer Singh has done a postdoc fellow at Ajo University, South Korea. Prior, he completed his PhD from Institute of Physics, Bhubaneswar. He is recipient of the Brain Pool Fellowship. His research interest includes surface energy, engineering, and use of different functional materials for their application in optoelectronic, hot carrier injection, energy harvesting, and memory devices. In addition, he is also interested in charge transport and ultra-fast devices at nanoscale. He is the author and co-author of more than 50 publications in international journals. Though I invite Dr. Ranveer to present his visionary words in his field.
Thank you, ma'am. I think I am audible to all the participants? Is it?
Yes, sir.
Okay. So let me share my screen first. So, okay. So thank you very much for the nice introduction, and a very good morning to all. First of all, I would like to thank the organizers, and my special thanks goes to Professor Chaganlal for giving me a chance to present my research work in the second international conference on renewable energy. In this talk, the title of my talk is based on the ultra-fast optoelectronic devices based on the hot carrier generation and injection. So in this talk, these are the outlines of my talk. In this, first I will discuss a brief introduction on the operating devices and why we need ultra fast. Then I will talk about conventional and hot carrier based ultra fast photo detector. Finally, I will discuss experimental parameters and results followed by conclusion. In addition, I would like to thank my all collaborators and funding agencies. And this is my current research group. So in my group, we have more than 70 people. And also now in our group, we have opening for the graduate and postdoc students. So if anybody is interested, they can contact to my lab. So now, what is the optoelectronics and why we are so interested in these devices? So the simplicity, the optoelectronics is the study and application of different electronic devices which interacts with the light. Or in other words, optoelectronics is the study of the optics and electronics together. Like if, for example, you have any kind of electronic devices, for example, diode or transistor, and if you will sign that device, that electronic device with the light, in turn, there will be some kind of interaction will be there. And I mean, the whole effect will be the whole device, the whole effect with the light will be called as a optoelectronics. Or in other words, like you have some optoelectronics device and the optics, and you will combine, then it will be known as the optoelectronics. So optoelectronics is an emerging technology for electronic devices that source, detect, and control light. Like by using these optoelectronic devices, we can convert this optical light into the electrical energy and vice versa by using this optoelectronic device. It is a multidisciplinary domain with fusion of energy, engineering, and science. The area of study mainly deals with the optics, like as we discussed with that, we need light or photons. So mainly it deals with the optics, and finally there will be processing of light through the semiconductor material. Nowadays, there are many examples of these kind of devices, like we are using solar cell, light emitting diodes, laser diodes, photodiodes, and optical fibers. And these all the optoelectronic devices are used in our almost in daily life. But all these devices suffer from high speed because whenever there will be the interaction with the light, there will be always loss of charge carriers in the device, and in turn, the efficiency as well as the speed will reduce. So why we need ultra fast optoelectronic devices? Because ultra fast process is needed in almost all branch of sciences. Like for example, if you will talk about we need ultra fast physics or science in the high energy physics, in the material science and medical science and others also. But finally, why we called it ultra fast and what is happening in the material at the time scale? I mean, why it is known as ultra fast? So for simplicity, like when light interacts with the atom or materials, there will be the generation of charge carriers just within a few femtoseconds. So after there will be the thermalization of these charge carriers in a range of 100 femtosecond to 1 picosecond. And this is known as the loss of charge carriers. This will happen within just after the generation. You can see here within 10 femtosecond, there will be generation, and just after that, there will be the thermalization. So this is known as a loss of charge carriers. if we move to further, then in the time scale of 10 picosecond, the charge carriers will separate out, or they can be injected in some other materials. But this is at already before that, we have lost the charge carriers due to thermalization. And if we will go to the longer time scale, then there is many processes like thermal and structural effects are dominating. So therefore, studying the ultra-fast dynamics of these charge carriers is very important from the fundamental point of view, as well as to fabricate the ultra-fast devices. Because if we will not, if we are not going to understand that what is happening at the ultra-fast time scale, we cannot make a device which can have good efficiency, or in that other terms, it can have like high response, fast response. So that's why we need to understand the ultra fast dynamics at the nanoscale, or maybe in the material. So based on that one, there are two requirements. One is the ultra fast device, and the second is that is the device can work as the cell bias. I mean, in the cell bias condition. So whenever there will be the cell bias condition comes in the picture, it means without applying any bias. Without applying any bias, that device should work. So the terms which the cell bias means, we are not going to apply any voltage in the device. We just shine that device with the light, and just after shining, the device should work. So the first device which comes in our mind by using by concept on the cell bias, that is solar cell. So therefore, to make a cell bias or ultra fast device, the first condition is that it should work as a solar cell or without any applied bias. So thus in my today discussion, first I will focus on the solar cell, and then I will come to the ultra fast process and how this ultra fast is related to the hot carriers, because hot carrier means the charge carriers which are generated in this range. So can we utilize these charge carriers to make a device? So basically, I will focus on these those two topics. One is the solar cell, and other will be the ultra fast, the photodetector using the ultra fast process. So why we need solar cell or energy? As we have already listened many talks on that energy is one of the most fundamental needs in modern life, and its demand is increasing very fast. Also, it is used everywhere. So therefore, to maintain the ratio of generation and demand of power becomes a more and more critical challenge for the world population. Natural resources like fossil fuels, coal, petroleum, etc., they have been the main energy source for the mankind over the last 2 centuries. However, these energy resources are depleting very fast. For example, if we will talk about coal, then it is predicted that within the next 200 to 300 years, it will be depleted. If we move to another on the source, that is petroleum, that will also going to deplete within few decades. So it's our necessity that we need to move from these energy resources to some other energy resources, and that should be also we can call it we need to move from the conventional energy resources to non-conventional energy resources. So in that race, out of the all available energy resources, solar energy is the cleanest, cheap, and available everywhere, especially in India. If you will talk about our India, so in almost in all states, we have the solar availability. And also it have the capability to fulfill the demand of energy for the whole world. So if we will talk about, just for example, like on a one sunny day, the sun gives approximately around 1000 watt of energy per centimeter per meter square on the Earth's surface. So that energy is sufficient to easily power our homes for free. But is it really that we can use this energy? So what are the difficulties? Because we cannot use that energy fully. So there are different kind of losses which is known in the solar cell, which are going to affect the solar cell efficiency, or you can say that we cannot use the solar energy in a whatever energy is coming from the sun on the Earth's surface, we cannot use that one. So what are these losses? So for example, normally we have this kind of solar cell, or we can say this is kind of a solar module in which we are going to use different kind of layers and contacts and different process. So based on that one, like you can see, first of all, the loss is the reflection, because in solar cell we are going to use the metal contacts on the surface, because whenever there will be the generation of charge carriers, we need to extract the charge carriers by using proper electrode, and these electrodes are made by the metallic films or like that. So whenever metal is there, so normally metals are known to reflect the lights. So in that way, we are going to reflect, we are going to lose the light. We are not able to observe the lights on the solar cell. Another factor is shadow. Again, as we are using these metallic contacts, so like if you have 1 centimeter square area, in that one, if you are using many metal contacts, so finally you are not going to use this whole 1 centimeter square as a, I mean, it is not going to, we are not going to use this whole area to observe the lights. So again, this is a kind of loss. Other factor is like a recombination, as we already discussed that in the few femtosecond, there will be the recombination of charge carriers. And after all, this after this one, in the materials, we in the almost of the all of the materials right now we are using for the solar cell, they have kind of dangling bonds on the surface. And when we are going to make the PN junction, so at the interface, due to these dangling bonds, there will be the generation of recombination centers, and they are also going to I mean, they on that way, there will be the loss of charge carriers by using these recombination centers. So this is also a kind of loss. Others also, like there will be, we are going to use many cables and contacts for the to make the solar panel. So there will be like different kind of resistance factors. They will also going to lose the efficiency. Other factor is absorption and transmittance, because in solar cell we are going to use like at least 2 layers, because PN junction, to make the PN junction. So in sometimes it is multi-layered also. So these all layers they are not able to absorb the light in a fully way. Like sometimes they are going to use only the visible part. Sometimes they are going to use only the IR part, like that one. So we are going to lose the one part of the solar spectrum. We are not able to absorb the wide band spectrum. So this is also a kind of loss. Other factors are like dirt on the solar cell. Especially if we will talk about Rajasthan, then in the summer region, in the summer, there will be like kind of dust on the solar cell, and if it will be continuously going to deposit on your solar panel or like that one, so finally the light will not absorb in the solar cell, and we are going to lose the efficiency, or we can say that there will be no absorption of light. So these are the mainly factors which are going to affect the solar cell. But still the scientists, and they have tried many ways that how we can reduce these losses, and can we increase the efficiency, or in other words, can we increase the absorption of light. So in that way, there are different processes to enhance the light absorption, like anti-reflection coating and graded index surface, or surface modification by chemical method. So I will show one example by using surface modification, by which we can enhance the light absorption. So for this study, we did the chemically texturing of silicon surfaces for different etching time. This is a well-known method. And in turn, the pyramid formation took place. These are the typical SEM image of these silicon surfaces for different etching time. The size of these pyramids increases with the increasing etching time, as we can see from these images, that as we increase the etching time from 30 seconds to 2400 seconds, the size of these pyramids increases. And also, by the help of these pyramids, we are able to decrease the reflectance from 43% to 0.4% in the wide wavelength range, from like 300 to 800 nanometer. Now, later on, I will show the example that we can also reduce the reflection from 3000 to 300 to 3000 nanometer. So this low reflectance is due to the multiple reflection of light from these pyramids. As we can see from this schematic, that whenever the light is incident on one surface of these pyramids, so it will reflect in this way, and there will be the kind of trapping of these lights, and finally it will absorb in the material. So that means by doing the surface modification, the maximum absorption of light is possible, and which helps to generate more photo-generated charge carriers. And finally, we can enhance the efficiency. So in this race, because as we know that in the 21st century, out of the all available energy resources, the solar energy is the cleanest and safest, and thus a huge effort is being put out throughout the world to find out more efficient solar cells using inorganic or organic materials. Out of these, the cadmium telluride CDT is one of the most prevalent candidate, which has more than 5.1% market share in the world after silicon-based PV cells. Although cadmium is considered to be toxic, because but CDT is one of the very stable compound and offer the advantage of making cheaper cells as well. In addition, it has direct band gap and gives maximum absorption of light in the visible region, as we can see from here. Its absorption coefficient is almost 10 times higher than silicon. So based on this one, in 2006, this Bosio group et al., they have shown that theoretically, the CDT-based solar cell, only the simplest CDT-based solar cell can have 30% efficiency, although till date, the maximum achieved efficiency by first solar cell in the USA is 22.1%. And this high efficiency is gained by the CDCl2 vapor treatment at 390 degrees Celsius, which leads to the grain growth, passivation of grain boundaries, and in turn enhance the minority carrier lifetime. However, the CDCl2 is completely soluble in water and thus faces environmental issues at the end of their lifetime. In addition, this conventional CDT-based solar cell normally uses as a CDS, cadmium sulfide, as a window layer. And this is also going to possess the excess cadmium, which is toxic. Therefore, in a bid to find out suitable alternatives, the simplest CDT-based solar cell without any CDCl2 vapor treatment has recently been demonstrated to have around 6% efficiency in 2014. But still, you can see there is huge difference between the theoretical and experimentally achieved efficiency. So thus, further to improve upon the same, we have tried to fabricate a multi-junction hole blocking solar cell without any using the CDCl2 vapor treatments. So our proposition is like that. We have fabricated a multi-junction solar cell, and this working principle of this solar cell is like that. When light is incident on the window layer, the visible light get absorbed in this layer, while UV light is get absorbed in the tissue layers. This one is as a like top contact, and this one is going to use as a like hole blocking layer. So just after absorption, the electron hole pairs are generated and get created in the observer layer and further collected at the electrodes. Also, this entire mechanism can also be understood from this energy band diagram, like incident like this one, and it will generate charge carriers like this one, and electron hole pairs move this way, and holes cannot move this way. Holes will be blocked this way from this CD2 to MO3 due to this high barrier height at this interface, and this high barrier height is due to this MO3 layer, which is working as a hole blocking layer. So to fabricate this whole solar cell or this whole configuration, we have used that texture silicon substrate surfaces to grow this CDT layer, as we can see from here. So for comparison, we have deposited this cadmium telluride layer on this flat silicon as well as the texture silicon surface. These are the SEM images, and these SEM images confirms the conformal growth of this CDT thin film. And further, by the help of these CDT thin films, we are able to further decrease the reflection of light from 0.4% to 0.2% in the wide wavelength range, as we can see from here. Finally, we have measured the efficiency of both the configurations, and as we can see that the efficiency increases from 0.3% to 1.9% after using this texture silicon substrate. But still, it is very low, because here we have just used only one configuration like silicon and only CDT. This is simplest CDT based solar cell. Why we did this experiment? The only conclusion which we conclude from here that these texture silicon surfaces are going to help us to enhance the efficiency. And as we can see from it increases from 0.3% to 1.9%. So this is an example of the simplest solar cell. In addition, using these pyramidal texture substrate, we fabricated this multi-junction CDT based solar cell, as we can see from this schematic diagram. And these are the cross-sectional SEM image of the full solar cell grown on pristine silicon with and without MO3 layer. As we can see from this zoom image that the presence of MO3 layer where there is no MO3 layer. And also, as we can see from this zoom image, that there is a very smooth interface between these two layers. We cannot see the interface, and this is the need of to fabricate a high efficiency solar cell, because as we already discussed that at the interface there will be different there are many dangling bonds, and they are going to create the recombination centers, and they can lose the charge carriers. So the smooth interface is much needed in to fabricate the to fabricate an efficient solar cell. And also we have measured the reflectance of this surface, both the configurations, and again we can it is found that it is below around 0.2% in the whole wavelength range, which will be extremely helpful to enhance the efficiency. Finally, we have measured the efficiency of all the configurations, and it is found that after using this MO3 layer and texture silicon surfaces, the efficiency increases up to 8.2%. And to the best of our knowledge, this is a maximum achieved efficiency to the simplest CDT solar cell without any CDCl to vapor treatment, to the best of our knowledge. But still, as we have discussed that theoretically, this kind of solar cell can have 30% efficiency, and that is the case of the only single layer. But after using the multi-layers and without any CDCl to vapor treatment, we are going to enhance the efficiency only up to 8.2%. Still, we are far away from this theoretical efficiency. So why it is happening? Why we are still very behind upon from this theoretical efficiency? Because there is always loss of charge carriers in the conventional PV devices due to the narrow band light absorption and short magnetic area lifetime, as well as the charge carrier scattering. And as a result, these devices, I mean the conventional devices, exhibits the lower power conversion efficiency. So further, how we can enhance this power conversion efficiency? So as I discussed in the first slides, that if we can utilize the charge carriers before their thermalization, I mean just after the generation, like in the range of femtosecond, if we can utilize those charge carriers, we can enhance the efficiency further. So by utilizing that concept, that is known like hot carrier injection. So by utilizing the hot carriers, the predicted energy conversion efficiency is around 65%. So the concept is like that: when the incident photon energy is larger than the band gap, the photo-excited carriers have higher kinetic energy than the lattice thermal energy, and they are known as the hot carriers before their recombination. So these hot carriers, before their thermalization, can be injected in a wide band gap materials to improve the efficiency. So how we can utilize these charge carriers? Can we utilize these charge carriers or not? And what is the process? How we can utilize these charge carriers? And also, what kind of the properties should have a material that we can utilize the hot carriers? So generally, the materials in which we are going to use the hot carriers, it should have large phononic band gap and narrow optical phonon energy dispersion. Also, it should have small band gap, like less than 1 eV, as well as it should have a good carrier transport. In that case, there will be no loss of the charge carriers in the transport. We can extract them easily. So the simplest way to utilize these charge carriers or to injection for these hot carriers is the wide gap materials. Like for example, we can see from this schematic that in that case, this is the metal and this is semiconductor material. And normally metals are used to generate the hot carriers. And if they have sufficient energy and momentum, they can inject through this one, through this Schottky barrier, and we can utilize them before their thermalization. So for example, like in this one, you can see that this is an example of simple TIN, zinc oxide and TIN. And in that one, they have used this concept. Like for example, they have shown the photocurrent responsivity at different wavelengths like 400, 550, and 700 nanometer. So as we all know that if we are going to use zinc oxide, so in that case, zinc oxide will absorb the light only in the UV range. Zinc oxide will not absorb the light in the visible range. So whatever response here we are getting at high wavelengths like 550 or 700 nanometer, which is not in the UV range. So if we are getting the response in as this wavelength, that means this is due to the injection of these hot carriers. This is just a signature. So to utilize or to further understand this phenomena, we have made this kind of device. Like we have used the metal oxide and titanium nitride, because normally metal nitrides, they have the wide range of absorption of light. So therefore we have used this titanium nitride. And the mechanism of this device will be like that. Like if we will consider that this is moly oxide and this is in this side, this is TIN, and after absorption of the light, the charge carriers which are generated here, if they have the sufficient momentum and kinetic energy, they can tunnel through this barrier. If they have not, if they don't have the sufficient energy, they cannot cross this barrier. So for that, this is just simple topography measurements which shows that how the structure of the device, and so this is just for the confirmation. In addition, we have also measured the transmittance, which is a very important factor for this one, because we are going to use it as a for the wide wavelength range or at higher wavelengths. So for that, we have measured the transmittance, and as you can see that from this transmittance spectra, that moly oxide, this red one belongs to the moly oxide, which is completely transparent in the visible region. And after using this TIN layer, we are going to able to absorb the light in the visible region. Whereas after using the double layer of TIN, further there is a reduce in the transmittance. That means we are going to increase the absorbance of the lights. So this is just for the device how we make the device and what is the kind of just optical properties. So further to confirm that this one that is really is due to the hot carrier injection and why is this effect is there, we measure the nanoscale dynamics of these charge carriers by using this AFM technique. By using this simple, we can see from this schematic diagram that by using AFM we can measure the photocurrent. So simplicity, like when light is incident on this one, if we have a conducting probe in the AFM, we can measure the current. We can measure the photocurrent. So for by using this technique, we have measured the current of this only single layer like AMOX and only TIN layer. So for the comparison, we have measured the current at zero bias, because we need a device which should work as a cell bias condition without applying any bias. So we can see from here that is almost no current on the surface without illumination at zero bias. It's almost in the range of picoamps. So it's 32 picoamps maximum. So it's almost, there is no current. But when this device is illuminated with the lights, and this is white light, so you can see that there is a generation of the current on the whole surface. You can see the current increases from around 792 picoamps. It is in the almost around in the range of nanoampere. So that means there is the injection of the charge carriers after the light illumination, and that's why we are getting the current in the film. In the single frame, we have also checked the effect of the intensity, as we can see from this image, that at the low intensity, there is less generation of the current, whereas at the high intensity, there will be the more generation of current on the surface, but still it is not that much uniform. This is, you can see that at some places it is higher current, at some regions there is very less current. So to get the stability, you can see from this double layer of TIN structure that again, we can see from here that when there is no light, there is no current, it's almost zero current. But after illumination, in the case of the double layer of TIN, we can see that there is enhancement in the current. It's almost around 1 nanoamps. And also this generation of the current is very stable, as we can see from this image, that when there is no light, there is almost zero current, very low current. But as we are going to increase the intensity, the current increases, and this is also uniform current on the surface. So that means by using the double layer of TIN, we can enhance the current as well as we can enhance the we can enhance the injection of charge carriers in the metal oxide layers. So this is the proof at the nano scale. Okay, but as we all know that at the nano scale there are in the AFM there are many processes. I mean there will be recombination of charge carriers, and also we at this point we don't know exactly that what is the decay dynamics of the charge carriers and what is the time scale in which we are going to extract the charge carriers. So to find out this process, or to find out this mechanism, the most versatile technique is the femtosecond transit absorption spectroscopy, and we did that one. So you can see from that we have measured this all layers like single layer, then combination of this metal oxide and TIN layer, then double layer of TIN. So as we can see from that, at the lower wavelength side, in this side, we are getting some signal. This is due to the photo-induced absorption. And at the higher wavelength side, we are getting this signal due to the photo bleaching signal. And this signal is going to increase after using the double layer of TIN. You can see that at the initial, I mean, just in the at the time scale of few picosecond, you can see that there is huge enhancement of in the intensity. So this is due to this hot carriers, due to the injection of these hot carriers. Further, to find out this decay dynamics, we extract the data from here. As we can see from this figure, that after using the double layer of TIN, this is shifted from this lower wavelength around 50 nanometer. So that means after using the double layer of TIN, we are going to absorb the light in a wide wavelength range, or we can say that we are going to use the charge carriers little bit higher energy also, because we are going to shift towards the lower energy, lower wavelength. So that means we are going to use the higher energy photons as well. Also, the decay dynamics is also very important for this process. So for that, we can see that at the initial time stage, there is a very fast decay dynamics, as we can see from this image, that initially there is the time scale is less than 0.2 picoseconds. So that means this is due to the electron-electron scattering, and this one is due to the electron-phonon scattering, and this is not going to touch the zero. So that means there is the injection of charge carriers, because why we are getting this one, because this is related to the states filling of the hot carriers. And final conclusion from here, that by using the double layer of TIN, we are able to enhance the injection of charge carriers, and they can dissipate their energy to the lattice or to the metal oxide layer before their thermalization. I mean, we can extract them within the picosecond. So now we have discussed on 2 points, like on the cell bias conditions and as well as to utilize these hot carriers. So to use them together, like for the solar cell concept and for this ultra fast technique also, we have fabricated self-powered and high performance photo detectors. So to fabricate this device, again, we use a simple device, just metal oxide and gold film. So initially we have deposited moly film by using the simple technique, it's called sputtering technique. And after that, we did the RTA, rapid thermal annealing, to make the moly oxide film. As we can see from this transmittance spectra, that we confirm that this is moly film, moly oxide film, because normally this transmittance spectra belongs to the molybdenum, because it has very low transmittance. And you can see that after making this moly oxide layer, it is going to show that transmittance spectra in the visible region. It is transparent. So that means this is moly oxide film. And after that, we deposit gold film, and to make this gold nanoparticles, again we did the RTA, rapid thermal annealing, and we can see that the gold film will transfer to the gold nanoparticles. So also after depositing these gold nanoparticles, we can see that there is a reduction in the transmittance in the visible region. So this is due to that this plasmonic effect of the gold nanoparticles. That means in this range, it will show the absorption of lights. Also, these gold nanoparticles, they are nearly spherical, as we can see from these SEM images, and from this high resolution TM, which confirms that these both films, I mean this monoxide film as well as this gold nanoparticles, they are crystalline in nature. So this is just for the to find the structural property and what kind of device structure is that. But now after that, we have measured the photo activity of this device, that it is really working as a cell bias condition or not, and is ultra fast or not. So for that, we measure this photo activity in this configuration. Like we make the contact on the gold film and one is on the bottom substrate silicon, and we have used the different LEDs to shine the lights. So from this IV measurements, we can see that as we are going to use the different wavelengths like 365 to from 365 to 914 nanometer, there is a generation of the photocurrent, as well as there will be the curve is shifting from zero, as we can see from this zoomed region, that it is going shifted from 0 to around 0.06 volt. So this is the VOC. So that means this confirms that yeah, this device can work as a cell bias condition. This is just a simple proof. Also, we have measured this I photon to I dark ratio. That means is there generation of the photocurrent at the all wavelengths or not? I mean, because we want to make a broadband photo detector. So for that, we have measured, we have extracted this data, and we can see that we are getting the photocurrent at the each wavelengths, and the highest photocurrent we are getting at around 420 nanometers. Now, further to just check the effect of the intensity, we choose this wavelength around 420 nanometer, and you can see that as we are going to increase the intensity, the current increases. So this is directly related to the number of photons. That if you are going to increase the intensity, that means there are generation of the more photons, and they are going to enhance the current. So this is simple. This is the photo detector measurement with the time. As we can see that we have switch on the light on in on and off conditions with the in the time scale of with a 0.25 hertz, and you can see that when there is light off, so there is no current, but after the light shining off, there is the generation of the current, and again when we switch to the light, again it's come to zero. So this is like on off condition, like that one. But interesting thing is that you can see that there are two kind of peaks. One is this peak, which is just after the lighting on, and another peak is also when we are going to switch off the light, and this is another peak which is after stabilization. So these peaks are known as the AC current, I mean alternating photocurrent, and this is known as a AC photovoltaic effect, and this is known as a well-known the DC photocurrent. I mean, just after when we are going to shine the light, so after some time there will be the equilibrium condition, and after that we have this photocurrent. So this is well known. Again, we find out the time response. I mean, what is the delay time, rise time, and fall time. So as we can see that the device is responding within the 35 millisecond. So this is a very good rise time, and also it is going to recover in the 48 milliseconds. So this is okay. Further, to find out this as a broadband device, first we measure this the effect of the intensity, as we can see from that one, that as we are going to increase the intensity, the photocurrent increases, especially at the low intensity, as we can see from that around 0.4 milliwatt per centimeter square, or at this wavelength, at this intensity, there is only AC effect. There is no DC effect. But as we are going to increase the intensity, here we are getting both effect. So in the next slide, I will discuss that why we are getting these two kind of peaks. And this is the broadband measurement. As we can see from that, from 365 to 914 nanometer, the device is responding. So that means we can use this photo detector as a broadband photo response. Also, this device is very stable, as we can see from that one. You can see that this is like kind of a broad spectrum, but if you will zoom this one, it will be like this one. So this device is very stable.
Hello.
Yes.
Sir, sorry to interrupt.
Yeah, I have only few slides. I think I have only 2 or 3 slides. I will finish it.
Try to sum it up. Yeah.
Yes. So, okay, so let's move to the mechanism. Why we are getting these two peaks? So when, let's say condition, when we are here, so this is the direct condition. And in that case, this is the equilibrium condition. And at the equilibrium states, the concentration of the electron and holes, they are stable and they are determined by this Fermi level and distribution functions. So the net carrier concentration are constant and independent of time. So when at this point, when the light starts to shine on the semiconductor, it perturbs the original equilibrium condition due to the light excitations. And in this condition, in this non-equilibrium condition, the excess electrons and holes are created, and the carrier's generation rate is larger than the recombination rate. And this photogenerated electron pair shift the Cauchy Fermi level upward for electrons and downwards for the holes, which are going to away from this Fermi level. And when this light is removed, now to obtain this equilibrium condition or to balance this Fermi level, electrons will flow from high to low Fermi levels at this condition, at this point. So that's why we are getting that very strong peak. But when the light is removed again, there is a non-equilibrium condition, which leads to the reverse photocurrent in this condition. Thus, therefore, we are getting this AC and PV effect, and this is the result of the photo-generated carrier imbalance induced Cauchy Fermi level splitting and the realignment of this equilibrium condition. Or we can say that this is the sudden splitting and realignment of this Cauchy Fermi level under the light illumination, which leads to the generation of these AC peaks. Okay, so further, this is the concept, or this is the photodetector which we fabricate on the bulk. I mean, if we are going to make this one like this device, so let's say this is the square. But what happens, because nowadays we are moving to the nano scale. So can we make a nanoscale device, or can we make like, if we are going to use this, like I want to make a photodetector by using just only this one gold nanoparticle. So can we make it or not? So just to show this one, we have measured the again nanoscale measurements, and this is the kind of electrostatic force microscopy measurements. In that one, we can find out the charge distribution on the surface. So we can see that at the interface, I mean, this is the interface between the gold nanoparticles and this moly film, and we can see that there is a little bit high charge carrier density. And this one is the current map, CFM map. So and which one? This one we have measured as a different voltage, like 0.5 volt and minus 0.5 volt. But in that one, if the interesting thing that you will see that at the boundary, I mean, let's say this is the gold nanoparticle and this is the middle one. So you can see that in this image, the charge density is a little bit higher at this point. So at the boundary, we are getting higher current due to the higher charge trapping. And to make this one, we have measured this photo response as a single this gold nanoparticles at only at one this gold nanoparticle. And as we can see that this device is working as a like when light off, with the light on, it is giving the signal. So this is just a demonstration that we can make a nanoscale device also. I mean, if we are using 1 mm square, we can many photodetectors in that one. And finally, why we are getting the photo response at higher wavelengths? So that is due to this LSPR effect, localized surface plasmon resonance, and this is due to the injection of these hot carriers before the thermalization. So that's why we are getting the higher the photocurrent or photo signal at the higher wavelengths, like 9740 or 940 nanometers. So with that one, I will conclude my talk. So as we have seen that by using these cell-wise conditions and by using this ultra-fast process, we can make device. And I have shown one example in which we have used gold nanoparticles and MO3 based heterojunctions for the broadband light absorption, or to make a photodetector based on the ACPV effect. And by using this ACPV effect, we are able to enhance the sensitivity by 97%. So this is a very good result. And by using that one, we can utilize that one. And with that one, I would like to thank you very much for your kind attention and for listening my talk.
Thank you so much, sir. It was a spectacular by you. It was pleasure. Thank you so much.
Yeah, thank you. So if any questions, I can take them.
If anybody have any query, the few questions are invited for the talk. Okay, as we are not having any query for this session, so now moving forward, we are going to enter in our oral presentation session second. The chairperson of this session are Dr. Ranveer Singh, Department of Material Science and Engineering, Azov University, South Korea, with whom we just had the session, and Dr. Vidyadhar Singh, JP University, Chhapra, Bihar, India.
So you will proceed this session, or we need to proceed this session?
We are going to give some instructions to the participants, then you will proceed this session. But
Okay.
I want to give a brief intro about Dr. Vidyadhar Singh. Dr. Vidyadhar Singh is currently positioned as Assistant Professor of Physics Department at Jai Prakash University, Bihar, and he has received his PhD from IIT India. Earlier, he was a postdoc scholar at Okinawa University Institute of Science and Technology. He has published 65 articles in reputed journals. He has received 4 US patents also. I welcome both of you, sir. And before we start our presentation session, I want to give some instructions to the participants. First of all, we have a limited amount of time, that is 5 minutes. So it's request to all of you to keep the presentation short and crisp. Thing that if you have any queries during the presentation, you may type in the chat box. We will bring them up during the presentation if necessary, or we will also have time for your questions at the end. So we are gonna start our oral presentation.
Excuse me,
Yes.
dear organizers, can
Yes.
you please give me a favor?
Sorry.
This side, Professor Khasa from D-Crust Murthal. Can I
Hun-
present my work?
Yes, sir. We will
Because I
schedule if you present your work.
because my presentation is on 8th number, and I have some constraint regarding the backup. If you please accommodate me.
Just a second, sir. Can you please give us 1 minute? We will inform you back.
My ID is 0288.
Hello, am I audible to you all?
Yeah.
Yes, Mr. Satish Khasha. I have just talked to our organizer committee. You can present your work right now if you want, but it's a request as we are running out of time. Please conclude it in a very
Thank you. Thank
ladies.
you. Please share my presentation.
Yes, sir.
साइंस की टीम बनाओ साइंस टीम वाले सुनील जी लिखो ना आप कॉमर्स के
Please mute yourself except the presenter because we have to maintain the quality of sound. Mr. Satish Khasha, we are going to do your presentation slides from our side.
Thank you. Good morning, Dr. Ranbir and Dr. Vidyadhar. Myself, Professor Satish Khasa, presently working in the Department of Physics, Deenbandhu Chhotram Institute of Science and Technology, Murthal. I am presenting my work on transition metal iron doped oxide glasses. And these materials are specially prepared for solid state electrolytes in lithium ion batteries. Next, please. The flowchart of content is research objective, significance, preparation and characterization, result discussion, and conclusion. Next, please. Yes. As all of you know that nowadays there is a crunch on the, you can say, fuels. And to avoid this crunch, more and more work is carried out in the direction of electric vehicles, and especially in India. And we focus ourselves that up to 2025, at least 1/3 of the market should contain electric vehicles. But all of you know that the heart of electrical vehicle is lithium ion batteries. And to improve the efficiency and work of lithium ion batteries, work is carried out nowadays a lot. Next, please. Yes, this is the first state who started a lot of work in the direction of electric vehicles. And to improve the quality of these electrical vehicles, or to improve the presence of electrical vehicles, the government of Delhi first of all submit a electrical vehicle policy. Even though to motivate the, you can say, the people of the state, they are providing some incentives in the form of cash, in the form of average electric two-wheeler, in the form of 50%, you can say, this registration charge, etc. and etc. Means the main focus is that to improve the environmental conditions, more and more electric vehicles should be on the roads. That's why this policy play a significant role presently in our capital towards this electrical vehicles. Next, please. See, up to 2025, our government and our, you can say, other institutions wants that at least the main component of this electrical vehicle is the personal user. And if some more and more incentives as well as some good electric, you can say, vehicles are provided, then we can achieve our environmental conditions. Next, please. Now see, as all of you know that everyone wants to breathe in clean air. And this is possible only when we reduce the vehicle pollutions. That's why to achieve this target, India unveiled a national electric mobile mobility mission plan in 2020 to address the issues of national energy securities, vehicle pollutions, growth of domestic manufacturing capabilities. Next, please. Now see, if we want to take the breath in clean air, then what we should? We will use electric vehicles. And to improve the efficiency of electric vehicles, we should use lithium ion batteries. And the heart of lithium ion batteries is the solid state electrolyte. So to improve the efficiency of this lithium ion batteries, some more or more good solid state electrolytes should be used. And to do that, nowadays, the material used as electrolyte is the lithium ferrophosphate. Next, please. Now let us discuss some facts related to this solid state electrolyte. That is, it is a solution of lithium salt with organic solvents similar to the ethylene carbonate is used as electrolyte. And lithium ion liquids, gels, or dry polymers electrolytes. The liquid version is flammable in organ. Or we can say that a self-heating behavior may occur that can lead to the thermal runaway if not properly cooled. Or nutshell, we can say that we should use a solid state electrolyte in lithium ion batteries that which needs less these side effects,
Your time,
especially the thermal runways.
sir, your time
And
is.
to do that, sorry, just a minute. Next, please. I will just show the some slides only. Okay, so that's why we must take care of this expensive battery recycling process. We must take care of this electrolyte, that is lithium ferrophosphate, and we have to modify this solid state electrolytes by using different compositions of glass. Next, please. Okay, skip this, skip the slide. Again, skip it. Yes, again, skip it. Yes, these are some compositions based on bismuth borate glasses. In the presence of lithium, their conductive behavior is quite good and they can be used as a solid state electrolytes. And if we use these materials as a solid state electrolytes, then we overcome certain, you can say, the limitations. Those are presently imposed on our lithium ion batteries. And to improve the working of this lithium bismuth borate system, we can use various transition metals like vanadium, like nickel, like cobalt, like iron, and again to move some more, you can say, the behavior of this electrical conductivity, we can use instead of one, we can use two transition metals, or we can use a combination of transition metals. And for that purpose, we prepared some compositions using cobalt vanadium, nickel vanadium, and nickel cobalt. And out of these compositions, we came to know that this mixed transition metal, especially this nickel and vanadium, they play a significant role in the improvement of the working of the solid state electrolyte. I just show some electrical behavior, only the last slide. Yes, skip it. Just show me the electrical properties. Skip, please. Yes, please go back. Please go back. Yes. See, if a material is so, yes. See, if you want to use a material as a solid state electrolyte in lithium ion batteries, so we must take care its conductivity behavior, especially the DC conductivity behavior. And the main component that play a significant role in that is the activation energy and conductivity at a particular temperature. And from these studies, we came to know that the activation energy required to participate these ions in conduction is the activation energy. And the order of activation energy is almost of the order of 1 electron volt. And due to this order, we can very easily say that these materials can be used as a solid state electrolyte. And among these, if we see the this DC conductivity, it is of the order of 10 to the minus 5. And especially if we're talking about this composition, that is your this CVLBB. In that case, you will find that the conductivity order is 11.7 into 10 to the power minus 5. Or we can say that this composition is very close to the semiconducting behavior of the materials. So just by carried out these electrical studies, we just came to know that there are few compositions those can play a significant role in the form of solid state electrolytes in these batteries. And if we use more and more compositions in the presence of some other transition metals as well as some alkali oxide, so we came to know that yes, we have a alternate solid state electrolyte, and this electrolyte is stable physically, thermally, and optically. Next slide, please. Now see this, as I have already told you that if we take this NCLBB, in that case your electrical conductivity is high at the same temperature conditions
You again.
and the energy is low. So this particular composition can be used, or we can suggest that it is the best material that can be used as solid state electrolytes. Next please.
Thank you so much, Satish Khasha. Dear participants, again,
Sorry. Okay, thank you. But because as you have mentioned in your schedule that you will provide me 10 minutes and 2 minutes for this presentation. But okay, no issue.
Sir,
These are the constraints of organizers.
please, we are feeling very sorry that we could not give you 10 minutes. It's just short of time. But we had a very great session with you. Thank you so much that you joined us. We are very privileged to have you here. Next, before calling next participant, I again want to give you the instruction. Just please keep in mind that you have a limited amount of time, that is 5 minutes. So without introducing or without giving the material and methods, directly jump to the conclusion or summary.
I also want to add something.
Okay.
Just try to focus on the what you are doing and why you are doing. What is the main purpose, that if you are doing any experiment or any technique, why you are using, show that one, because that is more important beside the basics and other things.
Yes, sir. And
So this one I am requesting to all the participants or presenters, especially in my session.
yes, sir. Now I would like to call Meena Yadav for
Yes, ma'am. I'm present. Please share my slide.
yes. You are sharing your you see your presentation.
Yeah. Shall I start?
Yes, you can.
Okay. Very good morning to all of you. I, Meena Yadav, as a research scholar in Department of Chemistry in Deen Bandhu Choturam University of Science and Technology. So my topic for today's oral presentation is electrochemical capacitance of novel PPY, TiO2 and SiO2 nanocomposite as modified electrode for energy applications. Next slide, please. These are the contents. Next slide. So let's start with the introduction. I think I need not to explain it more. In this work, I have synthesized novel PPY and TiO2 SiO2 based nanocomposites, and I have employed the material as electrode material for energy applications. Next slide, please. So this is the synthesis and modification part. Actually, I have synthesized the nanocomposites by using in situ chemical oxidation polymerization of pyrrole. And we have used a calculated amount of the precursors and then added FeCl3 solution, which act as oxidant. And we have stirred the solution on a magnetic stirrer, and we have kept the temperature below 0 degree throughout the experiment. And in between we have added calculated amount of TiO2 and SiO2 composites. These are synthesized by using sol gel technique, and again stirred for 12 hours, and after that we have air dried the nanocomposites at 60 degree for nearly 12 hours, and we get the composites. And in next step we have taken the composite, a calculated amount of composite binder and acetylene black, and we have made the slurry in DMF. Then we coated the slurry on graphite sheet by using drop casting method, and after air dry we have used the electrode for electrochemical analysis. Next slide please. So in structural characterization, we have characterized the composites for FTIR and XRD spectra. From FTIR spectra in TS, there is a broad peak from 3500 to 300, which represents the hydroxyl groups in TS composites. And there is a peak at 1631, which also represents the OH bending vibrations. And there is a peak at 934 centimeter inverse, which represents the TS binding of TiO2 and SiO2. And in PPY, all the characteristics peaks are present between 1600 to 400 centimeter inverse, and all the nano composites formed by using these precursors contains all the characteristic peaks, and we can clearly see from the plot that as we increase the amount of TS in PPY, the intensity of peak increases. So in next spectra XRD, we can clearly see. Okay, in structural characterization, we have gone through electrochemical analysis. We have taken cyclic voltammetric of all the precursors and the composites at a scan rate of 10 millivolt per second in a potential window of minus 0.2 volt to 0.5 volt. And from the CV curve, we can clearly see that the PTS2 composite has the largest surface area, and the calculated specific capacitance was 499 Faraday per gram, which was highest. So this is our best material. So we have to analyze it more. We have taken CV at different scan rates from 10 to 100 millivolt. And from the CV graph, we can clearly see that as we increase the scan rate from 10 to 100, the surface area increases, but the specific capacitance decreases. We will discuss it in next slide. And further, we have back one, please. Previous slide, please. Okay, thank you. So in next curve, we have taken galvanostatic charge discharge. We have taken the GCD curve at a current density of 0.5 ampere per gram for all the precursors and composites. And from the graph, we can clearly see that at 0.5 ampere per gram, the PTS2 composite again shows very good discharging time, which is a very good value for specific capacitance, and it again shows highest specific capacitance. So we have taken the GCD curves at different current densities for this particular PTS2 material. Again, we can see that on increasing current density, the discharging time decreases, and so as the specific capacitance. Next slide, please. And again, from Nyquist plot, we can clearly see that from the table where RS is solution resistance, RCT is charge transfer resistance, CPE and N value defines the non-ideal behavior of the supercapacitor, and CDL is again capacitance. So the PTS2 material has the lowest RCT value. That means it is the best material for supercapacitor application. Next slide, please.
Ma'am, your time is over.
I think 5 minutes are not yet completed, ma'am. Next slide. I have 2 more slides just.
And we have timer with us.
Okay, thank you. Any questions?
If there are any questions, you may type it in the chat box. Now I'll call our next participant, Chaitanya Nagesh from Shiv Nadar University, Gautam Budh Nagar, Uttar Pradesh, India.
Hi, good morning. I'm present. Can you please present my
Good morning.
presentation?
Your presentation.
Yeah.
Let us know if it is visible.
Yeah, it's visible. Can I start?
Yes.
All right, perfect. Good morning, everyone present here. I am Chaitanya Nagesh. I'm from Shivnadar University. I'm currently doing my undergrad, and this is under a special opportunity for undergraduate research where I did a project under Dr. Sushanta sir. So what I did today is I'll be talking about is the in situ synthesis of ZNO decorated MXC nanosheets and their study of electrochemical and photodegradation properties. Next slide, please. All right. Yeah, here are the contents. So the main goal of this project is first to exfoliate the tantalum carbide and then prepare in situ ZNO and tantalum carbide composites, and then we characterize them by using certain techniques. Next slide, please. So MXCs are basically 2D nanostructures made from 3D max stages, and they have huge potentials in all the way from cancer treatment to energy storage. And we are using tantalum carbide, which is not very explored and has a lot of good physical characteristics. And there have also some studies have shown that they're very good superconductive electrode materials. Next slide. All right. So here we first purchased tantalum carbide bulk from Sigma Aldrich, and then we sonicated it for 12 hours, and then we centrifuged it at 2000 RPM. This was basically liquid phase exfoliation method for getting MXCs of tantalum carbide. And then this was dried, and then it was actually mixed with zinc nitrate hexahydrate to form in situ composites. And the mixture in the end was actually heated for 3 hours at 100 degrees Celsius. So all these steps were actually confirmed by using certain techniques, which I will be talking about from the next slide. Yeah. Next slide, please. Yeah. Okay. So all these methods, which we confirmed that the successful making of all these composites, we first used XRD and then SEM and then UV vis and then CV, and then we did photo degradation. Please, next slide. Okay, here there are two important things to note here. Firstly, that in the left side, the graphs, you can see that there's a significant variance in intensity and the FWHM, full width half maximum, basically. So in the exfoliated tantalum carbide, it has a higher full width half maximum. This basically means that from the Debye-Sturr equation, it says that crystalline size is inversely proportional to the full width half maximum, and it's larger in the exfoliated one, which is on the top, than the bulk one, which is on the bottom. Also, the decrease in intensity from Bragg's law, it says that there's a scattered lattice in the above one than the below one, which means that there are layers of tantalum carbide which are separated. And then on the right, we can see the both peaks of zinc oxide and tantalum carbide, which says the successful synthesis of the composite. Next slide, please. We also did SEM analysis of both the compounds. We can see the tantalum carbide synthesis, and it's the first above left one, it's for 100 nanometer scale, and the below one is for 1 micron. And the second, in the below one, we can actually see the zinc oxide ones intercalated into the tantalum carbide. And here on the right, we also get the EDS graphs, which is energy dispersion thing, and we can see that all elements are present in certain weight percentages, which shows that there is expression of each of the element in the composites. Next slide, please. Okay, here in the UV visible spectra, we can see that the band gap for the tantalum carbide was about 4.17 electron volts, which is a typical semiconductor / insulator behavior. And we can see that there is a decrease in band gap for the composite, which basically means due to increase electron mobility, the decrease in band gap. And it says on the y-axis for the graphs, it's alpha h nu to the power half. This basically means that it's in the electronic transition. It takes an indirect route. So it doesn't go from directly conductor to valence bond. It takes an indirect route to that. Next slide, please. Okay, and then we performed CV for both the composite and the individual compounds. As we can see, there's a huge variance in the composite than the individual compounds in the right. And we performed CV for different scan rates from 10 to 90. And actually the specific capacitance was found, and it was seen to be 20 times more than the pristine ZNO or tantalum carbide. So there's a huge variance here. All right, next slide. We also observed great photo degradation properties at the actually we added the composite to methylene blue, and this was actually a pseudo first order reaction because the composite particles were actually very less compared to the methylene blue, and we found that it degrade. Oh, can you go back 1 second? I'm almost done. Excuse me.
Yes, sir, your time is over now.
All right. Yeah. So basically, the photo degradation said that it degraded up to 50% of the compounds. So there's a lot of prospect for this. All right. That's all. I'd be ready to take any questions now.
I have request to all the oral speaker. We have a large number of speakers, and we just want to ask you that anybody can give a talk itself, but confined to your 5 minutes. And I request you only to give results so that you have enough time to present your result. Thank you.
Now I'm calling the next participant, Devina Paul.
Yeah, I'm here. Can I share my own screen?
Yes, wait a second. Do please take care of the time.
Sure.
Have only 5 minutes to present. We have allowed you to share your screen. You may share your screen now.
Okay.
Devina, are you listening?
Yes, I'm doing that.
Yeah.
I will remind after 4 minutes to every presenter that your 1 minute is remaining. So please keep in mind.
Am I visible?
Yes.
My screen?
Your screen. You may start with the presentation now.
Thank you. I'm Dr. Devna Ratan Paul. I'm from Center of Excellence for Energy and Environmental Studies, Deenbandhu Choturam University of Science and Technology. I'll be talking about the topic, the photoactivity and the antibacterial activities of magnesium and lithium co-doped graphitic carbon nitride catalyst for wastewater remediation towards sustainable development. So in this work, we have taken consideration for textile dye as organic pollutant for water, definitely due to high rising demand in fashion industries. Another focus is bacterial contaminated water. Our application is based on eco-friendly technology for oxidation, that is advanced oxidation processes in more refinedly, I should say it as photocatalysis. Here, if I talk about the need of the work is to develop visible light responding material with appropriate band gap, as it is still a challenge in this field. Our material of choice is graphitic carbon nitride, as this is a material which is metal free and visible light active photocatalyst, and also it can be made very economically. So coming to the sample preparation, urea has been taken for GC3N4 synthesis because of its economical aspect in the mind, and which is then further dissolved with the dopant precursors, where we have taken magnesium from magnesium nitrate and lithium chloride for lithium. The raw material so formed after drying was calcined at 550 degrees Celsius for 2 hours. So this is a thermal polymerization reaction, and which further gives us the final products with different comparisons of dopants as shown here. Coming to the ICRE analysis, we can see there are the two pictures which are given, the two figures. One is with the co-doped materials and other with the comparison with the monometallic counterparts. So XRD analysis here, we can see the decrease at the peak of 27.4 degree, which actually show the hindrance to the crystal growth of the graphitic carbon nitride, and otherwise the innate structure of graphitic carbon nitride was all restored. The lower intensity of the peak at 13.1 gives an idea of good interaction of GCN pure host and introduced dopant species, which is visible here. Moving further, the FTR analysis again gives us a good idea for the chemical coordination among magnesium and lithium species with nitrogen in the nitrogen pots of GCNM and GCNL respectively, which can be depicted in the range of 2169 and 2157.17 per centimeter wave numbers. Moving further, this is a DRS analysis, which was done to have an idea of the band gap. So we can see here the red shift in the absorption edge has been taken place, and this was from 525 to 507 to 489, and it is very much better in respect to its GCN pure, which is 472 nanometers, and we can see the co-doped material with the best of the band gap was 2.58 electron volt in comparison to GCN pure, which was 2.76 electron volt, and it also overshined its monometallic counterparts. And this is the PL spectras, which suggests the suppression for charge carriers recombination as we added the both codependent here. So we could again see the observed red shift in the peak position, which supported our observation in DRS analysis. And in SEM analysis, we could see some of the evolution in the morphological aspects. And the magnesium and lithium in the pure GC3 and 4 has resulted in the formation of many in-plane fractures of nanoscale dimensions. Coming to BET analysis, we could see there was a decrease in the surface area. GCN pure was at 84, but in GSN-M, it was...
1 minute is remaining.
Okay. Yes, coming to the results, we could see GCN pure, which actually degrade only 62% of dye in 120 minutes, which is methylene blue in this case. But with this co-dopant, we can reduce the time to 60 minutes and the efficiency was increased to 93%. And it also overshined its monometallic counterparts as well. This is because of the synergistic effect of the magnesium and lithium both. So we can have it as a 60 minutes in 93% in comparison to GCNP, which is only 62%. Coming next to antibacterial analysis, the GCN-ML actually show the 25 mm of the inhibition zone, which is better than the standard antibacterial drugs, which is only 9 mm. So it is 5 times better than what also already prevailing in the market for the antibacterial aspects. And for Escherichia coli also, it actually overshined the standard drug of gentamicin as well as the GCN pure samples. So we can see here the GSN-ML showed 93% degradation efficiency for MB dye, which is 60 minutes. It is 5.4 times better than that of GCN pure and 3.2 times to that of its monometallic counterparts, that is GSN-ML and GCN-M. And GSN-ML also showed distinguishable antibacterial activity towards Klebsiella and Escherichia coli pathogenic bacterial strains. So this material can actually explode further for like gas sensing and water catalytic activity. And the water catalytic activity we are also doing. And in another week or so, we'll be available with the results for that. Thank you so much.
Thank you so much, Devina. Now I call upon our next presenter, Yogesh Kumar Saini. I repeat the name, Yogesh Kumar Saini. As the presenter is absent, I call the next presenter name, that is Sophia Rani. Sophia Rani Sheikh. Sorry, as the presenter is not present, so the next name is Christian Kumar. I repeat the name, Christian Kumar.
Yes, ma'am. I'm audible?
Yes.
Yes, ma'am. Please share my slide.
Excuse me, ma'am. Sophia here. So can I present after this presenter or should I continue?
Sophia, we are planning to schedule your presentation tomorrow. Is it okay with you?
Okay. Yes, it is very much fine with me, ma'am. Thank you very much.
Okay. Actually, your supervisor instructed us with it.
As you announced my name, so that's the reason I disturbed you people from the conference. So I'm extremely sorry for that. I'll be doing it tomorrow then.
It's okay. Krishan Kumar, be ready.
Yes, ma'am.
Sharing your
Please
slide.
share my slide. Yes, ma'am. Please share my slide.
Yes, you can. We have made you co-host.
Yes, ma'am. My slide is visible or not, ma'am?
Yes, they are visible. You may proceed further.
Thank you, ma'am. With due respect of eminent scientist, teacher, and respected all members. My name is Krishan Kumar, and I am research scholar under the supervision of Dr. Vijay Pariva. Today is my presentation on the topic of phosphor materials, a facile platform for photocatalytic reduction of carboxylic acid in visible light irradiation.
Please maximize your screen size.
Okay, okay, ma'am.
Press F5.
Yes, ma'am. Phosphorus is a luminescent material in fabricating optoelectric device, having potential applications in various regions, such as plasma display panels and in the preparation of postage stamp, lighting devices, toy industry, and also available in organic synthesis, in which phosphorus are significant in many organic reactions, especially synthesis of alkene via novel reactions and synthesis of aminophosphorus and many phosphorus reaction. And then in which found the successfully investigating phosphorus in multiverse reaction in many scientists. We synthesize a lanthanide drop phosphate due to photocatalytic properties and investigate carboxylic acid reactions. As per my knowledge, for the reduction of carboxylic acid into corresponding aldehyde using photocatalyst, a few papers are available, but they are synthesized aldehyde via mediator. It means direct method not available until now, and we synthesize europium dop phosphorus via combustion method. For the synthesis of europium dop sodium calcium phosphate phosphorus, we took sodium carbonate and calcium carbonate, ammonium dihydrogen phosphate, and europium oxide with a molar ratio of 1:2:1. First of three starting materials were mixed together in piston mortar and then mixed with the mixture was transferred into a partial crucible and heated simultaneously from 200 to 900 degrees Celsius and cooling with the room temperature. Then successfully synthesized a europium dop sodium calcium phosphate photocatalyst. And as shown in slide, the PL emission spectra shows the orange red emission band peaking at 592 nanometers and 65 nanometers under 257 and 395 excitation. In this excitation PL, this broad peak opening of 246 and 280. This is attribute a charge of transition between europium and oxide ions. And the europium dop sodium calcium phosphate successfully investigated the reduction of carboxylic acid with help of urea as a hydrogen sources and water as a solvent in the presence of visible light irradiation at room temperature and gain with various aldehyde derivatives. These various derivatives, which is successfully synthesized by using uh, European dope sodium calcium phosphates in visible light irradiations. And the catalyst can be recovered and use the same reaction up to 5 to 6 cycles without a significant loss of catalytic activity. By the help of this mild reaction and cheap and readily available and short reaction time are the important of our protocol. Conclusion.
You have 1 more minute.
Yes. Okay. Thank you, sir. It will be measured a step forward to carry to organic reactions in water for environment in organic reasons. And more significance and successful methodology would push up the use to it for the synthesis of other biological activity and molecule and could be contributing development new and green sustainable synthesis. And development of this technique development methodology is highly efficient and environmentally behind in the term of product recovery and atomic economic etc. And acknowledgement UGC for providing a fellowship for research and Department of Chemistry for giving the research areas and thankful for IIT Delhi and IIT Bombay, MNIT and CDRI Lucknow, SI Chandigarh for spectral analysis. Thank you, sir. Thank you.
Thank you so much, Krishan. Now, next in the queue is,
If any queries, sir?
if anybody would have the query, they will type in the chat box.
Okay, okay.
There you can reply them.
Okay, then thank you.
I repeat the name, Jeet Sharma.
Yes, ma'am. Very good morning. So
We are sharing your slides in a while. Is it visible?
is my slide visible, ma'am?
Okay.
I have actually shared the slides.
Okay.
Okay, so very good morning to everyone. My topic for this presentation is dedicatedly based on the enhancement of oxidative stability by using cerium manganese oxide, bimetal oxide composite material. So basically, in fuel cell device, the major issue which is in the part of the membrane is the oxidative stability of the membrane. And considering the naphion being an oxidatively stable component, prime component, it is very difficult because these membranes are very costly. So an alternative approach by using hydrocarbon-based membranes is studied in this, in which we have used SPEAK, and we have synthesized one composite, bimetal oxide composite, based on the assumptions in the sense from the literature perspective that cerium ions can actually absorb 89% of the free radical which are generated during the electrochemical process in the fuel cell devices, which degrades the membrane. So 89% of the hydroxide radical they can absorb. And also, in consideration to the noble gas metal atoms like palladium, the manganese ions have the 1.3 monolayer of hydrogen adsorption on it. So in comparison to the palladium, which is 1.9, 1.3 is the best known for the manganese. So based on these assumptions, we have modulated the cerium and manganese in a single phase, and we have designed a composite material for that. In considering the synthesis aspect and confirmation of that, we have done the XRD analysis, and we have got different peak values, diffraction patterns. So for 28.9, 33.62 and 47.77, these are the peaks for cerium for 111 phase, 200 phase, and 220 phase. Also, we have done the SEM analysis, and from that we have seen that these materials possess the distorted rhombohedric shape. And further, we have done the confirmation for the functional analysis, because the metal oxide bonds are very important to be characterized. So we have done the Raman analysis, and from that we concluded that we have got the peaks of around 1150 and 2726 for the manganese and the cerium oxides. And also the prominent peak at 448 shows that there is a CeOC bond. And finally, the hydrophilic surface was confirmed from the peaks in the range from 3000 to 4000, nearly 4000. And speak was synthesized by a simple electrophilic substitution reaction in concentrated H2SO4, and the confirmation analysis was done using the NMR spectrum. Unfortunately, we have able to quench the proton of the speak material, and this confirms that there is a sulfonic acid group grafting. And finally, the membrane was synthesized by solution phase intercalation, and the two solutions were prepared. The composite solution was prepared by ultrasonication, and the speak was by simple dissolution at room temperature, and both were mixed. And finally, we conclude that there is an inclusion of these composite materials from the ATR-IR spectroscopy, and very significant peaks for the cerium and manganese oxides are visible in the region of 500 to 625 centimeter inverse. Furthermore, physicochemical analysis was done in order to understand what are the water absorption properties and how the properties are changing in the relative humidity condition. And from this, we conclude that the hydrophilic surface of the cerium have very prominent effect on the water uptake up to 0.58% loading. And also the ion exchange capacity, if you see, they are actually decreasing because of the constrained restriction by the interaction of cerium, manganese oxides, and the sulfonic acid group in the polymer matrix. Overall, we consider that 0.5 to 4.8% was the good spectra of addition, where we are getting a good properties. And furthermore, AFM analysis was done on the surface in order to understand the homogeneity of distribution at different loading levels. For the pristine speak membrane,
You have one more minute.
Okay, sir. So you can see the difference here. And from this, we conclude that, okay, with increase the composite load, the surface is increasing. The surface area is also increasing. Then further electrochemical analysis was done in terms of Nyquist plot and the Bode analysis plot. And the Arrhenius plot was generated by calculating the conductivities at different temperature. From this, we concluded that the diffusion behavior was also changing, and with the increase in load up to 4%, the diffusion behavior was increasing, and the activation energy was decreasing. So at higher temperature, the 0.5 to 4% load was good enough. Further, the Fenton stability test was done, and from that we screened that 1% was 1 to 4% were perfect in terms of stability and electrochemical analysis. And further, the mechanism was proposed that how these binuclear complexes are actually helping to gain the stability in the oxidative environment, and to how the proton conductivities are improving. So from this, we concluded that these are very good materials, low-cost materials for enhancing the oxidative stability in alternative polymer electrolyte membrane for fuel cell applications. With this, I would like to thank everyone and the CSIR. Thank you very much, ma'am, and thank you very much, sir, for having patience, and all the participants. Thank you very much, and UGC for funding as a funding agency.
Thank you so much, Ajit Sharma. Now our next presenter.
Any questions will be more.
Nagendra Prasad. I repeat the name, Nagendra Prasad. So your slide is, you may proceed further.
How many slides you have? It was showing 42.
I remind you again, please consider the time that is confined to 5 minutes only.
Mr. Nagendra, how many slides you have?
Mr. Nagendra, you are not audible. Please turn on your mic. Mr. Nagendra, sir, you are not audible to us. Sir, is there any issue, you can tell us on the chat box. I think there is a glitch at that side. So we are calling our next presenter, that is Sonia Rani. I repeat.
Yes. Hello.
Yes.
Very good morning to everyone. Ma'am, please can you share my presentation?
Yes, we are doing. Sonia Rani, you may start now.
Ma'am, please present my screen. Yes, ma'am, it's visible. My topic of presentation is elimination of CV and BG dye from wastewater by Algeria Libec plant as an adsorbent. Next slide. Abstract. Dyes are mainly used in printing, textile industries. Crystal water and brilliant green dyes may cause skin irritation, eye damage. So their removal from the wastewater is necessary. And we use various techniques in removing these dyes from the wastewater. Adsorption is one of these techniques. And I use Alzevia Libec plant as an adsorbent for removing the crystal violet and brilliant green dye. And we use techniques like FTR and SAM and BAT. Next slide. Adsorption, as we all know about the adsorption process. In adsorption, a particle gets absorbed on the surface of an adsorbent. Adsorbent which is absorbed the particle is called adsorbent, and adsorbed which is being absorbed is called adsorbate, like dye. Next slide, ma'am. Crystal violet and brilliant green are two important dyes. Here we use these dyes to eliminate from the wastewater. Low-cost adsorbent like Alzevia Libec plant is used to remove these dyes. Next slide, ma'am. Methodology: sampling stock solution of 1000 ppm of these dyes are prepared in the labs, and different concentration 20, 40, 60, 80 and 100 ppm and pH of 4, 6, 8, 10, 10, 12 are prepared from stock solutions. Preparation of adsorbent: collection of the material, washing of the material, and then dry the material is 60 to 70 degrees Celsius for 24 hours. Then graduate to reduce size, and then save the mass size from 0.15 to 0.300 nanometer and stored in the Ziploc and bottles for use. Next slide, ma'am. Yes, activated carbon preparation. Ma'am, back slide. No, ma'am. Back. Yes, ma'am. Activated carbon. Okay, ma'am, please stop. Activated carbon, I have prepared activated carbon from the adsorbent and then analyze the samples to check the effect of contact time, concentration of the adsorbent dose, and effect of pH. Next. Results. The removal efficiency was calculated by the formula C naught minus A into 100 divided by C naught. The C naught is the initial concentration, C is the final concentration, and characterization of the SAM. I used SAM and FTR techniques to characterize a sample. Next. Adsorption of CV and BG dye. In this figure, we can see the A denotes the before adsorption process, and B denotes the brilliant green dye adsorption, and C denotes the adsorbent after crystal violet dye adsorption. We can see the changes in the peaks before and after adsorption of both dyes. Next slide, ma'am. Here we can see the two figures. First figure before absorption of adsorbent and after absorption of CV dye. In first figure, we can see the pore structure of the adsorbent prepared. And in second figure, we can see the dye molecules get absorbed by the surface of the molecules. Next slide, ma'am. Here same, in first figure we can see the pore structure of the adsorbent, and in second figure we can see the dye molecules get absorbed on the surface of the adsorbent. Next slide, ma'am. In first figure we can see the concentration graph with removal percentage. When we increase the concentration, the removal percentage decreases. And in second figure we can see the time. When we increase the time from 5 to 150 minutes, the percentage removal increases from 24 to 86 degrees Celsius in case of BZ dye, and in case of CB dye, the percentage removal increases from 44 to 85 degrees Celsius percentage. In third figure, we can see the effect of pH. When we increases from pH 4 to 12, the removal percentage increases from 77 to 87% in case of BG dye, and in case of CV dye, 84 to 90 removal percentage increases in case of crystal violet dye. In case of dose, when we increases dose from 0.1 to 0.5%, percentage removal increases from 86 to 89% in case of CV dye, and in case of a BG dye, 86 to 89% removal increases. We applied. Please stop, ma'am. Please stop.
Over.
The result shows that crystal violet and brilliant green dye showed excellent result in removal by LGBL equipment as an adsorbent. 85.77% removal of crystal violet dye and 86.5 removal for brilliant green dye in 45 and 150 minutes at a pH value of 7. Thank you so much.
Okay, our next presenter is Vinay Anand. You may present now. Vinay Anand.
Hello. Very good morning. Audible?
Hello.
Hello. I'm audible. Hello.
Vinay Anand, you may present.
Hello. Am I audible, ma'am?
Yes.
Very good morning. I am Vinay Anand, a research scholar from Library Professional University. My presentation is on the topic of technological.
Can you make it full screen?
Sorry.
Can you make it on full screen?
Yes, this is the full screen, sir.
No, we are not able to see it. Can you make it F5?
You may put it on slideshow mode.
Or maybe you can press F5.
Yes, I pause it. Okay.
Press F5 to screen. Please make the slides in full screen mode. Press F5.
Now, okay.
Okay, go ahead. Let's see.
Okay. So my topic is technological integration of the solar energy in electric vehicle and various their options. Here the transportation is in higher demand in India just because of comfort and safety. IC engine-based vehicle which uses petrol and diesel, which generated more power pollution and harm the environment very badly. Electric vehicles become a wide interest of the riders, and so researcher attraction towards the efficient and electrified economic pollution-free zero-emission vehicle design and trying to remove the limitations to adopt it. And basically, that some of the piece of the literature elaborated better way about the electric vehicle and technological integration of the solar improve efficiency as well as maximize to reduce the limitations. This is the investigation-based study actually done with the help of some of the study that understand the opportunity of solar power electric vehicles. Very exactly, we go for the electric vehicle is pollution is the major cause of the vehicles. So the vehicles is exhausting carbon dioxide emissions, nitrogen oxide emissions, carbon
In
monoxide.
which slide you are speaking? Your slides is only, we are only seeing the first slide.
Okay. Now visible, sir?
No, we are able to see only your first slide. Where are you speaking? We don't know.
Okay. Now is it okay, sir?
Yeah, we are able to see your screen, but you are just sticking on the first slide. You are not moving.
Let's move on. Can you please share from your side, sir?
Please handle it.
Please press F5.
So already pushing, but unfortunately it is not being shared. Is it now visible?
Continue it, please.
Is it okay?
Please continue it.
Now is it?
Don't have Vinay Anand, so sorry for the inconvenience.
Okay, so I'm should I go ahead? I'm just giving this electric vehicles is basically the advantage is 0% carbon dioxide emissions, low carbon CG because of the battery located under the floor, tank to wheel efficiency up to typical 3 times better than IC engine based vehicle. Some of the basically disadvantage of the this particular electric vehicle is similar to higher weight PHEV due to the battery size, charging infrastructure limited, and they fully depend on the cost of the battery. Some of the mild electric vehicles is being occurred is high FC reduction to a dead cost ratio and degradation in the conventional cars. No concern about the HV safety. Basically, some of the disadvantages about it is the limited boost, no option of external is PHEV option to charge externally. Per kilowatt cost is very low, provides the burst both sides due to the fuel and battery both is being convenient to be using. And now, whenever talking about the disadvantage, the higher weight because of the batteries, it is the more costly than FHEV. So some of the challenges faces by the electric vehicle in India is storage, energy forecasting, limited charging station in India, cost of electric vehicle not attractive and out of the reach of the customer, driving range limitations, age of the battery life low due to the fast charging at charging station, limitations of the availability of electricity in the few of the region. Skilled mechanic and electricians are required. Basically, electric vehicles, some of the barriers are Indian market, technical issues are there, and some of the government policies are not very good enough to come into it, and the infrastructure of the charging is limited to the availability. And some of the most important advantages of the electric vehicle is no fuel required, no emission of the harmful gases, economical in running cost, benefited in health point of view, and noise free, no vibrations, and very safe in the all point of view. Accessories basically required is induction motor.
You have 1 more minute.
Yes, prime mover is basically the induction motor. Various electric vehicle manufacturers in 90s maximum used the induction motor. Around 30% of whereas 60% of use PMC and found induction motor as the prime mover most suitable for the all types of the electric vehicle, which are robust in the physically and maintenance is very low. Now only 32,000 AH battery capacity is widely required in the electric vehicle. And so most important is while I'm just talking about the technical integration of the solar panel is monocox crystalline silicon high efficient solar panel for photovoltaic powered electric vehicle is widely taken into the application. It is also there the photovoltaic performance efficiency on the urban road received approximately 9%, whereas the panel efficiency was 13% in full sunlight month with capacity of approximately 8 to 20 watt per. And the battery charge 12 volt battery is 120 Ah used in the low capacity of solar powered electric vehicle. Yes, I'm finishing on, please. The basically is the most important part of the electric vehicle is converter to charge the auxiliary battery of electric vehicle application of the DC to DC converter is used. Now we got the some of the results about the particular study of the literature. Is this work is performed of the observed that the solar operated electric vehicle and battery why to stop us from daily use. And so it is in this regard, various relevant research article investigated and so that the electric vehicle may be the future of the transportation and will be help to the lowest load to the grid, and the life of the battery can also be improved by slow charging method, and also it will help to the weight of the electric vehicle of amount of the battery, and it may be extend the driving range of the electric vehicle. Conclusion: the above studies conclude that India has a huge quantity of non-renewable sources as well as renewable source of energy, whereas the solar, wind, biogas, etc. is a renewable source of energy can preserve our nature, and in this which is the solar. The scholar is studied about.
Thank you so much, Vinay Anand. Your time is over. Now, next presenter is Karishma Joshi from University of Rajasthan, Jaipur.
Hello. Hello.
Yes, you are audible.
Please share my. Hello. Please share my slides.
Yes, we are sharing. Wait for a minute.
I have one announcement for the remaining participants. So when you are presenting your slides or your talk, so be sure that you are being the present on the slide that you are speaking on that one. Otherwise, I will make it absent. It should be clear to all.
Yes, sir.
Good afternoon, everyone. I'm Karishma Joshi, research scholar at Department of Physics, University of Rajasthan, Jaipur. The topic of this presentation is design and analysis of silicon on sapphire-based evanescent field sensor for detection of trace gas in mid-IR. Next slide, please. Next slide, please. These are the outline of my presentation. Next slide, please. Most of the gas like carbon monoxide, carbon dioxide, nitrous oxide trap energy from the sun. So the temperature of earth is rising and these gases have major impact on physical and mental health also. Figure first shown is the global emission of harmful gases, whereas figure second is shown the various health disease like migraine, skin cancer, asthma that are occurred from the harmful gases. So we tried to detect harmful gases, and for this work, optical waveguide based sensor is a promising tool. Next slide, please. Skip this part. Okay. A sensor measure a physical quantity based on its modulation on the intensity, phase, polarization of light traveling through an optical waveguide. Optical waveguide based sensor is a promising tool for detection of trace gases since it has attractive feature like low cost, immune to electromagnetic interference, fast response, higher sensitivity, convenient for lab on chip system. Next slide, please. Skip this part. To design an optical waveguide based sensor, we opted silicon on insulator based slot waveguide scheme. Next slide, please. Next. Okay, since slot waveguide confined the major part of incident light over the slot region, so we opted slot waveguide for our design. Silicon slot waveguide consists 2 silicon bricks separated with a few nanometer gap and employed on a low refractive index. Slot waveguide follow the Maxwell discontinuity equation. Let NH and NS are the refractive index of core and slot region, and NH is greater than NS. So according to the Maxwell discontinuity equation, light confinement over the slot region is very high due to the refractive index contrast between silicon and slot region. We opted evanescent field sensor for our work. Previous slide, please. Previous. Okay. Field sensor for our work. This is the schematic view of evanescent field sensor. Propagation of EM field through the waveguide has 2 types of confinement. Major part of light is confinement into the core region, and extended part of this guided mode is confined into the cladding and substrate region. This extended part of the light known as the evanescent field. Since cladding and core region is filled with trace gas and light confinement over this region is very high, so the interaction of light with the trace gas is also very high. That is the key factor of evanescent based sensor. Next slide, please. We choose evanescent field ratio is defined as the power confinement over the sensing area to the total power confinement. As you can see from equation 2 that sensitivity has direct dependency on eta, which is evanescent field ratio. Next slide, please. Next. Okay. We choose sapphire as a substrate material. Most of trace gases have their fundamental rotational vibrational band in mid-IR region, and sapphire retains less than 1 dB per centimeter losses in mid-IR and also have higher refractive index contrast in mid-IR region. Next slide, please. Okay, this is the parameter which is required for our simulation. This is the refractive index of sapphire, refractive index of silicon, and refractive index of trace gas at operating wavelength. Next. Okay. First, we detect carbon dioxide, and the operating wavelength of carbon dioxide is 2.76 micrometer, which is the characteristic peak of CO2 in mid-IR region. We have done simulation for waveguide height 0.6 micrometer, 1.0 micrometer, and 1.4 micrometer. And as you can see from above figure that for 1.0 micrometer height, 60 nanometer slot gap, and nearly 0.32 micrometer slab width, EFR reaches maximum value, that is nearly 35%. And for other values of a structural parameter of waveguide, EFR tends to lower values. Next, please. Next. Okay. The same simulation.
1 more minute.
Okay. Same simulation have done for nitrous oxide. Next, please. Next. Okay. Next. This is the table for my result that carbon dioxide, nitrous oxide, for ammonia and for methane, the obtained EFR is 35%, and these are the structural parameter of my waveguide, and the 35% EFR is a good range of sensing device. Next, please. Next, please. Okay. I have presented my work in this conference. Thank you. Any questions?
Okay, thank you, Karishma Joshi. Wonderful presentation.
Thank you, ma'am.
Next presenter is Dipendra Jhankal from MNIT Jaipur, Rajasthan. You may present now.
Yes, ma'am. Am I audible, ma'am?
Yes, you are audible.
Okay, ma'am. Please share my slide, ma'am, please. Good morning, all. I am Dipendra Jhankal, PhD scholar at the Department of Physics, MNIT Jaipur. Today, I am going to present my research on MS2 flowers decorated reduced graphene oxide for intermediate bifunctional electrode in photo supercapacitor. Next, please. This is the outline of presentation. Next, please. Okay, now the introduction and motivation. Basically the photo supercapacitors are fabricated by integrating solar cell device with a supercapacitor into a one module. The first photo supercapacitor was fabricated by Miyaska and co-workers in 2004. The basically problem is the solar cell that convert the solar energy into electrical energy, and the storage devices like the supercapacitor store the electrical energy. So when we combine the solar cell devices with the energy storage devices, we require the external connections. That connections reduce the efficiency and also reduce the energy density of the device. So we require a device that contain both the device in one module that enhance the device efficiency and energy density also. Next, please. Okay, now when we modified a reduced graphene oxide with the morphologically that enhance the surface area and it enhance the device performance. In this research, we synthesized the reduced graphene oxide by the hydrothermal method where KOH and NaOH was used as the reducing agent. After that, the MOS2 floors was also synthesized by the hydrothermal method, where molybdenum trioxide was used as the molybdenum precursor and potassium thiocyanide used as the sulfur precursor. For the modification of the graphene sheets, the MOS2 floors decorated on the graphene sheets. This was synthesized by the also hydrothermal method, where the reduced graphene oxide was mixed in the solution at the precursor time. Next, please. Okay, now the result and discussion. The same image shows the morphology of the synthesized material, where the MOS2 shows the MS2 shows the flower-like morphology of the MS2, and the MS2 are the composite shows the morphology present of MS2 flowers between the reduced graphene oxide seeds. The Raman results confirm the presence of the MS2 with the presence of the D band and G band of the reduced graphene oxide. The XRD result also confirm that the presence of RGO in the MOS2. The intensity ratio of D band to G band decreases when we introduced MS2 with the RGO. It due to the MS2 flowers decorated on the reduced graphene oxide seeds. Next, please. Okay, now the electrochemical results of the counter electrode and supercapacitor. The electrochemical results of a counter electrode in 3-electrode system where the iodine and triiodine used as the electrolyte. The oxidation peak and reduction peak of MS2-RGO has the high current density as comparison to MOS2 and MOS2 and RGO. That reveals that the MS2-RGO has the high catalytic activity towards the triiodine attraction. The linear relation between the square root of scan rate and current density reveals that the triiodine reduce on the surface of counter electrode. There is no particular interaction between the electrolyte and counter electrode material. Now the supercapacitor result, the charge discharge result shows that the MS2-RGO has the high discharge time that represent the MS2-RGO has the high capacitance as comparison to MS2 and RGO. The EIS electrochemical impedance spectroscopy reveals that the MS2-RGO has the lowest charge transfer resistance that also enhance the performance of the supercapacitor device and a counter electrode device. Next, please. After that, after the individually check the performance of the counter electrode and supercapacitor, the photo supercapacitor was fabricated. Stainless steel foil was used as the common substrate. The MS2-RGO decorated on the both the side that act as the working electrode of the supercapacitor and act like the counter electrode for the dye-sensitive solar cell. The PVA membrane was used as the separator. The dye-absorbed TiO2 used as the photoanode for the dye-sensitive solar cell, and MS2-RGO act as the second working electrode of the dye-sensitive solar cell. Now the device is performed in the dark and light condition. In the light condition, firstly the charge generated from the dye-sensitive solar cell is directly stored to the supercapacitor that increase the voltage up to the 0.5 volt. After the completion of the charges, the light is off, and in the dark condition, the photo supercapacitor continuously discharge at the 1400 second. Next, please. Okay, now the conclusion. In the conclusion, the MS2-RGO was successfully synthesized and it's characterized by the same Raman and XRD. The supercapacitor was performed in 3 molar Na2SO4. Also the MS2-RGO based symmetric supercapacitor has the high capacitance as comparison to MS2 and RGO composite. A simple photo supercapacitor was fabricated that performs better as comparison to MS2 and RGO. Now the MS2-RGO that was the morphologically modified act as the intermediate electrode that acts as the counter electrode and that acts also the working electrode in the supercapacitor have the good performance for the future energy storage device. Next, please. These are the references and thank you.
Our next presenter is Mudassir H. Rathar. Be present now. Mudassir H. Rathar. Are you? Okay, the next presenter is Sandeep Sharma from University of Rajasthan, Jaipur.
Yes, ma'am. Please share my slides.
Yes, we are sharing. Sandeep Sharma,
Yes, ma'am.
share your screen.
Okay, ma'am. Is it visible, ma'am?
Yes, it is visible.
Okay. Good morning to all. I am Sandeep Sharma, research scholar of University of Rajasthan. My topic of presentation is the degradation of dyes using biologically synthesized nanoparticles by aloe barbadensis leaves extract. I use aloe vera plant to synthesize the nanomaterials. As all we are familiar with the approaches of synthesis of nanoparticles, we use the green synthesis method, and plant used as a metal as a reducing and capping agent. This is the formation method of nanoparticles. These are the some applications. These are the challenges. Why we use green synthesis method, that it is eco-friendly approach which produce no toxic byproducts. It do not requires any type of experimental arrangement, just like high pressure, high temperature, and other heavy requirements. This is the main reason to choose this thing. These are the materials for synthesis of copper oxide nanoparticle. We use copper sulfate pentahydrate as metal precursor salt. And for zinc oxide, we use zinc acetate and sodium hydroxide pellets to maintain the pH, and aloe vera leaf as a extract as a reducing and capping agent. This is the synthesis process. 2.5 gram of copper sulfate pentahydrate mixed with 100 ml DI, and pH get managed with the help of sodium hydroxide pellets, and the solution get stirred at 50 degrees centigrade for 3 hours. And after stirring, we found that the solution becomes blackish in color. This is the main beauty of green synthesis, that we can found the formation of nanoparticles with naked eyes. Similarly, we can find a white precipitate for zinc oxide nanoparticles. This is the basic process for the synthesis. First, plant leaves, then extraction, then plant extract mixed with metal precursor salt, then stirring at different temperature at different pH, and we can found the nanoparticles. These are the characterization techniques. For structural and morphological parameters, we use XRD and FSM, and for optical characteristics, we use U visible and FTIR. This is the comparative study of FTIR spectroscopy. Both FTIR spectra reveals the details of functional group that are attached with our sample. The peaks below 700 shows the formation of metal oxide bonds. So both FTIR spectra shows the formation of metal oxide nanoparticles. These are the FSM analysis. The FSM of copper oxide nanoparticles shows that copper oxide nanoparticles are of spherical shape, and the EDS also reveals the presence of copper and oxide in our sample. Similarly, the FSM of zinc oxide shows the formation of zinc oxide nanoparticle like the nanoflex structures, and EDS spectra reveals the presence of zinc and oxide. This is the XRD analysis, which is compared with the different JCPDS file, and also verify the formation of copper oxide and zinc oxide nanoparticles. This is the application part. We use these nanoparticles to degrade the cationic and anionic dyes. We use methylene blue, methyl orange, and methyl red as the sample. We prepared a solution of 100 ppm concentration and applied 10 milligram of nanoparticles. And these graph shows the decrease in absorbance under the exposure of sunlight of 8 hours. We found that methylene blue degrade about 59.92%, methyl orange degrade about 73.48%, and methyl red degrade about 73.10%. Similarly, these are the absorption spectra for degradation of zinc oxide. Zinc oxide produce high efficiency toward these dyes. It produces 81.44% for methylene blue, produces 76.46% for methyl orange, 63.30% for methyl red under the exposure of sunlight for 8 hours. These are the conclusion. We found that both nanoparticles are efficient for degradation of textile dyes, and due to the cost effectiveness and environmental friendly nature, the green route for synthesization have remarkable potential for the field of nanotechnology. These are the references. Thank you. Thank you so much.
Thank you, Sandeep Sharma. Now our next presenter is J. Vigneshwaran.
Can you share my slide, or otherwise I have to share?
Yes, we are sharing.
Yeah. May I share? Hello, ma'am, may I share or you have to share?
Yes, we are sharing.
Yeah, okay. Yeah, can I start?
Yes, you may start now.
Yes, ma'am. Thank you. Thank you for the team ICRE 2022 for this wonderful opportunity to present my work. My work is the hierarchical 3D COMN204 for ball decorated TA3CP nanosheets for supercapacitor, high performance supercapacitor application. Please go to the next slide, ma'am. The background of this work is to synthesize the major two materials. One is the mexine and another one is the cobalt magnetite to application of the application of supercapacitor. So both these materials have two unique properties that mexines are having two-dimensional material, having a high metallic and hydrophilic nature, and having a good hydroxyl terminations for capacitive applications. And also cobalt magnetite have a different valency and also earth abundant, environmentally friendliness with good electrochemical properties. Both this combination of material, we prepared the electrode for supercapacitor application. The major work of this work is to fabricate two materials. One is the mexine and also the cobalt magnetite composite. Individually, we can study the electrochemical properties of both this material, and we finally combine this material with another material. So fabricated a supercapacitor. Go to the next slide now. So this is the prime objective of my work. We already know about the supercapacitor basic properties and this different classification. So I don't want to explain this slide more. So go to the next slide, ma'am. And also this is the major application advantages of this supercapacitor. So this also I don't want to explain. Go to the next slide, ma'am. This is the literature review we have done for the individual materials like the metal oxides and mexines. So I already told that this material having a good electrochemical property and having a high metallic conductivity and hydrophilic surfaces and all, and also the this kind of same property is having the cobalt magnetite having the different valency and also good electrochemical property. Go to the next slide, ma'am. So the preparation of mexine and cobalt magnesite. First, we will take a max space for H with hydrofluoric acid. Then it will be exfoliated. After the exfoliated, the delaminated mexine will be taken as a slurry form. Then it will be mixed with the cobalt magnetite composite. Then it will be used as an electrode for a supercapacitor application. For first, we will prepare the mexine, then it will mix it with the cobalt magnetite. We will make it as a slurry and also another form, sheet form, so that I will show in upcoming slides. This CV curve of mexine and also porous activated carbon is shown here. Go to the next slide. So the basic properties of this cobalt magnesite composite are shown in here. This is the cobalt magnesite magnetite composite, so the heterogonal structure with JCPDS value matching with the 77041 structure. This is the stable structure. After the TG analysis shows that three phases of losses, different three stages of weight losses has been observed. The first stage is in 100 to 350, and second stage is 350 to 600, and the third is the 600 to 1000 degree. 600 to 1000 degree, we optimize the decomposition temperature for a stable structure, and then Raman shows the disorder and graphitic band for the COMN204 and mexine, and also it significantly indicates the 2D nature of mexine, and also the functional group analysis of mexine cobalt magnetite composite shows the graphitic carbon-carbon bond and also CW bond and OH bond also clearly shows that the material having a stable structure with enough surface functional groups for supercapacitance application. Then go to the next slide.
You have 1 more minute.
Yeah. This morphological analysis shows that three different material, that cobalt magnetite and mexine and also another material. Please go to the next slide, ma'am. And also this is the fabrication of coin cell, which I have shown which I have shown for the complete cell. And then go to the next slide, ma'am. This is the magazine electrochemical studies, that is 0 to 0.8. We have given the potential voltage and shows that this material having a excellent supercapacitive properties, and shows that 5,000 cycles in the stable cycle life with 77% of Coulombic efficiency. Go to the next slide, ma'am. This is the final slides. This is the structure of cobalt magnesite porous activated carbon, showing the excellent cyclic stability with the capacitance of 563 farad per gram, and also with the coin cell having a very good stable at room temperature and also high temperature. So go to the next slide. These are the results which I have shown here. The individual components were studied, and also it will stable in 1,000 cycles, and also shows the 93% of efficiency for both anode and cathode part together in the cell. Go to the next slide, ma'am. I have to thank these people for financial support and technical support. Thank you. Thanks a lot.
PC Bhamu is the next presenter. You may proceed now if you are there. PC Bhamu, you may share your presentation on your own.
Yeah, I'm sorry, I was muted. So
your slides are not visible.
I'm sharing now. Okay, is it visible now?
Yes, now it is visible.
Okay, thank you very much. Okay, so my talk will be basically to show the bridge between experimental people and the theoretical people, how the theoretician work. So my work is based on density functional theory. So these are outlines where I will explain that understanding of DFT, and then introduction, then my work. So how we DFT person help experimental people. So we validate their results, and then we guide them how we can overcome their special problems, and then we reduce the manpower and equipment costs, and then we can save chemical expenses.
Sorry to interrupt, but your slides are not moving. Yes, now it's movable.
Is it okay now? Is it okay now? Hello? Is it okay now? Is it okay now?
Yeah, it is okay now. Don't put.
Yes, it is okay now. Okay, thanks. So, so let's understand how the DFT scale is related with the microscope level. So we work here at the quantum level or electronic level, and we predict the property of the continuum model. So this is my work where I explain that liquid organic hydrogen carriers that is basically used for storage. So background, so there are multiple sources of energy resources, fossil fuels, but the use of fossil fuels is limited because of the drawbacks, that it commits CO2 in the environment, rivers, and it causes the global warming, and it increases the mortality rate also. Then there is another technology, but with a short lifetime and limited storage capacity, it also has some problems. So what we can do to keep our Earth green, we should look for economic and environment friendly resources. So hydrogen is the very much environmental friendly element. That is with water and methane. So as you know, one and one like that. If you put hydrogen and hydrogen, it can produce energy. So this is news I was reading yesterday. So this the French aircraft makers announced that they will test the hydrogen fuel engine in this jet. So there is a future in hydrogen energy. So, why my field is important? Because these organic molecules are very low cost, reusable, and safe, and they are efficient for storage and transportation of the H2. We can use the already available transportation infrastructure for these carriers. So this is basically my system where all the carbon atoms are occupied with the hydrogen atom. So this stage is hydrogen rich, and when we release all the hydrogen, so it is hydrogen meal. So so this is actually reusable. We can store hydrogen in the Stirling system, and this is the process where we store and use the hydrogen and vessels. I use the combination techniques. So, I will explain the minimum energy part. For experimental people, it's very difficult to check how they can easily release the hydrogen. So I will show you the minimum energy path for that dehydrogen process. So why it is important? Because in earlier days, it was very difficult for experimental people to synthesize ammonia because they required that high temperature and high pressure. So DFT people investigated how this ammonia synthesis can be easily done. So they tested that many reactions of the nitrogen, our PT catalyst, and they saw that breaking of that nitrogen was a crucial step. So in the same way, I will show you how experimental people can do easily synthesis my system and then release the hydrogen. So this is hydrogen system. We go step by step. So these are the hydrogen steps. So you see in each step there is a red bond. So that is the most sluggish reaction step. So if experimental people focus on that red step, then they can easily synthesize that or the dehydrogen system. And the step with that green circle is the IDS that requires more energy. So actually, experimental people require from us that what are the average dehydrogen energy. For the pristine system, we have a little bit higher dehydrogen energy that is actually equivalent to dibenzyl toluene. So we try to reduce that dehydrogen energy. So we
Dr. Vamu, your slides are not moving.
Here it's okay. Is it okay now?
Now we just got on the directly on the 26 number slide. I don't know.
Okay. So is it okay now?
Yes. Go ahead.
Okay. Maybe my laptop may have problem. So this red step with that green circle is RDS. That is most sluggish step in the reaction. So with that nitrogen, we predicted that if you have boron nitrogen in the organic molecule, the dehydrogen energy can be this 11.17. So BN substitution was found very suitable. So these are the kinetics.
Now your time is over.
Yeah. So this is the kinetics. So this is more sluggish equation. So yeah, this is last two slide only. So we carried out the homonomo states. So the decreasing homonomo gap so that this system is reversible. So these are my conclusions. So BN substitution was found very suitable, and our results can be very profound for that LHC compounds. So these are references and acknowledgement, and I'm open for collaboration in these fields. Thank you. If you go out, please wear mask. Thank you.
You may present now.
Is there any question?
Hello. Can I start?
Yes, you may start now.
Yeah. Good afternoon to everyone. My name is Pradeep Kumar Rajput, and my topic is presentation planning for sustainable development in the framework of renewable energy, a case study of Tawa River Basin, Hosangabad district, MP, India. Is a geographical study. Next, ma'am. My introduction of a study area. The purpose of this research is to understand the stakeholder perspective, which seem be missing in the case of energy planning process. And second one is we prepare a plan for renewable energy in the life cycle of human being. And third one, the main aim is to provide an ecosystem to use the renewable energy in terms of development. And we develop with a spatial and temporal analysis of land use, land covers, and consumption of energy required in that area, and define the way of production of energy to stakeholders by using different models to study the land use and land cover impact on climatic change condition, also by using a SWOT and HMS for planning purposes. And this helps in creating effective policy implementation in the futures and ensure the healthy interrelations between nature and culture. Next, ma'am. This is a steady area. The total drainage of steady area basin is 6,500 kilometers. Next, ma'am. This is showing a my steady area map. In the my objective of the study to promote the generation of power through the hydro power project in private sector participation, because Tawa Dam is here a small hydroelectricity power production, and to define the incentive benefits available to the stakeholders and to create a favorable environment for promoting the sectors. And last one, to lay down the framework for implementation of the projects in the terms of renewable energy. Next, ma'am. Methodology, I'm proposing a supply demand module planning for energy demand, how much energy required in that area, and developing a method of energy study module, and estimating the learning curve method for that region of case study area, and also study the socioeconomic analysis and SWOT analysis, strength, weakness, and opportunity threatened in that area. Next, ma'am. The conclusion of the we got a final plan, the water and energy sector planning for the towards a higher share of renewable energy in that area, and local planning and methodology is developed to model interlinked planning of interlinked sectors. And last, this is steady able to configure each sector has direct impact on the other sectors, and provides a sustainable planning for renewable energy in this area. Thank you, ma'am.
Hello.
Okay.
Hello, ma'am.
Yes.
Hello.
Yes.
Madam, I am ready to present, madam. Nagendra Prasad. Now I am audible, madam.
Okay.
Hello.
First we'll be having other presentations.
Shall I present, madam? Hello. Visible, madam? Hello.
Yes, it is visible.
Okay, shall I start, madam?
Yes, you can.
Good.
You may start with the presentation.
Okay, madam. Just 1 minute, madam. 1 minute. Good afternoon to all. Today I am going to present my work talk titled Enhanced Proton and PEM Fuel Cell Performance of Novel Sidechain Tape Sulfur and Polyoxide Benzyl Graphene Acid.
Mr. Nagendra, 1 minute. How many slides you have?
Yeah, I will skip, sir. Mostly introduction part I will skip. Results I will show, sir. Just 5 minutes.
Okay.
Within 5 minutes.
Yes, sir.
So, coming to introduction, PEM fuel cells, polymer membranes, and the synthesis of coming to the synthesis, preparation of the novel aromatic solvent dicarboxylic acid monomer and the corresponding novel solvent polyoxide benzimazole, and the preparation of graphene oxide, and the preparation of the corresponding intercalated composite membranes, and then PEM properties such as water properties, filling ratio, thermal, hydraulic, oxide stability, mechanical properties, proton conductivity, PEM fuel cell performance. Finally, conclusions. So what is this? What is a PEM fuel cell? It is an electrochemical device that is reacted with small amount of water and heat through a chemical reaction of hydrogen and fuel oxygen. The chemical reactions, whatever will happen on the anode side, cathode sides are designed here. So PEM is a semi-permeable membrane made from ionomers, connect only protons, not electrons. The minimum requirements of PEM must be low cost, long-term derivative, good thermal hydraulic oxide stability with good mechanical properties, and high proton conductivity must be shown with a good fuel cell performance. But first of all, starting polystyrene sulfonic acid membranes are developed by General Electric Company, and then followed by perfluorosulfonic acid membranes such as Nafium family and Acyclovir dome membranes. The one of the disadvantages of these membranes are they can be operated below 60 to 70 degrees Celsius, only suitable for low temperature PEM fuel cells. And one of the most disadvantages of this perfluorosulfonic acid membranes such as Nafium family and Acyclovir dome membranes are found to be proton decreases at the high temperature, and oxide stability decreases, mechanical mechanical strength, methanol cross will be decreases at high temperature. So in order to overcome these disadvantages, alternate polymer networks developed by several authors, researchers, such as sulfuride polybenzimidines and sulfuride polyethers and sulfuride polyamides. So in our laboratory, we concentrate on sulfuride polybenzimidines. So according to literature survey, the presence of the sulfonic acid group on the from the main chain exhibited low PEM fuel cell performance, and while presence of the sulfonic acid away from the main chain of the polymer backbone exhibited high hydrogen stability, oxidation stability, high proton conductivity PEM fuel cell performance. Based on this literature, we designed. Based on this literature, we applied this concept in polybenzimidines. There are three kinds of methods available for the polybenzimidines. Out of them, the third method is a very good method compared to the method 1 and method 2. Because of method 1 and method 2, we will get side reactions and you cannot control to degree of sulfonation. And but by using third method, we can control degree of sulfonation, and then we can avoid the side reactions also. So we till now these are the second type sulfuride polybenzimidines. So based on this idea, we designed one novel polymer electrolyte, novel dicarboxylic acid monomer bearing sulfonic acid as a side chain away from the main chain. So these are the various synthesis steps, and this is the FTIR number of the monomer. This is the proton number spectroscopy. This is the depth analysis. This is the C13 depth analysis, and this is the polymer, whatever we prepared polymer NMR. So according to literature survey, based on Keith Scott articles, they inserted graphene oxide to the polymer, and then they developed the enhanced PEM fuel cell performance polymer membranes. Based on this literature survey, we synthesize the graphene oxide. Till now there are three methods are available. Out of them, first one Hammer methods, modified Hammer methods, and improved method. But we selected improved method because of simple protocol, high yield, no toxic gas compared to the first one, second one. So these are the whatever we got the result, FTIR spectra and the TGA and wax analysis and Raman spectra and SEM analysis. So these are the synthetics. These are the types of the interaction between the polymer and the graphene oxide. This is the synthetic steps of the whatever we prepared membranes in our laboratory. These are the types of hydrogen bonding interactions in dry form and wet form. And coming to the TGA analysis, as the GO content increases, the thermal stability of the membranes gradually increased. And then here also the TGA DSC from DSC values, the TGA values also found to be gradually decreases. Coming to the photoexide analysis, the presence of the broad peak between the 15 to 30 degrees is due to the presence of the polymer, and then while the 10 to 11 degrees is due to the GO peak, indicates the GO is successfully inserted between the polymer chains. And these are the various physiochemical properties. Coming to the water phase sterility proton conductivity, as the content of GO increases, the proton conductivity, oxidation stability both increased, and in the same manner the mechanical properties also increased, but hydrogen stability also increased for a 9 weight per stage, 11 weight per stage. At the end, coming to the proton conductivity, the 9 weight per stage, 11 weight per stage membranes are expedited more compared to the NAPN-117, and the fuel cell performance also found to be more compared to the NAPN-117. So finally, we concluded that the 9 weight per finally we concluded that we successfully synthesized the monomer and then polymer and intercalated composite membranes. Coming to the physiochemical electrochemical properties, the thermal stability, mechanical properties, and enhanced while the addition of GO content in the SPO membrane. The composite selects 9 weight per stage, 11 weight per stage showed high oxidation stability, high proton conductivity PEM fuel cell compared to the NAPN-117. Finally, we conclude that the designed membranes are expected to be promising PEM fuel cells for PEM fuel cell applications. So acknowledgements to my supervisors and DC members and the financial assistance. So
thank you. Our next participant, Anjali, can answer all the questions.
Yes, ma'am. Ma'am, can I share my screen?
Anjali Kesarwani from IAS Plateau. Anjali, you may share your presentation from your screen.
Okay, ma'am. Ma'am, is it visible?
Not visible. Yeah, it is visible now.
Okay.
Make it a slideshow mode. Yes, you may start your presentation.
Okay, ma'am. Thank you. I am Anjali Kesifani, pursuing Masters in Microbiology from ISDMW University, and I am presenting my project work, and it is about the biosynthesis of iron nanoparticle with by using banana extract for dye decolorization, which is coming from the textile industries. And as we know that by increasing population and by urbanization, pollution increases, which means then generation of waste, and this waste can be of many types, that is solid, liquid and gaseous. And like every waste generate some residue and it damage the environment. Likewise, if we talk about the dye, then it is made up of two components, that is chromophore and oxochrome, which inhibit the penetration of light in the water body, which ultimately decrease the living organisms of water and affect the environment. Although there are a lot of methods to treat this dye and other pollutant which is coming in the water bodies, like ultrafiltration method, precipitation method, but this is very expensive and it is not very good for the dye decolorization or for removal of dye from the wastewater. So we have combined two methods, and we have combined solid waste with the liquid waste, where we have reduced the solid waste to form the nanoparticle, which is used for the treatment of dye. And there are two methods for the biosynthesis of the nanoparticle. That is, either we can synthesize it from the chemical method, physical or biological. Here we have used green method, that is biological method, for the synthesis of nanoparticle, and this is a methodology what I have used for the synthesis. Here I have used kitchen waste like banana peel. I have taken 25 gram of washed banana peel and mixed it with 75 ml of distilled water and boiled it at 85 degrees Celsius for 10 minutes. There I have got this yellow PPT, and after the filtration and stored at the 4 degrees Celsius, I have got this brown colored filtrate that is used as a reducing agent. And after combining it with the precursor, that is ferric chloride, in the proportion of 2:3 proportion, we get a black color solution, that is nanoparticle. And by in this method we have not used any other physical method and other expensive method, that is like for heat and pressure. It is a very common method where we have used normal room temperature for the synthesis of this nanoparticle. This is a result that I have got. First one picture, this is a banana peel extract that is combined with the FeCl3, where we have got this black color solution, that is a nanoparticle. And after the centrifugation at the 7000 rpm for 10 minutes, I got this filtrate. And after the drying of this filtrate at water bath for 100 degree Celsius, we get this powder form of nanoparticle that we have characterized for the UV spectroscopy and for the zeta potential. And we have tested it for the dye decolorization and as well as the antibiotic activities. This is a result for UV spectroscopy. This is a peak which show surface resonance peak, which we have got at 240 nanometer. The next one is the result of zeta potential, and the size range of nanoparticle that we have synthesized is varies between 0.54 to 1.5 D nanometers. This is a graph which depicts the dye decomposition, percentage dye decomposition, that we have taken 100 mg per liter of methylene blue at pH 10, and after the exposure of the sunlight for 30, 60 and 90 minutes, we see that with increasing IONP concentration and with the time, the decomposition of the dye increases with time. Dye decolorization is affected by different parameters, and one of this is the pH.
And we have seen that at pH 6, the decomposition is very good and it is very effective at the pH of 6. Then we have also tested that IONP for the antibiotic activity, and we have taken gram positive as well as gram negative bacteria for the effectiveness, and we have seen that gram positive, like example like Bacillus, is more effective as compared to the E. coli against this IONP. And it shows that with increasing IONP concentration, the viable cell count decreases with increasing time limits. Like at 72 hours, the peak is at lower absorbance, and at higher concentration it shows the higher effects. The conclusion of my work is that we can successfully synthesize by using green method. By using green method, we have synthesized iron nanoparticle, and which is cost effective and environmental friendly, and by almost 20 to 25% of dye decolorized by using these IONP, and it is effective for the gram positive and gram negative bacteria as well. These are references.
Thank you, Anjali. Done with session second oral presentation of the conference. Moving right along, it is my pleasure to introduce our guest speaker, Dr. Panagiotis Grammatikopoulos. He is assistant professor at Osaka University, Okinawa, Japan, Department of Engineering, University of Liverpool. Dr. Panagiotis is a computational material scientist and nanotechnologist with extensive experience as a simulation expert, experimental nanotechnology groups, and involvement in industrial research. His research lie on fundamental processes regarding nanoparticles, but extend to device fabrication and application, including gas and biosensors, batteries, hydrogen storage, etc. He has worked as research associate for NCSR Demo at the University of Greenwich in 2011. He has also collaborated with the University of Helsinki as a visiting researcher. Enos is peer reviewer of 38 international journals and national keynote talks and 20 and poster presentation national conference.
Thank you so much.
Hello, can you hear me? Okay, I have some feedback, so it's quite difficult. Anyway, thank you very much for your kind introduction, and I would like to thank the organizers for giving me this opportunity. It's been very nice since I have had the chance to meet and see again some of my old friends and colleagues in Japan, and also I got the chance to attend a few of the very nice presentations, and also see people whom I had never met before but knew of. So greetings to everyone from Greece, where I'm currently located right now. But the work I'm going to present was mostly done in Japan at the Nanoparticles by Design unit in Okinawa, and partly at the Particle Technology Laboratory in ETH in Zurich in Switzerland. So my presentation is slightly different than the ones that have come before. It's mostly on trying to figure out a good solution to create battery anodes, lithium-ion battery anodes based on silicon, which will have big advantages compared to the current ones. So we used nanoparticles. My group in Japan was on nanoparticles, so that's the main idea. So let me first start with some economics of lithium-ion batteries. Lithium-ion batteries, as you probably all know are getting more and more widely used. 7 billion units were sold in the whole world in 2019, and there is an expected rise in sales. The main drivers for these upsurge of the impact of the lithium-ion batteries is mostly the automotive industry, electric cars, electric vehicles, and also this has been the use of lithium-ion batteries has been promoted by favorable government policies. There is growing demand, and the policies are changing to enable the use of such batteries for electric vehicles. Also, other consumer electronics are currently using lithium-ion batteries, so that's also helping the market a lot. Now, the projections for the future, it looks like the main target, the main market for lithium-ion batteries will still remain to be Asia-Pacific, mostly China, but then again, Japan, Korea are major players, and the expected projected market for the next 5 years is all projections estimate something around $100 billion. So some of them are a little bit higher, some a little bit lower, but the main idea is around $100 billion by 2025. And this is another projection which is slightly lower than $100 billion, but it still remains in the same order of magnitude. One of the reasons why this is an attractive market is also that the cost of lithium, the price of lithium, is declining because of the rising demand. So the anode itself is about 10 to 15% of the total cost of the overall lithium-ion battery, which means that we expect a market roughly worth $10 billion US dollars by 2025. So as you can all understand, it's a big market, and there's plenty of research going on in this area. So what are the criteria for anode material selection? Well, first of all, it's energy capacity, how much energy you can store in the anode. The anode is the part of the battery where there's the energy storage. So it's crucial to be able to store as much energy as possible. Second is performance, which if we're talking about electric vehicles, also means the speed of recharging. You wouldn't want to have a car which will have a big capacity battery, but which will take forever to charge. You want it to be comparable to what you normally have if you go to fill your tank with petrol. Also, the cyclability, which translates into the lifetime of the battery, is a very important factor. And of course, the actual size of the battery, which translates into the weight. You want to have the battery be as lightweight as possible, so the density that you can store, the energy density, is quite crucial. Of course, there are other considerations, such as the ecological design, the footprint of the creation, the development of the battery, its safety. It's not as crucial for anodes itself, but it's very crucial for the overall battery design. And of course, last but not least, never least, is the cost. It all comes down to cost eventually. So right now, most of the lithium-ion batteries that are currently being sold are based on graphite. And the graphite is a very nice material because it offers good structural stability. However, its electrochemical performance is not optimal. So on the plus side, the advantages of graphite is cheap, of course. The production is scalable, so you can make big batteries and loaded batteries. And the overall structure is robust. This is the main advantage. The disadvantage, of course, is that it has relatively low capacity, and this is directly related to the robustness. So when you charge a battery, it absorbs lithium ions, which means that the battery itself swells. And if the energy density, the amount of lithium ions that it can absorb is low, then the swelling is limited, therefore the structure is robust. So robustness comes at the price of low overall capacity, which then means that in order to have good capacitance altogether, you need to have a bigger anode, which makes the whole structure heavier. Now, a good alternative for graphite is proposed to be silicon. Now, silicon has exactly the opposite type of behavior in terms of advantages and disadvantages. It has a much better electrochemical performance, but on the other hand, its structural stability is much lower. So on the plus side, very high capacity. Silicon, of course, is also cheap. It's very abundant, so it's not difficult to get. It's lightweight, and it's, of course, being silicon, it's integratable to all things electronics, so it's not difficult to put it in a circuit. Of course, the problem is because of the very high capacity, it shows huge swelling upon lithiation, which then leads to problems such as continuous solid electrolyte interface growth, which means that the capacity goes down with time because you're losing lithium ions in the process. And of course, eventually, because of the huge swelling upon lithiation, the electrode eventually pulverizes. It has very low structural stability. So, however, the silicon is still awesome, as Elon Musk mentioned at the Tesla Battery Day recently, a couple of years ago. And let me just get rid of these. Okay. So what are the strategies now to stabilize the silicon anodes? First of all, there are two main families of strategies, either by trying to restrict the lithiation swelling in order to make the silicon anode more robust. And the other way is to try to accommodate it somehow, try to find some structure which can accommodate the swelling. So various solutions have been proposed, for example, to make silicon composite anodes, to encapsulate the anode in some kind of matrix which is not active, and therefore it contains the swelling, or to add some inactive material in order to control the overall process of the swelling. And this has actually increased the stability of the silicon-based anodes, but at the cost of reducing the electrochemical performance, making the electrochemical performance worse because of reduced silicon content. The second family is based on structuring the anodes, some type of nanostructuring mostly, or microstructuring, either making it in thin films, using nanoparticles or nanotubes, nanowires, etc. Now, this sometimes has shown increased stability, not always. Still, you can get some electric breakdown. For example, if you're using nanoparticles, the nanoparticles seem to behave quite well in the beginning, but then eventually they get pulverized as well. And of course, this idea also usually adds some fabrication complexity, which is also adding to the cost of the anode. A common example, one of the most successful examples of using the second strategy is a company called Amprius. Is a spin-off company from Stanford University in the US, and they have actually they're basing their technology on CVD synthesized silicon nanowires, and they have recently had a contract with Airbus for their new prototype airplanes. And it seems to be getting traction, this company, based on accommodating lithiation swelling by using nanostructuring based on nanowires. The anode, which I'm going to show, which I will be referred to as the OIST anode, because it was fabricated at OIST in Okinawa in Japan, is part of the second family. We try to find a way to accommodate the lithiation swelling. So let me walk you through the process of how this anode was created. So this is our cluster beam deposition source. It comprises a DC magnetron sputtering inert gas aggregation source where we grew tantalum nanoparticles. The tantalum nanoparticles were mass filtrated and then deposited on the rotating substrate. And there was also an RF magnetron sputtering, which we used to deposit silicon. And this process was sequential, step after step, and we created these composite anodes, which I'm going to show you in the next slide. So the whole process can be broken down into 3 steps. The first step is tantalum nanoparticle deposition. We use tantalum nanoparticles because we had extended experience in doing this. We deposited them on an appropriate substrate, which acted as the collector in the battery anode, the current collector. So we deposited tantalum nanoparticles and created what we called a nanoparticle scaffold. Then the next step, step number 2, is we grew the amorphous silicon amorphous film by depositing directly RF sputter silicon atoms, which created a columnar film of silicon, amorphous silicon. And the crucial point here is to stop the deposition exactly when these pillars start touching each other. These pillars have this inverted conical shape, so they start narrow, but as they are grown, they become thicker, and at some point, they start touching each other. And it's crucial to stop the deposition exactly at that stage. And this is what we call the vaulted structure. In the sense that vaults are created underneath these pillars, these touching pillars, these arches of pillars of silicon, amorphous silicon. Now, while we're doing this, some voids were created within this structure. So a third step was necessary to anneal at some low temperature to get rid of the voids, to make each and every of these pillars more robust by itself. So what are the advantages of this structure? Well, first of all, the whole deposition method is integratable, and it's also ecological. There are no binders, no solvents, no chemicals used, so it's clear whatever you deposit remains on your anode. The fact that we have this layer of metallic nanoparticles at the bottom improves the adhesion between the silicon anode and the collector. It also prevents interdiffusion of atoms from the anode, from silicon, into the collector, which is usually copper foil or copper foam. So there's no interdiffusion of copper atoms or silicon atoms. And of course, the particles being metallic enhance the electrical contact between the anode and the collector. Now, I mentioned that a part of this anode is tantalum, but we need to emphasize that it's a very, very small amount of tantalum. So it's the overall anode structure still remains almost purely silicon. More than 99.5% of the structure is still amorphous silicon. This structure also creates a high surface area to allow the lithiation process to happen. And of course, the voids in between these pillars can be used as fast lithiation paths for lithium ions to penetrate the overall structure. And the lithiation then starts from the surface of these pillars towards the body of the pillars along the whole height of the structure. And this also means that there's plenty of space available for anisotropic swelling, which means that when the anode swells after being lithiated, there's plenty of space to accommodate the stresses that are being created. And of course, the fact that the pillars are clamped with each other increases the stiffness of the overall structure. So even if there is some stress being present during the lithiation process, it can be relatively well accommodated by the pillars being clamped with each other. Of course, the surface, since the pillars are all touching each other, they create a continuous surface. So the surface is sealed, which also helps creating a stable solid electrolyte interface, which can be detrimental if it's unstable for the lifespan of the anode. Another quite important thing is that the pillars, the way they are grown, are amorphous from the beginning. There are plenty of cases, plenty of examples in the literature which show very nice nanostructured crystalline silicon anodes, which are very, very efficient for the first cycles of lithiation to lithiation, but after a while, they get amorphized because the whole lithiation process is an alloying process. So the overall structure of the material changes during lithiation. So to start with amorphous pillars means that after the delithiation happens, after the battery is discharged, the structure goes back to its initial shape and its initial condition. So there's no deterioration of the performance with time. And of course, the main advantage is that you can repeat the process of creating the structure for a second time, and you have this possibility to stack the pillars vertically. And if you do it twice, you can create what we named the aqueduct structure, because it kind of, at least in 2 dimensions, looks like this Roman aqueducts of the ancient times. But of course, you can repeat this process as many times as you'd like and go beyond this aqueduct structure and increase the overall silicon amount, which is also crucial. And the overall design is flexible, controllable, and scalable. So there are plenty of different types of advantages in this strategy. So what are the main features? This is what I showed you so far is just a schematic. We've done a lot of experimental and computational verification of what we claim. For example, we demonstrated the growth mode using large-scale molecular dynamic simulations. What you can see in this animation here is the growth of the pillar, which is based on the shadowing effect created by the tantalum scaffold. There are other simulations in the publication, for example, where we didn't use the silicon, the nanoparticle at the bottom of this structure, and then we had continuous amorphous film growth, which had completely different mechanical properties than the film grown in columnar form. And this is an example from the elastic modulus measurements based on AFM measurements. And you can see that the first structures called 15C and 25C and 35C, C stands for columnar. When the columns have not touched each other yet, they're becoming more and more robust. The elastic modulus is increasing. But when we reach exactly the point where we have the nanovolt, you find that the elastic modulus is the optimal, the highest value. This is the structure called 54V. V stands for nanovolt. And of course, if we kept increasing the thickness of the film without a second layer of tantalum nanoparticles, then we get what we call the sedimentary structure, where we have a thick amorphous film which has a much lower elastic modulus, because it's becoming more like a sponge, because the annealing process is not enough to remove all the voids which are trapped inside the structure. This is what an aqueduct structure looks like from an SEM image. You can clearly see the point where the first layer of pillars stops there is a deposited layer of tantalum nanoparticles in between, and then there's a second layer of silicon pillars. And of course, we've done a lot of electrochemical performance measurements. Here you can see the energy capacity retention after 100 cycles, and you can see that especially for the aqueduct structure, the double layer structure, the capacity is quite high, about 3000 milliampere hours per gram. And the Coulombic efficiency reaches, especially for the aqueduct structure, reaches almost 100%, which is quite spectacular. And this is an SEM post-mortem image. This is the, we tested the mechanical stability of the structure after cycling. And this is what I'm showing you here is the vaulted structure, the single layer vaulted structure, which we had to mechanically remove from the support in order to be able to take this SEM image. Whereas in other cases where we had a fully sedimentary structure, a continuous film of silicon, after a few cycles, the whole anode was delaminated, completely destroyed because of the stresses induced by swelling, the swelling due to lithiation. So this technology is now at the technology readiness level number 3, which means that we have demonstrated the proof of concept both analytically and experimentally. So how does our architecture fare with existing technology? Here's just a few examples taken from a relatively recent review paper at Nano Energy. There are various anodes which were created, synthesized with different methods, salt gel reaction, CVD, and so on. And on the right-hand side of this table, you can see some of the electrochemical performance measurements. And this is the OIST anode, which is based on a CBD, cluster beam deposition, and physical vapor deposition combination. And you can see that the discharge capacity is almost is higher than the reported ones. But then again, I would like to emphasize that the actual numbers themselves are not really important because our anode is not fully optimized yet. So in a previous study we did in 2017, we did a multi-layer anode with many layers, and we got we found the potential of a very good structure there. But at the time we hadn't completely identified the critical point of stopping the deposition exactly when the pillars touch each other. So we had many layers, a lot of quite high concentrate content of silicon there, but we hadn't optimized the structure. In a recent 2021 paper in Communication Materials, we actually did all the mechanical analysis, the mechanical stability analysis of the anode, but we have not yet put the two together to make a thicker multi-layer structure with optimized characteristics in terms of the architecture, which will be based on our recent findings of the importance of stopping at exactly the nanovolt phase of the deposition. So what are the challenges for the commercialization? We have demonstrated, as I said, the improved electrochemical and mechanical response of the nanostructure unit. So what I showed you was a unit which can be repeated many times in order to build the anode. And of course, we have found that the vertical repetition in multi-layers is actually beneficial to the performance. What needs to be done in the future is to further optimize the structure, the dimensions, the materials used, the numbers of layers. We don't need to use tantalum nanoparticles, for example. We just chose to use those because we had a lot of experience in depositing tantalum nanoparticles. And of course, we need to scale up the fabrication process. There are various thoughts about replacing even magnet and sputtering with other CVD methods in order to have a much higher yield of nanoparticles and film. And of course, we need to benchmark our nanostructure against similar approaches like the Amprius, anodes that I showed you, that I talked about earlier, both in terms of performance, but also in terms of environmental impact of the actual growth and synthesis. And we believe that this structure can be applied for high-end, mostly high-end lithium-ion batteries, because we accept the cost will be higher than graphite, so it will be difficult to replace graphite immediately. But there are applications where energy density over weight is important, for example, aeronautics or space applications, and this could be a first step of applying this technology before we have completely solved the scaling up issue. And of course, we believe that the main idea of the structure can be used for other applications which require variable high-stress cycling. Hydrogen storage might be an option. I think plenty of you here are experts, much more experienced in hydrogen storage than I am. So any ideas of using such a structure could be interesting. Also bioimplants and so on. We have filed for a patent which should be released any day now. With this, I would like to thank mostly the collaborators my co-workers who worked on this, mostly Marta Haro, who was our electrochemical expert, who led the project, experimental aspect of this project. Vidya Dar Singh, who is actually in the audience, I believe, today, and who was the responsible for the deposition method, which was also used by other co-workers eventually, but Vidya was the person who actually was in charge of the deposition of the particles and the film. Junlei Zhao, who performed all the simulations and who actually provided the main answers to some questions, some fundamental questions we had in order to understand the structure. And of course, Professor Mukhles Sowan, who was the guy who initiated this project, who had the initial idea of intercalating layers of tantalum, of nanoparticles and continuous film. With this, I would like to close my presentation mentioning that I'm now in Greece. I'm in transition. I will start a new position as associate professor at Guangdong Technion Israel Institute of Technology in China in about a month from now. So I will be looking for hiring postdocs or lab technicians. Sorry, okay. Okay, and well, that's all for me. Thank you for your attention, and I will be happy to answer any questions anyone might have. Thank you very much.
Thank you so much, sir, for giving your valuable time and insights on the topic. Now, I would like to invite Dr. Chhagan Lal to thank you, sir.
Hello.
Hello.
How are you? Fine.
I'm quite good. It's quite good to see you. I saw you speaking with Shushan Kumar yesterday. It was nice to see. It's like a reunion. I'm quite enjoying it. It's very nice.
You are now in Greece.
I'm now in Greece temporarily. Preparing my visa application for China, and will be moving to China hopefully soon. I don't know exactly the date, but hopefully soon.
And I really thank you for special your lecture. I think I have tried to change your lecture with a short.
Yes.
And
thank you very much. It was quite useful, actually.
Okay. Have a nice day again. Okay.
Thank you. It's nice catching up with you.
Next month we will again meet for another conference. Maybe.
Okay. Yeah, please let me know.
Thank you so much, sir. And again, I want to thank you, and I'm feeling very grateful that our previous chairperson of the last session, Dr. Ranveer Singh, who were with us and chaired the session. I'm very grateful and thank you so much, sir. Thank you so much that you gave us your valuable time. Now moving forward, the more that you read, the more things you will know. Here with these lines, the next distinguished to honor us with his words is Dr. Balaji Subramaniam. Dr. Balaji is an assistant professor at Mechanical Engineering, Indian Institute of Technology, Tirupati. Dr. Balaji did his PhD from Zurich, Switzerland, Swiss Federal Institute of Technology. He has completed his MTech in aerospace engineering after BTech in mechanical engineering. He is recipient of many alumnus awards like prestigious Swiss National Foundation Fellowship for postdoctoral research at University of California, GE Management Award for filing 5 invention disclosures in 2008, Design for Six Sigmas, GE Active Volunteer Award by Lions Club in 2010. His title of the talk is Wind Energy Opportunities and Challenges. I invite you, sir, for the talk.
Yeah, thank you. Let me share the screen. I hope you can hear me. Okay, let me share my screen. Just a second.
Sir, we are unable to hear you.
You cannot hear me. I'm sorry. Hello.
Yes, you are audible now.
Okay. No, I was speaking always. I guess there was some internet issue. I'm sharing my screen. Okay. Is my slides visible?
Yes, slides are visible now.
Okay. And let me also turn on my video.
Yes, yes.
Okay. So I hope you can see me. Okay.
Also visible.
Yeah.
Slides.
Okay, fine. Thank you. Thank you so much. Thanks for those wonderful words. I'll put it in full screen mode. Okay. So thank you. Hello, everyone. My name is Dr. Balaji Subramaniam. I'm going to speak here on wind energy. I'm switching gears. I'm speaking, probably I'm the only speaker on wind energy in this ICRE. Before I start, I would like to thank the organizers for inviting me, okay, for giving me the opportunity to speak in this conference. I have structured my talk in a way in which since it is since most people will not be familiar with what are the opportunities available in wind energy, okay, and how it exactly works. So I have structured it in a more general way to make it more useful. So let me start. Okay. It's not navigating. Just a second. Yeah. So yes. So here is the outline of my talk. So I'll start with the introduction, then I'll present some motivation and objectives. Then I'll give you an overview on what wind turbines are all about and what makes wind, how to design wind turbine, and how the wind turbine aerodynamics, because aerodynamics is what drives it. Okay, so my research here at IIT Tirupati focuses mainly on, we are trying to build some novel test facilities, which is a drone-based measurement system for, we are trying to build a drone, okay, a fixed-wing drone, which will help to measure the flow structures in a wind farm. Okay, so that is one which we are actively working on, and parallelly we are also working on setting up a wind tunnel test facility here at IIT Tirupati. This will be, the nice feature of this wind tunnel test facility is that it will have the lowest turbulence wind tunnel in the country. Okay, so there are a lot of studies which needs novel facilities like these, especially transition facilities. And if you want to do some fundamental research, you want to a very low turbulence wind tunnel, where you can vary the turbulence level and test for different conditions. So we are working on designing it from scratch fully. Okay. So we are involved in that. And apart from that, As you know, the place where I am here, where I'm presenting to you, is in the East Ghats of the Eastern Ghats range. Okay, it passes through, even the famous Tirumala temple is here, in part of the Eastern Ghats. Okay, so you see pockets of a lot of good wind resource sites. And in fact, even the Tirumala temple has 6 wind turbines installed in it, because they realized that they can keep generating power with wind turbines. Okay. And they are, they installed it some time back, and they are adding 6 more, because those initial 6 were so successful. Okay. And now we are trying to map this whole terrain. We started to understand the wind flow field in this terrain, and identify which are the pockets which are, where there is a lot of wind resource available. Okay. So with this, I'll start with the introduction. See, wind energy is growing rapidly. Okay, so you will see that if you look at, if you just Google it, you will see that in the last 20 years, continuously, there is a double-digit growth of wind energy. Okay, so here I have the data from IREA, International Renewable Energy Agency. Okay, here it shows you the growth and penetration of renewable energy. Okay, this is just the growth rate and the share of new electric generation capacity, what is installed. So you can now appreciate just from this one plot, one thing is clear, that renewable energy is gaining ground. Okay, so compared to the conventional resources. Okay, and the growth is unmistakable. It is expected to continue. Okay, in fact, it is expected to accelerate more. Okay, even Japan has jumped into it. People, here will tell you that after the Fukushima, they have started investing heavily in wind. Okay, even companies like Hitachi, they manufacture wind turbines. I don't know how many people know that. And here you have the share of global renewable energy capacity that is installed at the end of 2018. And you see here the renewable energy source. This is just the renewable energy source, and you see wind is already accounting for 1/4 of all the new, all the global wind, renewable energy source. And mind you, hydroelectricity is there for 100 years. Wind energy just started for the last 20 years. Okay, its growth has started just for the last 20 years. And here I have more plots just to convince how the trend is unmistakable. Okay, the double-digit growth rate and the acceleration of wind and solar energy is expected to continue. There is no wonder in that. Okay, here you have the share of new installed power generation capacity. All these are 2018 data, which I got. Okay, so here again, you see, this was in Europe. Okay, in Europe, wind accounted for 55.2% of all new installed capacity. Okay, 55.2. Okay, so imagine the progress which is happening in Europe. Okay, so now here on the right side, excuse me, somebody called, so I have to cut the phone. Okay, so here on the right side, you have the global wind new installed capacity at the end of 2018. Okay, this is again from Global Wind Energy Council, and here also you will see that the top countries which are in terms of if you mark the top 10 countries which have the largest installed capacities of wind energy, you will see that India is also one among them, and China is unmistakably the leader. You can clearly see from this chart. Okay, this is in 2018, but the trend now in 2022 is very similar. Okay, so this is the latest data when I got the chart, and that brings me to my motivation. Okay, so you see a lot of unmistakable trends are happening around the world, which is difficult to miss. In 2017, for example, you see that the tender prices in Mexico cratered at 0.02 kilo per kilowatt hour. Okay, even in India it happened, but this became a news. Okay, so it became a news, and in Germany, the first subsidy-free offshore wind farm was tendered out in 2018. Okay, and all this happened within a span of last 5 years, and the Global Wind Energy Council has forecasted all these trend, I mean, something which is making big headlines, which uproots the whole conventional way of thinking, is going to continue in the near future. So it is going to become cheaper. It's not only the reason why it is penetrating is because the price is falling. Okay, the price per kilowatt hour is undoubtedly falling. Okay, so that is why we expect it to be cheaper than fossil fuel. Now coming to the scenario here, do we have enough resources in India? Okay, so the potential of wind and the solar energy also, if you see, it will correlate very similar to what you see here in the picture. Here is the global wind atlas. Okay, and you see all the coastal zones and the lake, in the Jammu and Kashmir in the top, the lake, you see that you have a very good wind resource. Okay, a lot of wind resource where you can just keep mining power from them. And that is the reason why you will see that the installed capacities of wind, as it accelerates, more and more of these sites get populated with wind turbines. So if you are traveling, especially along the western coast, okay, even up to Gujarat, okay, you will see that the reason for a lot of wind turbines is because of the resource available. Okay, in fact, as I understand, the Indian wind, it's called NIVE. Okay, the Indian wind in the certifying agency has started out for the offshore in Gujarat and Tamil Nadu. Okay, so they are actively working on setting up the pilot projects for Gujarat and Tamil Nadu. You can see in their website, okay, because of the resources. Okay, the large offshore wind farm plants. Okay, they started working on them. Okay. And now coming to what is the state of scenario in India. Okay, fine, wind is doing good globally, but if you see, there is no reliable wind turbine OEM, megawatt scale OEM, a large OEM in the top 5. Okay, so the top 5 you can see it starts from Vestas, and then from Goldwind, and followed by Siemens, GE, and Envision. Okay, and then it continues. We have Suzlon, but it is very small, and in kilowatt. If you go to kilowatt scale range, okay, there is no reliable wind turbine OEMs. They will tell you. Okay, even if you want to search, there are hundreds globally. Okay, so Make in India is an opportunity for indigenous design and development, and it is one of our goal to design the wind turbine blades here. Okay, and I'm working with my colleagues to realize this dream. Okay, so now why wind energy? I mean, you might have read in news that renewable energy, anyway, no doubt that because of the global warming and carbon emissions, you want a clean energy source which you can trust, which can work reliably day and night. Okay, and this is a clean zero emissions source. You just to put it up, it will work for 20 years. Okay, and the air quality, water quality is not going to be affected. And because of climate change, you will see that the more and more of these turbines are getting installed now, both in Europe, US, and in Asia. Okay. In fact, in US, the Midwest is called a giant wind tunnel because so much wind resources available. Okay. In fact, I believe that I don't have it referenced here. Harvard has published a study which they claim that you can just keep powering US whole economy over and over 2 or 3 times just with wind. Okay. So much wind resources available. It's untapped. Okay. So now with it will, of course, it will reduce our dependence on fossil fuel, the exchange, the dollars that you spend will be okay. So that, it is expected to continue. This trend, as I said, whatever I showed was a global trend. In India, if you see, the similar trend is catching up, but at a slower rate. Okay, but it is catching up. Okay. There is a delay between the global acceleration and the acceleration that is happening here. Okay. And the technological development of today. So what we have today, if you see, 50 years back, when I was working in GP, the standard was that you have a 1 or 1.5 megawatt wind turbine. Okay, that was the standard work horse with which technologies at the time. But now if you see, okay, the turbines have got bigger. Okay, so they have already, you speak on terms of 2.5 and 5 megawatts getting very common commercially. So the turbines have become larger. Even 10 megawatt prototypes, okay, they are tested and they are installed successfully in Europe. Okay, so now most manufacturers are working on 10 or larger megawatt machines. If you see most global manufacturers, okay. So and they are targeting the offshore market because offshore you have so much wind resource. So you just put a large wind turbine. All you need is, you see, 10 megawatt means you need maybe 100 turbines, which will produce as much energy as a nuclear power plant. So that is a big advantage that you have. Okay, now we will see how the things work. Okay, what makes wind first? If you start with wind, is caused by energy radiated by sun. Radiated to earth by the sun. Okay, and this wind is a form of solar energy. Okay, so the radiation from wind that heats up and it drives the flow. So what we see. Okay, so this only advantage that you have is that you have wind, especially in early mornings and in the late evenings when solar energy is not available. Okay, so when solar energy is not there, you will see a lot of wind there. So it is going to be complementary, wind and solar. Okay, as we make as it progresses and as we install more and more of them, it is going to work in a complementary way. Okay. So the planetary boundary layer, if you look at the planetary boundary layer, by planetary boundary layer, I mean that everything below 10 to 15 kilometers. Okay. So you see that there is a diurnal variations which is a characteristic feature of the planetary boundary layer. Okay. So diurnal means you have that day and night cycle. Okay. So the wind is operated by that because sun heats it. Okay. And there are a couple of stability regimes which we have identified. Okay. And this has this physics of it drives the design of wind. Okay, so the convective boundary layer, for example, okay, it induces turbulence. Okay, and the wind turbines are rated based on the turbulence class. Okay, so if you have a stable boundary layer or an unstable boundary layer, or it makes a difference. Okay, it affects the life of the wind turbine, and you need to consider this into account. In fact, in my PhD at ETH Zurich, we measured in a stable, neutral, as well as unsteady atmosphere. Okay, and behind a wind turbine, we were able to characterize how the flow behaves behind the wind turbine. Okay, so now of course, some simple things are that the turbulence is key because it affects the life of the wind turbine, and the turbulence is again driven by the sun. The sun heats the surface, and you have the evapotranspiration, which generates the turbulent eddies. Okay, and atmospheric turbulence is anisotropic. Okay, so it depends on the surface roughness and it depends on the vegetation. How the terrain is there. If the terrain is complex or simple, it affects. Okay, all this affects the amount of power you get from the turbine. So a good wind forecast is often critically dependent on the accurate estimate of these surface fluxes, what you have. Okay, and the mean wind speed profiles, which is again another very important driver. You want to predict how much power a wind turbine will generate, then you need to know the mean profile in the boundary layer. Okay, so we already said that there is unsteady, in neutral, or in steady atmospheric conditions. You have different wind profiles that you can expect. Okay, so here you have, the famous, we use a log law to model the atmospheric profile. Okay, and this is a standard practice which is used. Okay, or the power law is also used. Okay, so you both give you an idea of how the boundary layer over the land how it, what is the profile of the boundary layer, and which helps us to predict how much power a wind turbine can generate. Okay. Once you put a wind turbine here in this site with this wind profile, how much is the power you can generate? Okay. So this is of course, this is not the only factor. You could have gust. Okay, gust is the increase, a sudden brief increase in wind speed that you see here. Okay, so you can have gust even at low level gust, which you can have, especially in a complex terrain. Okay, and these things are maximum for a few seconds, and this will also affect the performance of the wind turbine. Okay, which is located there. So this also must be taken into account, especially if you want to understand the life of a wind turbine. Okay, so based on all this, IEC, which is the certifying agency, which has identified wind classes, and these wind classes are based on where at each site. Okay, what kind of wind do you expect? In some places, as we have seen, even in the map of India, we have seen that large wind speeds can be quite common. Annual average wind speeds are quite large in some places. Okay. For example, in Leh, Ladakh, we saw that. Okay, so the average wind speed is very large, and some sites which have a low wind speed but still decent. So when you make the wind turbine, you take this into account because each site has a different level of turbulence level, and this has to be taken into account. So the turbines that you use for a site is chosen based on the class, okay, the IEC wind class. Okay. So this plays a crucial role. Okay, so in wind power, okay, especially in wind resource assessment, when people do it, they tell you. Okay. And first we will see what happens before the turbine, that is the wind, and then we will come to the turbine. Okay, actual turbine blade, and I'll give you an overview on that. Okay. Now, wind resource assessment, meteorologists will tell you that they have towers, which are the wind measurement tools, okay, which they collect data, and you have variable distributions like these, which map how a site behaves. Okay, because if you want to get the average wind speeds at different sites, you need to have measurement of wind. Okay, you measure wind speed at a site for say 3 years or a certain time period, and then from that you can get a reliable estimate. Okay, how the wind speed at a site varies. Okay, what is the frequency and what is the distribution of wind speed at that site? You can get an idea. And these lot of statistical tools play an important role here. Okay, and these meteorological tools play a crucial role in getting the map that I showed you for India. They are they use towers like these for validation. Okay, so to create a wind resource map, okay, so you need to have some confirmation. So these the wind resource assessment is a very hot research topic, okay, because it has to be done with a very low uncertainty. And one of my goals is to map the wind resource in this area where I am presently there, okay, in the Chittoor district, okay, in the Eastern Ghats. Now coming to the turbine, okay, how much energy can you extract from it? Okay, wind turbine, see, when you what happens in a wind, the physics is simple. Okay, so physics is wind is blowing, okay, and the energy is captured by the turbine, and it cannot, of course, bring the wind to halt. It cannot. It can capture energy, but once you capture energy from wind, it slows down. Okay, and it cannot stop. Okay, it cannot stop. Otherwise, it's not going to. Then the flow is not going to happen. If the wind stops to zero speed, the flow is not going to go through. The upstream flow cannot go through. So the full maximum capacity, what the maximum wind energy extraction capacity, okay, is called Bed's limit. Okay, this can be mathematically derived. Okay, and this the amount of energy that you can extract using a wind turbine cannot exceed this 59, this magic number, 59.3% of the input, upstream input condition, which is the V1. Okay, the energy that you have there, okay, of course. Okay. So it cannot exceed that. Okay, so there is a physical limit. Okay, how much you can extract, and I mean that has to be understood. And still, we are a long way from this. Okay, our wind turbines, the CP that we get here, there is a lot of scope for improvement. So a lot of research work can be done to improve it. Still. Now, how the blades work? The lift design of the blades. The lift design implies the same principle that you have. That is the whatever enables the airplane and bird flight. It's the same. Okay, so here the logic is the same. And I mean, you have aerofoils. These blades, if you take a cross section of the blades, you have aerofoils. Okay. And the pressure differential that is created as the flow passes through the blade between the upper and lower surface, this creates the torque. Okay. This creates the torque to drive it to generate power. Okay. And so you lift the blade with this. Okay. But since the blade is, you have one end of the blade is held, so it keeps rotating. So the design is simple. Okay. But the challenge is that what kind of airfoils to choose. Okay, what kind of airfoils to choose, which is it the same as what you have in aeroplanes or bird wings? Okay, so what is the characteristics of making a good airfoil? Okay, the shape matters. The airfoil shape matters. A lot of research goes into it. Okay, so still a lot of research goes into determining what is the best shape at each section. Okay, at each section, what is the best shape for maximizing this to reach this as close to as possible. Okay, to reach the bed's limit as close to as possible. And I mean, when people start working on it, they will tell you that I mean, the law of similarity means that you have the non-dimensional parameters. Okay, so I mean, it doesn't matter which size turbines you work with. Okay, do you work with these coefficients or these non-dimensional coefficients? Okay, and since this wind turbines usually work in at the low Mach number conditions. Okay. Sometimes for a very large turbine, the tip of the blade could reach near the compressibility effect, because the tip of the blade, you see that it will, I mean, the speed with which it travels, okay, the R omega, the speed with which the blade tip moves, it is, I mean, it is of, I mean, order of like 0.5, 0.6 of the sound speed you can get for a large winds, it can enter into the compressibility. Okay. So the two most important non-dimensional parameters when we start working with this are the tip speed ratio, when we start working with it, and then the Reynolds number, which we calculate based on the rotor diameter. Okay. So these two are very important, and performance is monitored. Performance of a wind turbine is monitored in terms of the thrust and power coefficient. Again, these are the non-dimensional parameters which are very important. And I mean, Professor Schlugel, he published, I think it was in 2012. Okay, so he published this wonderful picture, which clearly demonstrates how this coefficient, the tip speed ratio, how it plays a crucial role in the design of wind turbine. Okay. So what impact the tip speed ratio has on the performance of a wind turbine? If the tip speed ratio is too low, okay.
Please.
Hello. I think, yeah. Can you hear me? Yeah.
A little closer.
I'm sorry.
Your voice.
Oh, my voice is breaking.
Yeah. Now it's audible.
Now it's audible. Okay. Yeah. Oh, okay. I'm sorry. Yeah, please tell me that. I don't know where the mic is here. Okay. This is a MacBook.
Here to the screen.
But I will shout.
Okay.
Yeah. Okay. Sure. Yeah, sure. I mean, if you mind, I will turn off the video, because the thing is, there is a bandwidth problem. Okay. So if I turn off the video, I think it will be easier to continue. But if it is okay, then it's fine. We will continue. you don't have an issue, I'll shout. Okay, but let me know if there is an internet issue. I'll turn off the video. I'm going to finish. Okay. So tip speed ratio is an important parameter, okay, which determines how a turbine performs, especially, the efficiency of a turbine, the performance of a wind turbine is dependent on tip speed ratio. What happens if you lower the tip speed ratio, if you increase the tip speed ratio, and understanding of this drives the design. Okay, and understanding of this is very important to drive the design because it affects so many parameters that are involved, which are critical to the power generation. Okay, so these non-dimensional numbers play a crucial role. Okay, and the blade geometry, if you look at any section, we said you have an airfoil. Okay, and this blade, by the way, designing a wind turbine blade is complex. It's a very complex task. And for your information, we don't design it here in India. Okay. In fact, one of my colleague and called Professor Subba Reddy and me, we have made it a plan to design at least a small wind turbine blades here in the country. Okay. So the wind turbine blade design, if you look, the blades are it's a design as well as a manufacturing challenge. Okay, so the design has the blade design has twist in it. Okay, so this is the blade which you look from here. Okay, so you look at the blade from this side, you will see the sections, the different sections of aerofoil sections are visible. You can see one of the aerofoil sections here. So all the aerofoil sections can be seen. So you can take any section, you have an aerofoil sitting there. And the aerodynamics plays a crucial role in the performance of a wind turbine and the design of the wind turbine blade.
So you
from near the roof.
Try to some presentation.
Yeah. Okay. Yeah. Actually, 1 second. I'm stopping the video because your voice is breaking. I'm stopping the video. I'll try to wind up. Can you hear me? Hello?
Yes, sir.
Oh, can you hear me? The voice was breaking. I don't know if your voice was breaking. I stopped the video.
That have 5 minutes. So try to sum up your presentation in 5 minutes.
Yeah, I'm going to finish. Sure. So this is the way in which the design of, the wind turbine design is evolving. From aerofoil, you have the blade. From blade, you make the wind turbine, and then as the wind farm level as a whole. In every step, the aerodynamics matters. Okay, in every step matters, so we need to understand it. And the design is driven. The design of a wind turbine is driven by multiple. It's a multidisciplinary field. It's a multidisciplinary optimization problem. Okay. So I will go a bit fast because I have to wind up. I'll just stop with the next slide. Okay, because the next one, few slides is going to finish. Okay. So how the blade performs in each section. The aerodynamics has to be carefully measured. In fact, this is what we do. We characterize the blade completely. Even as we speak, my student is working on it. Okay, so he is working on characterizing every blade, how the performance is evaluated. You simulate them in CFD. You make wind tunnel measurements and see which shape will best maximize power capture from wind turbines. Okay, so that's the challenge.
Hello.
And once we get the shape right, you will see that. I will just move on to the improvements that you can make. Okay, the improvements are at the tip as well as
Hello.
at the root. You have a lot of design improvements which you can
Hello.
make to enhance. That brings, this is my last slide. Yeah, I'll stop it here. I think already I'm running out of time. Yeah, I'll stop it here. Can you see me? Hello? Hello? I think there is a connectivity issue, right? Hello? Hello?
Yes,
Can you
sir.
hear me?
Yes, sir.
Yeah. So
Yeah.
I'm done. I just, there is a connectivity issue. So I'm not switching on the video. Actually, I am in office. Okay, I don't know where the problem is. There is some, the internet connection seems to be unstable. Okay.
Dr. Balaji, I want to have some information.
Yeah.
Power is cheaper than fossil fuels.
Yes. It's compared to fossil fuel, as I said, the cost of wind power generation is falling. Even in India, if you look, I think solar has fallen even more here. Okay, it has gone below, as I understand, the 5 rupees per kilowatt hour. That's what I remember last. I'm not I don't follow all the news, but this is what I remember. Okay, and for wind, I have presented the global scenario, not the local scenario here mostly. Okay, so the cost of wind globally is falling, and still here we are yet to reach the level and competence of solar. It will take a bit of time. Okay, because large wind turbines, whatever has been already commercialized in the West, is yet to come here. Okay, it's not yet here. Okay, the large, more advanced wind turbines are still not there. Did I answer your question?
And where is India in wind power in the world?
I showed that scenario. We are in the top 10. Okay. For example, just before Corona, we were installing wind turbines at a rate of about 5 to 6 gigawatts. Okay, every year. And the solar also in the same level, 5 to 6 gigawatts. Okay, so, and if you take that into account, we will be in the last, easily within top 10.
You say wind is generated by sun, so why is not solar energy?
No. Wind, see, that is what I said it in the talk, that solar has a limitation. You get it only from morning 9 to evening 4. Okay. So what about the early mornings and the evenings, late evenings or at night? Okay, that is when a lot of wind is available. You see, wind is complementary to solar. It is not competing with solar. Okay, so you can make a lot of power generation. Okay, especially when in the early mornings and late evenings, when we need it to support our load. Did it answer your question?
Okay, then Balaji, you that you have come for a very short call, and you have done a good job for us. Thank you.
Thank you.
Thank you, sir, for the wonderful presentation. We will be starting with first poster session, and for this I would like to introduce our chairpersons for the same. The chairpersons with us will be Dr. N.K. Acharya, MS University of Baroda, India, Dr. Vaibhav Kulshestra from Bhavnagar, Dr. Chandrasekhar Pati Tripathi, Department of Physics, Institute of Science, BHU, Varanasi, Dr. M.P. Sharma, Guru Ghasitdas University, Bilaspur, Dr. K.C. Bhanu, School of Chemical Engineering, University of Ulsan, South Korea, Dr. Dinesh Kumar, Dr. Sunita Mahavar, Dr. Narendra Jhakar, and Dr. Dalpat Meena from Department of Physics, University of Rajasthan. I welcome you all on the behalf of the team. All the participants will be divided into break room with one chairperson as co-host where they can give their presentations one by one. Co-host or chairperson will ask participants to present their work one by one. Candidates will get pop-up message on their devices to enter into break room, and you will have to click on Join tab to enter break room. It is requested to the participants to enable their mic and video, and they can share their screens and introduce themselves first, and then they can start with their presentations. Other participants who are not giving presentations at that time should disable their mic and video so that there should be no chaos and confusion. 1 hour time will be given during break rooms, and break room will end automatically after an hour. So try to keep your presentations short and to the point. Participants will be evaluated by assigned chairperson as well as other chairpersons at our end. Being said, I would like to explain it again. जो भी पोस्टर प्रेजेंट कर रहे हैं वो अभी ब्रेक रूम के अंदर पोस्टर प्रेजेंट कर सकते हैं। ब्रेक रूम्स में आपको एक को होस्ट प्रोवाइड किया जाएगा जो कि आपके चेयरपर्सन होंगे। आपके पास एक नोटिफिकेशन आएगा आपके डिवाइस पे जिसके अंदर आपको ज्वाइन टैब पे क्लिक करना होगा ताकि आप ब्रेक रूम को ज्वाइन कर सकें। और जब आप उसके अंदर चले जाएंगे तो जब आपका नंबर आएगा यानी जब आपको को-होस्ट बोलेगा तभी आप अपना माइक और वीडियो ऑन करें और अपनी स्क्रीन शेयर करें और अपना प्रेजेंटेशन दें। अगर और कोई कंफ्यूजन है तो आप चैट बॉक्स के अंदर भी अपना क्वेश्चन लिख सकते हैं। We'll try to resolve it. So we'll be entering into the break rooms and do make your presentation short because the break room will end in 1 hour. Thank you.
हेलो मैम।
Yes.
मेरा क्या है आई एम प्रेजेंटिंग टू डिफरेंट पोस्टर्स सो इज देयर एनी प्रॉब्लम फॉर दैट?
Your co-host or chairperson, if they allow you, then you can present your paper.
Ma'am, please allow me in a single room. That's why I can present one by one.
Sorry.
Hello, am I audible?
Yes, speak again.
Please, please allow me in a single room so that I will present my paper one after the another.
Yes, single room will be provided.
Okay, thank you, ma'am.
Excuse me, ma'am.
Yes.
Ma'am, we have submitted the posters. So our posters are displayed in that room, or we have to share again that poster?
You have to share the poster on your.
Okay, thank you, ma'am.
Yes, because we cannot include ourselves in the break room.
Okay, thank you, ma'am.
Yogendra Kumar Mishra will also be joining us as chairperson for poster presentation. He's from Max Clausen Institute, University of Southern Denmark, Sunderborg, Denmark.
Hello.
Yes. Once we'll notify you, then only you will get notification. We are making break rooms right now. Please be patient.
Naveen sir, good afternoon.
Very good afternoon, Sarman.
Sir.
Rules are created or still we are waiting?
I think we are waiting, sir.
Okay.
Dr. Sharma, good afternoon.
Good afternoon, Dr. Saab.
So, how are you?
Fine, sir, fine.
Okay, good. Seen you after a long time.
Yes, sir.
आएगा, अभी लिंक आएगा। हाँ हाँ
Make break rooms. We will inform here and then you will get pop-up. Please be patient.
Hello.
Yes.
Hello. Hello.
Break rooms have been created. You can join room now.
Hello.
Naresh.
Break room has already been closed.
Hello.
Yeah, break room has been closed.
My break room was number 8 and it got closed automatically.
Because of
Sir, my
issues.
my break room is also closed.
We are creating break rooms again. It will take hardly 2 to 3 minutes. So please be patient.
Okay, fine.
You can join the break rooms now. Everyone can join break rooms. You can click on join tab.
I could not find this joint.
बाहर से आवाज
You have to keep your pop-ups and notification on. Then only you will get notification for joining into break room.
Audience, I think you are seeing a pop-up message at your screen to join. Please, I request you to click the join button to enter in the break rooms. And one more thing, check in your PC or laptop whether the pop-up are blocked or not. If they are blocked, then you will not get the message to join.
Madam, it is not showing any pop-up. Hello. Hello. There is no pop-up room assigned. I am not able to get inside the breakout room, whether it is started. Hello, madam. Any host is available here?
चल जाएगा हाँ
Am I audible?
Yes, yes.
So actually, I am. Sir, my breakout room is over. So due to some connection problems. Hello.
Use various apparatus like cleanest open cup apparatus for analyzing fire points, tankies melted closed cup apparatus for flash point, and spectrometer for measuring refractive index. Yes, sir. We have so many types of apparatus which are
Please call next one.
Hello? No sound is coming here. Hello? Hello, everybody?
Now you all are out of your break rooms and back together. First of all, I want to thank you to all the participants.
Excuse me, madam.
Yes, say.
Ma'am, I have not presented yet.
You have not presented your poster?
Yes, madam.
Actually, we are going to have our oral presentation in the next. So we will schedule the poster over there.
Hello. Ma'am, I am out of my breakout room.
Hello.
I am presenting at the time.
Hello.
We go.
Hello.
Hello.
Ma'am, actually, I had presented half of my presentation, only the last part is remaining.
Can you hear me? Dear audience, you all are out of your breakout rooms.
Yes, ma'am.
Because the time is limited, the session was over, and then you are out of your rooms. So it's a request to all of you that who are still remaining to present your poster, we will reschedule your poster presentation in our next oral presentation session. Is it all?
Ma'am, I have already presented my poster approx 9.
It's fine. Okay. If still other people have any query, please tell us in the chat box only. Now I want to thank you all the chairpersons who gave their precious time to host the poster presentation session. And there is a request to all the co-host or chairpersons that whoever will be the winner or whoever had the better presentation, please personally to the Dr. Chagan Lal sir. I again announce that co-host or chairpersons can share the scores of individuals directly to convener Dr. Chagan Lal sir personally. Okay, so after poster presentation session that is over now, we are moving ahead with our next oral presentation session third. That would be chaired by Dr. Brahmanand Chakravarti, Scientist G, High Pressure and Synchrotron Radiation Physics Division, Bhabha Atomic Research Center, Mumbai, India, and Professor Ghanshyam Sharma, Department of Physics, University of Kota, India. I welcome both of you, sir.
Thank you very much for the introductions, and welcome all for the session. Now the first presentation is by Abhishek Kumar. So Abhishek, please share your screen and start your presentation.
Yes, sir. I am here. So can I present my presentation here?
Yeah, you have to finish by, I think, 5 minutes.
Yes. It's a request to all of you that you have to sum up your presentation in just 5 minutes. You have a confined time limit. So keep in mind.
My screen is visible or not?
Yes, your slides are visible and you are audible too. You can continue.
Okay. Wait a minute. Okay, I'm just presenting now. My name is Abhishek Kumar. I'm a research scholar in the Hydrogen Energy Center, Department of Physics, Banaras Hindu University. And my presenting topic is hydrogen storage in lab space-based high entropy alloys. The outline of my presentation is a concept of high entropy alloys, concept of entropy alloys, and then I will be recent development concept of lab space, then I will be motivational behind the work, then I will propose the synthesis method which I use, then I conclude my work. If we talk about the concept of high entropy alloy, we can easily say that the high entropy alloy defined by the two ways, with compositional based definition and entropy based definition. The compositional based definition, if any systems have more than five elements, then it will be called the high entropy alloys. If any system has the entropy greater than 1.5 watt, that will be called as high entropy alloys. The right hand side is representing an alloy word. In alloy word, we can easily see that the traditional alloys and medium entropy alloys and high entropy alloys. The medium entropy alloys have the entropy of mixing is greater than R and less than 1.5 R. Now I'm going to synthesis diagram, which is involving to introduce how to we design the high entropy alloys. We can design by the compositional design, by phase oriented, hydrogen property orientation. If we take about phase oriented, we know the hydrogen storage is better in BCC phase and also in a lab spaces. So we can select the lab spaces and BCC phases. And if we talk about the property oriented hydrogen storage material, we can select the hydride forming element and non-hydride forming element. And the most probable synthesis method is use arc melting, ball milling, and SPT technologies. The first investigation on the system is done by Kao et al. In 2010. And they reported 1.80 weight per ton hydrogen storage. And this system is done by arc melting, and this system reported C14 lab space. Here is the periodic table where the left hand side is representing the hydride forming element, right hand side representing the non-hydride forming element. We can select that element which are hydride forming and non-hydride forming for the systems. This is if we go through the recent literature survey, we can get that the arc melting and HE high energy ball milling method is most probably used for designing for high entropy alloys. And if we select the element base, then we can easily see that titanium, vanadium, zirconium are most probably used in e-synthesis method in recent years, about 17 years. If we can see that the number of articles published in year 2010 to 2021, most of the articles published in 2020, and the maximum reported hydrogen storage is 3.71 weight per ton. Here is the table. When we get the literature survey, I get the maximum reported 2.70 weight per ton till August. Then after reported 3.7 weight per ton. This is the sum reported ICRE in the recent year 2021, and this is a breakthrough the research, and the maximum reported is 3.51 weight per ton, and the system is BCC, and the system designed by the arc melting. I'm going to work on lab spaces, so I will be little bit introduce the relative lab spaces. Three type of lab spaces: the hexagonal, cubic, and hexagonal lab spaces. How will we select the element? Then the limit is that if any system is atomic size mismatch is greater than 5%, that will be called that will be formed lab spaces. If any system have L and electronegativity greater than 7%, the system will be high entropy alloy for lab space formation. Now I am presenting my work. I just select the 5 element and take the hydraulic press for making the pellet, and this pellet will be made in argon atmosphere in the RF furnace, and the pellet which I get and use for further characterization. First characterization, I used XRD. In XRD, I get Renewable refinement by the help of JANA 2006, and the goodness of rating of the system is 1.05%. And the all peaks will match with the hexagonal C14 lab spaces. So I will be concluded the XRD reveals that the system is C14 lab space formation for high entropy alloy. This is the new system not reported till yet. I just also use an SEM micrograph, and A is the representing that the ladder type arrangement of the system, and no cracking and no double faces form in the system. And from B to H, we can easily say that the all element mixed with together, which homogeneously mixed with together. And I also perform the PCI test for my system. I take the 0.5 gram of my sample and take a soak and release. For soak, I get that here's the A diagram representing at the S2. S2 absorb this system 0.53 weight per ton S2 absorbed within a 50 second, not 50 second, whereas the maximum storage capacity is about 0.72 weight per ton. And the B figure representing here the release of dehydrogenation of hydrogenation of my HEA, and the system is performing under 410 degrees centigrade under the 16 atm hydrogen pressure. And the B system representing here that the release 0.28% of hydrogen within 1 minute under 1 atm pressure at the 410 degrees centigrade. I also performed the PCI of the instrument. PCI means pressure composition isotherm for calculating the enthalpy of mixing of my system. When I perform the PCI and plotted a Van Hoff plot and get that my system have entropy of absorption is about 19.06 and kilojoule per mole, and the absorption entropy is about 34.108%. Now I'm concluding my work. We have successfully synthesized the HEA, titanium, vanadium, zirconium, cobalt, nickel, Mn. In this systems, I have selected the 3 hydride forming element and 3 are non-hydride forming element, because the hydride forming element support for hydrogen absorption and non-hydride forming element for support hydrogen absorption. And all the criteria related to hydride forming for C14 Lewis basis criteria, they are also possessed for this system. And on the basis of kinetic study, this show the hydrogen absorption within a 50 second, it absorbed 0.538% hydrogen absorbed. And the kinetics is a better reported kinetics ever reported study in my systems. But in this system, not getting a good hydrogen storage. I also calculated the experimental entropy of the system by the help of PCI, and then I plotted a Van Hoff I previously slide presenting there. And now, thank you for everything for listening. Now I'm answer to all of your questions.
Thank you, Abhishek, for giving a nice presentation and finishing in time. So since you have a alloy system, how is the stability of your system?
Yes, sir.
Since it is a alloy system, so
yes,
there are a lot of heavy metal. So how about the stability of the system?
So this is a high entropy alloy, and high entropy alloy is randomly oriented by the atomic position, and they are more stable in the performing of hydrogenation and dehydrogenation. So we can say that the HEA system is more stable than other intermetallics.
Okay, so and what is your desorption temperature?
Sir, my desorption temperature is about 410 degrees centigrade under the 1 atm pressure.
400 degree centigrade, 410.
Yes, sir.
Okay, so desorption temperature is quite high.
Yes, sir.
Okay. So any questions from audience? Okay, if there is no questions, we thank again Abhishek.
Thank you, sir.
Thank you. And we'll move to the next presentation. So you stop sharing your screen. So the next presenter is T. Senthil Shiva Subramaniam. So you please share your screen and start. Your slides is not visible, Senthil. Senthil, your slides not visible. Senthil, your slides not visible.
1 second.
Yeah, it has come now.
Is it fine?
Yeah, it is fine now.
Yeah. Thank you. Okay, thank you so much for the wonderful opportunity. My topic is on highly sensitive nanoplasmonic hydrogen gas sensor based on palladium gold nanoshell.
Senthil, you start your presentation. You are not audible.
Dear presenter, your voice is not audible to us. Please fix the issue. Sir, we can call the next presenter.
Okay. So, Senthil will take your presentation at the end. Meantime, you try to sort out your issues. Now, next presenter is Juhi Devangan. So, Juhi, you please share your screen and start your presentation. Juhi, please share your screen. Yes, your screen is visible. You start. Juhi, you are not audible.
Juhi Devangan, please turn on your mic. Juhi Devangan, I think your device is not supported with audio.
Ma'am, am I audible? Audible? Am I audible? Hello?
You are audible. You may proceed
Yes, yes.
now.
Yeah. And my screen is visible. Hello?
Yeah, it is visible.
Okay. So, yeah. So, as we all know, the energy demand is increasing day by day because of urbanization and industrialization, and we need the energy like renewable energy, which should be clean energy. And in this context, hydrogen may be considered as a green energy sources, which can reduce our dependence on the fossil fuels. And but the main challenges for the in hydrogen energy is the storage of the hydrogen. So hydrogen may be stored in the form of solid state, liquid state, and gaseous state. But if we store hydrogen in gaseous form and liquid form, it requires high energy consumption and high cost, and it is not safe. It is not safe also. So solid state and hydrogen storage may be considered as may be considered a good hydrogen storage medium, which overcome this challenge. And for the hydrogen storage medium, for potential hydrogen storage medium, Department of Energy USA has set some requirements, some criteria, and the two criteria are gravimetric density of hydrogen storage medium should be higher than 6.58%, and and the binding energy of hydrogen for the system should be between -0.2 to -0.7 electron volt. And for the hydrogen storage system, carbon nanostructures are studied that it may be a suitable hydrogen storage medium. And these are the methods which I have used. These are the computational methods which I have used to perform the calculation. And for the hydrogen storage, I have used the SciGraphen system. And metal decorated carbon nanostructures are considered as a good hydrogen storage medium. That's why we have decorated sign graphene system with a lithium metal atom. Sign graphene is we have considered here 2x2x1 supercell of sign graphene for the calculation, and it contains 48 carbon atoms. And here the four unequal it contains four unequal bonds, and all the calculated bond lengths are very good match with the literature value, and it contains five heptagon, hexagon, and pentagon carbon rings. And for the decoration of lithium atom, we place lithium atom just 2 angstrom, about 2 angstrom above the sign graphene, and calculate and optimize the structure. And the calculated binding energy is about minus 2.63 electron volt. And to understand the binding mechanism, orbital interaction, and charge transfer mechanism, we have plotted the partial density of state between the lithium atom and sign graphene system. We have plotted the partial density of state for carbon 2p orbital. This is left one partial density of state plot, and for the Li2s orbital. Here we can see that when the system absorbs lithium atom, the partial density of state of carbon 2p orbital, there is some enhancement of state near the Fermi level. So we can which indicate that there is some increase in charge, that is that carbon 2p orbital gains some charge when lithium atom is absorbed. Or when we plot for partial density of state for lithium 2s orbital, here we can see that there is the intensity of states near the Fermi level decrease. So we can say that there is some charge loss from the lithium atom. Or from the we have also performed better charge analysis, and we found that 0.80 electron is charge has transferred from the lithium 2s orbital to carbon 2p orbital. And to visualize this charge transfer, we have plotted the charge density difference plot between the Li decorated sign graphene system and sign graphene system. And here we can see that the electron loss near the lithium atom and electron gain near the carbon atom. So when lithium so this is the so this charge transfer is very important for the binding of lithium atom on sign graphene system. Now to study the adsorption of hydrogen in the system, we have place the hydrogen molecules one by one near the lithium atom, and allowed the system to optimize, and we got the these adsorption energies, and we can see that all the adsorption energies are in the range of minus 0.2 to minus 0.7 electron. That is all in the range of the criteria that guided by Department of Energy, USA. So we may say that the system is a good hydrogen storage medium. And again, we have plotted partial density of state to understand the binding mechanism between hydrogen molecule and the system. And here the binding mechanism we can also we can see that the enhancement of state near the Fermi level when hydrogen is adsorbed. So we can say that lithium atom donates some charge to the hydrogen atom. And to check the stability of the system and practical feasibility of the system, we have performed the diffusion energy barrier. And diffusion energy, we got the diffusion energy barrier about 0.78 electron volt, which is suitable. And diffusion energy barrier is suitable for the system. And the gravimetric weight percentage 59.15 weight percentage, which is much higher than the correct criteria set by Department of Energy, which was 6.5 weight percentage. And desorption temperature, we have calculated desorption temperature by using Bond-Hoff equation, and we got the desorption temperature 384 Kelvin for the average binding energy of hydrogen minus 0.30 electron volt per hydrogen molecule. And to confirm the stability of the system at higher temperature, we perform the ab initio molecular dynamic simulation for the sign graphene plus Li system and sign graphene plus 2Li system. And after the molecular dynamic simulation, we got the negligible changes in carbon-carbon bond and carbon-lithium bond. So we can say that the system is suitable for hydrogen storage. And all the results we got from the DFT simulation satisfy the DOE criteria and are stable. And also we have performed the diffusion energy and molecular dynamic system to confirm the metal-metal cluster formation, and the system, and we got the the system is suitable and prevent the system from metal-metal clustering. And this was all about my work.
Thank you, Juhi, for a nice presentation. So any questions from the audience?
Juhi, how many plane waves you have considered in your computations?
Sir, are you asking for exchange correlation function?
Basically, plane waves. I am talking about plane waves.
Plane waves, sir. So sorry, sir, I'm not getting your question.
So you know the how much plane wave cutoff energy you have taken?
Yes, sir, 500. Yes, it was 500 electron volt. I have presented here. It was 500 electron volt.
Okay. Any other question? Okay, so if there is no question, then we thank the speaker again, and we'll move to the next presenter. So next presenter is Sattuki Chandra. So Sattuki, you please share your slides.
Sir, can you hear me? Check that first. Hello? Hello, sir, can you hear me?
Yeah.
Yeah. I'm audible, right? Yeah.
So you share your screen.
Yeah. You can see the screen, right?
Yeah, your slides are visible. You start.
Okay. Okay, so welcome. I am Satyaki Chandra, a student, PhD student in the Energy Science Department of IIT Bombay, and this presentation is about our experimental study on a hydrogen reactor containing 5 kg of LaNi5 and featuring a novel conical fin system for cooling, and a numerical scale up after that of the same system using modular approach. So this is the basic reactor design. This is the outer cylinder of the reactor, and this is the conical fins I talked about. And there are these 3 thermocouples to detect the temperature. They are equally distant. I mean, longitudinally they are equally distant from each other, and the tip of the fin is radially halfway through. And there are also a central metal filter inside the reactor centrally. That's how it can disperse the hydrogen properly throughout the bed of this reactor. Now, why use conical fins? Because they perform better than flat circular fins. If a same number of flat circular fin and conical fins are compared, then it can be seen there is 14% improvement in performance. That is the absorption time from hydrogen in LaNi5. It's reduced by 14%, and because they are a little bit higher in volume, they are taking up more space inside the reactor, but it is a 2% decrease in LaNi5 capacity. So a justifiable trade-off. Now this better performance is provided by the higher contact surface area provided by these conical fins, and also they do not restrict the flow anyhow. And when I poured the metal hydride, because of this funnel-like shape of the fin, the metal hydride went inside proper easily. Many people have reported, and I talked to many people, they said they have to shake their reactor or vibrate that to push the metal hydride powder in, but I didn't need to do that. With that said, this is the circuit, that is the gas and everything, and this is the green line presenting absorption from the hydrogen cylinder to the metal hydride reactor for testing purpose. And this is how we safely throw the hydrogen release the hydrogen to the atmosphere. Now you can see there is this Coriolis mass flow meter attached in the circuit. This detects how much gas is flowing in or out of the reactor during absorption or desorption. Now these before presenting the results, these are the error chart for the flow rate versus flow rate of the Coriolis mass flow meter. As you can see, as the flow rate reduces, the error is increased. So at the very end stages of any absorption or desorption reaction, this particular or any Coriolis type flow meter cannot predict, cannot accurately detect how much flow is there. So a mass flow cutoff of 1.5 grams per minute is taken. The manufacturer Emerson, they suggested to take a positive mass flow cutoff. 1.5 grams per minute was chosen because below this cutoff, even if all the valves are closed, there was always some detection of some false reading. So 1.5 grams per minute was the way to go. And in this plot, you can see this region is errorful, the end region, and also when integrated the flow rate to get the absorbed hydrogen, you can see I am showing up to 63 grams. The total, maximum capacity of LNI5 is 1.4 gram weight percentage. It is 70 grams. I am showing up to 90% reaction completion because I cannot detect the end part. And initially, all the plots are for first 2 minutes they are overlapping each other. This is because the supply pressure is equal and the reactor is at ambient temperature, that is 30 degrees Celsius in our region. And the reaction is dependent on supply pressure by the equilibrium pressure. This equilibrium pressure is dependent on the temperature. So the initial part is same, but after that, 7, 5, and 2.5 LPM, that is the green, black, and red lines representing those flow rates of water through the 4 tubes. More water, better cooling, and so faster reaction, and the reaction is ending faster. Now the initial part is dependent on pressure. What if I change the pressure at the initial stage? 25, 20, 15, and 10 bars are shown in these plots. Initially, high reaction rate can be seen from this curve, and high heat generation is also there. But after some time, you can see the reversal of these plots. That is the purplish top and red is the bottom, the 25 and 10 bars. They are in reverse because the area under this curve, that is the hydrogen flow rate versus time curve, it is fixed because the system can only absorb a fixed amount of hydrogen. So initially there is more heat generation, more reaction. After like 10 minutes or so, the reaction stops. So removal of residual heat is happening for the high pressure cases, whereas the low pressure cases, the removal and generation of heat is happening simultaneously. So this kind of reverse trend is observed. And in this case, if in an area where the ambient temperature is lower than 30 degrees Celsius, they can use lower temperature water and they will be of course benefited from that feature of that region. So colder is better. It can be seen from here. Now the desorption part. Now you can see this red dotted line and the red farm line. There are 2 sets of dotted and 2 sets of farm line. Red is representing 60 degrees Celsius hot water for desorption and black for 50. The dotted one is preheated reactor. That's the reactor is preheated to that 60 degrees Celsius for half an hour and before the experiment started. Initially, the residual energy is residual heat, that higher temperature that is driving the reaction. The reaction rate is also higher here than the cases with ambient temperature. The reaction rate is very low at the beginning stages. And after some time, both of them are flattening for a certain amount of, certain temperature of inlet water. This is because in this flat region of temperature, all the heat supplied by the hot water is being used for the endothermic desorption process. So this flat region is noticed. And also, if you preheat the system for 60 degree case, it is only 1.5 minute faster than the non-preheated case, and for 50 degree it is only half a minute faster. So if you want to release the hydrogen to atmosphere, then preheating not a good idea. Not a fruitful idea. Now this is again a case with 7.5 and 2.5 LPM from 30 degrees Celsius, and the hot water is at 60 degrees Celsius. Higher flow rate, better heating, higher endothermic desorption, and you can see that from this plot also. Now on the computational part, this is the computational domain. These are the several assumptions. These are the various equations in a mass, momentum, and energy equation. Various parameters. Grid independency test. You can see the fine grid. They are almost producing fine grid. It is almost producing the same result as finer grid, but the time requirement is much less. So fine can be said as grid independence, and also computational less burden to the system. Now with this model, I validated this system. Now red dotted lines, these are the experimental one, and black, they are agreeing with each other. These for different flow rates, these two for different pressure, these two for different inlet temperature of water. Now there is a bit mismatch because the red dotted line, the experimental one, it is the integration of the flow rate as a downstream point than the reactor in the circuit, and the black one is a volumetric integration inside the reactor by simulation. So there is this bit mismatch. And also the same is true for this. The red one, that is experimental, is average of 3 points, strategically located of course, but the black one is a volumetric average. The arithmetic and volumetric average, they are a bit different, but the trend and they are very close to each other. So this model can be used for predicting properly. And the modular approach for scaling up, if you add now 5 series and 5 parallels. Series mean only the water line is connected
you
in
have
series.
to finish now. Time is up.
This is the last slide, sir.
Yeah. Okay, then it's fine.
This one is the last one. Yeah. So series is the water line is connected in series. As the water flow through the reactors, more than one, it gets hotter. So the process being, slower than the base case. That's one reactor. And parallel is had to divide in 5 or 10 lines. So less water, lower heating. So this kind of poorer result is one. But the amount of metal hydrate is 5 and 10 times. So this is expected. Now what I saw, find out that if you increase the water flow rate by twice, then even if the metal hydride or the heating load is 5 times, it is performing same. And that is true for 3 times water and 10 cases. So 25 kg and 50 kg cases, they are performing as good as the 5 kg lower capacity cases only by increasing the water in twice and 3 times. Water flow rate by increasing them twice, 2 and 3 times. So that's what I want to conclude, and I want to acknowledge Imprint for funding. Thank you.
Thank you, Satyaki, for a nice presentation. Now, is there any question from the audience? Any question from anyone? Okay, if we don't have any questions, we again thank the speaker and we'll move to the next presenter. So next presenter is Dinesh Das Babu. So Dinesh, you please share your slide.
Yes, sir. Is my screen visible, sir?
Yeah, visible.
Okay. Good afternoon to one and all present here. I am Dinesh Das Babu, a PhD scholar in Mechanical Engineering Department of IIT Tirupati. I am going to talk about the effect of aluminum substitution for nickel in LANFI on the performance of a metal hydride based compressor. So as hydrogen is a fuel source of future, metal hydride compressor act as an intermediary between the hydrogen production and end use. Metal hydride compressor uses the pressure difference generated between the absorption and desorption at 2 different temperatures to compress hydrogens. So researchers have used many different kinds of hydrides, AB kind, AB5 kind, AB2, A2B kind. Out of those, AB5 has some distinct advantages. One of those advantages is high tunability. So LNFI being an AB5 kind of material, the lanthanum in it can be substituted with mixed metal, cerium, calcium, etc. Whereas the nickel can be substituted with copper, iron, manganese, aluminum, etc. So in this work, the effect of aluminum substitution in LNFI is evaluated by estimating its performance parameters and its effect on the compression. So for measuring the PCIs, we have used a Sievert's kind of instruments which and measured the PCIs for at 20 to 140 degrees centigrade. And for the analysis, 1 kg of hydride is used, and the specific heat capacity is taken as 419 joule per kg Kelvin, and the hydrogen properties and specific heat ratio is shown. These are the PCIs of the 3 materials. The first one is LNA5, and the second, the middle graph is with aluminum 0.2, and the third one on the right is aluminum 0.4. Here we can see that the weight percentage, the maximum weight percentage is at 20 degrees centigrade is 1.47, 1.42, and 1.38 weight percent respectively. And the equilibrium pressure of these three hydrates are around 1.5 bar at 20 degrees centigrade. So comparing the PCS of three materials and 100 degrees centigrade, it is observed that the plateau pressure is decreased, the slope of the plateau increased, and the absorption capacity decreased with the increase in the aluminum content. This is the graph for Van 't Hoff plot. The Van 't Hoff plots are calculated by considering the equilibrium pressure at the midpoint of the plateau, which is at 0.6 weight percentage. The enthalpy of formation is tabulated, and notice that the absolute value of enthalpy increases with the increase in aluminum content, which increase the heat requirement or heat requirement while desorption and release by absorption during absorption. This compares the throughput per cycle with absorption temperature for all the three materials. At low temperature, the increase in the throughput with the increase in supply pressure is very less because there is no much increase in the absorbed weight percent after the material gets saturated. But at high absorption temperature, the variation is significant. Here, another important thing to note is the decrease in the throughput due to the higher absorption temperature is less for the material with higher absorption, higher aluminum content. This figure shows the dependence of isentropic work done at different work done at lower absorption temperature increases linearly as work done is directly proportional to the desorption temperature. But at higher absorption temperature, LNFI shows low work done because of the incomplete absorption. Higher aluminum content has higher higher minimum temperature of desorption. For example, here we can see the figure on the right. LaNi 4.6 aluminum 0.4 fails to work below 80 degrees centigrade, for LaNi5 works even at the temperature. This graph shows the effect on the theoretical heat supplied. At low absorption temperature, LaNi5 shows the least heat requirement, but at higher absorption temperature, the low heat requirement is shadowed by the fact that the decrease in the low heat requirement is caused due to the low throughput of the material. So the compressor, even though it is taking less heat, it is giving low throughput, so it is not beneficial. The next is the graph of pressure ratio obtained for the three materials. Here, LaNFI without the aluminum substitution shows the highest pressure ratio achieved out of all the three materials. And the figure on the right, we can see that at 80 degrees centigrade, the graphs are converging to 1, which means that it is not giving any pressure output at all. So in 80 degrees centigrade, we can see that the material with aluminum substitution doesn't work, whereas aluminum somewhat works. Basic LNFI somewhat works. This is again the comparison of efficiency with absorption temperature. Here we can say that the graph in the middle, which is for aluminum 0.2, works as a stable, gives a stable performance throughout the absorption temperature range from 20 to 40 degrees centigrade, where LNFI drops its performance at higher temperature, and the material with aluminum 0.4% gives like throughout low efficiency. This graph shows the variation in efficiency of the compressor with supply pressure. Low supply pressure gives better efficiency for the compressor at low absorption temperature. The graphs in the from the graph in the right, we can see that lower pressure ratio can give higher efficiency, but the increase can be offset by the low throughput. Coming to the conclusions, due to the aluminum substitution, there is a decrease of weight percentage from 1.47 for LNA5 to 1.47 weight percent for LNF5 to 1.3 weight percentage for aluminum 0.4, while decreasing the equilibrium pressure from 1.5 bar, which is for LNF5, to 0.83 bar for LNI 4.6 aluminum 0.4 at 20 degrees C. The heat of formation increased with aluminum substitution. There was a decrease in the throughput due to increase in absorption temperature at is lower for the material with higher aluminum content. This analysis also showed that the bounds of the operating temperature for all the three materials. In our studied operating temperature and pressure range, the maximum efficiency was found to be 0.24 for LNF at 3 bar supply pressure, 30 degrees centigrade absorption temperature and 140 degrees centigrade desorption temperature with a pressure ratio of 8.97. These are the references. Thank you. Any questions?
Yeah, thank you for a nice presentation. So any question from the audience? Audience, any question?
Hey, can I ask a question?
Yeah, sure.
Thank you. Well, can you comment a little bit on the PCI? Because it seems that depending on X value, you do not have the same slope of the plateau. So in some case, you have a very flat plateau. In some case, you do not have a flat plateau. So increasing the X value seems to increase the slope of your plateau. Can you comment on that? And my second question will be about efficiency. Because is it better to have the same efficiency all the time or to have an efficiency depending on the temperature?
Sorry, sir, I could not understand your first question. Can you please repeat?
The first question is about the slope of the plateau, because depending on X value, for X equals 0, you have a plateau which is almost flat. And if you increase the value of X, then you have a plateau which is not flat at all.
Yes, sir. The ideal case when we construct a gun, we desire a flat plateau, but when we substitute with aluminum, the slope increases. So for the analysis, for this analysis, hello.
Yeah, you can continue.
Yeah. For our analysis, we are considering the equilibrium pressures of the middle of the plateau. For in case if the plateau is having a slope, it will give some error in our calculations. Means like to the lower end, the portion which is like on the left side of the midpoint, those hydrogen may not come out. So that is the effect of the slope of the plateau.
Okay, and about the efficiency, is it better to have always a efficiency or to have an efficiency varying about as a function of temperature?
Having it is always desirable to have a near about efficiency for a compressor, but in case we know that the temperature of the bed is not constant, we give some like cooling fluid outside the
No, sir, ऐसे तो सही आपको सही है सही था लेकिन एक तरफ
hello, may I continue?
यानी अब वहाँ पे ये हो जाएगा
Yes, you can. I think that somebody do not put the microphone off.
Yeah, you have another question on that efficiency, so you can explain that.
Yeah. We always expect a constant efficiency for our compressor, but we know that in the running time of the compressor, we give a cooling fluid, but the heat transfer is not proper. Though there is a thermal gradient which is existing inside the bed. So as a result, there may be some places inside the reactor like which will have some higher temperature than the expected value. So as a result, if the efficiency drops significantly, we don't want that. So we want a stable efficiency. So we should select a material like I said in this. Let me go to that slide. Yeah, in this slide, we can see that if the absorption temperature, the LNFI is 0.2, the second graph in the middle, it shows a relatively stable efficiency throughout our absorption temperature range, which is desirable. We don't want the material like in the top LNFI, when it comes to 40 degrees C, it drops drastically. So I hope I answered your question, sir.
Okay, yeah, perfectly. Thank you so much.
Okay, Dinesh, thank you.
जीरो ही मान के चलते कोई उपाय नहीं था कि क्वेश्चन डाला गया था now check कर देंगे.
Okay, Dinesh, thank you. Now we'll move to the next presenter. So the next presenter is Harsh B. Patel.
डालेंगे तो 24 का 6 चौका 24 होता है 4 का रूट 2 आएगा.
Yes, sir. Am I audible, sir?
Within 5. Yeah, you are audible.
या फिर यहाँ भी गलती हुई है जबकि हम यहाँ लिख चुके हैं फॉर इक्वल रूट डी बराबर 0 यहाँ 0 होना चाहिए 0 यहाँ रखोगे तब ना ये इधर आएगा.
Thairud wala, please off your mic.
नंबर ये वाला
Yes.
हेलो दोबारा जब तो वहाँ लिखे फॉर इक्वल डी बराबर
My screen are visible.
इसको
My screen is visible.
टेस्ट बहुत मस्त चीज होता है क्लास
Screen is visible.
क्योंकि
You start.
तो अभी हम लोग किए हैं लेकिन टेस्ट होना चाहिए एक बार नहीं कई बार होगा बात समझ रहे क्वाड्रेटिक इक्वेशन देते हैं तो फिर हम आपको एपी देंगे उसके बाद एपी है ना एपी का देंगे
Yes, myself Harsh Patel, and I am a research scholar from the Applied Physics Department from the Maharaja Sajirao University under the guidance of Dr. N.K. Acharya. And today my presentation topic is the transfer property of polymer blends and composition membrane for the selective permeation of hydrogen. So these are the outline of my work: introduction, membrane synthesis, hydrogen separation process, experimental setup, and the different characterization of the membrane synthesis, and result and conclusion. So we know that when we do the polymer with the composite, so these are the three example for the polymer with the synthesis of the composite material. So by using the solution casting method, I just made my material of my membrane material by using the solution casting method. So these are the synthesis process. And this is my material of polystyrene and PMM with RGO, graphene oxide, with sonication and without the sonication. And this is the system. By using this system, I just found the pure hydrogen. So the system is the concentration variable volume operators, and these are my membrane cell. And by using this equation, I just found the permeability of the hydrogen. And these are the result. In the blend of the pure PS and pure PM, I just got this kind of the permeability, which is really very good. And by using the RGO, when I used the RGO of 1% I got very much increase, almost a double in the permeation of the hydrogen. And as we increase the rate of the RGO with the pure polymers, we got the increment in the permeability. So this graph is very interesting. I just used different gases by the same membrane material, like hydrogen, oxygen, carbon dioxide, nitrogen, methane, and argon. So in all these different gases, I just observed that the hydrogen gas permeability is very higher other than the other gases. And as we increase the rate of the RGO with the pure polymer like PS and PMM, we just got the increment in the permeability of the hydrogen. These are the graph of the permeability versus the kinetic diameter of the different gases with the different material of the pure polymers and the composition of with polymers. And these are the selectivity versus the different ratio of the gases. Particularly for the hydrogen of with carbon dioxide, we just observed that the selectivity is almost the same for all the materials. And here is the Robinson plot. So Robinson plot of hydrogen versus hydrogen with respect to nitrogen versus the hydrogen permeability. And here is the material, the placement of the material when the where the upper bound of the 1991 and between the 2008. So I just observe the Robinson plot with the different ratio of hydrogen, like H2 with N2, H2 with methane, with oxygen also. And here I just observe the with oxygen, it is give the better result with oxygen selectivity, with carbon dioxide also, and with oxygen of with respect to the nitrogen, and carbon dioxide with respect to CH4. These are the same result of my membrane of PS with RGO of 1%. And here we can easily observe that the dispersion of the hydrogen with polystyrene. And these are the EDX energy result of the polystyrene with the RGO. These are the same result of the PMM with RGO with 1% RGO, 8%. Here also we can observe the dispersion of the RGO, and here the EDS result of the RGO. So the conclusion of my work is the work is aim is the hybridization of the PS and PMM membrane to better the transport mechanism of the hydrogen molecules. So as we increase the RGO nanoparticle, it is the play the vital role to transfer the H2 molecules. Here, when we add the RGO in the pure PS and pure PMM, then we got the increment in the permeability.
Thank you, Harsh.
So the composite of the PS and RGO shows the highest permeability with respect to the PMM, PMM and RGO. So these are the references that I have to use.
Okay, thank you, Harsh. So is there any question from the audience?
Very good afternoon, sir. Hello.
Hello.
Yeah, any question from the audience? Okay, if there is no question, then we thank Harsh and we move to the next presenter. So next presenter is Mukesh Singh. So Mukesh, you share your slides. Mukesh, you share your slides. Mukesh, share your slides.
Hello, am I audible, sir?
Yeah, start.
Okay, thank you, sir. So my name is Mukesh Singh. I am going to present the high capacity hydrogen storage in zirconium functionalized gamma graphene. Gamma graphene because it is most stable in the all three graphene, alpha, beta, gamma. By the way, why do we need energy? Okay, why do we need hydrogen energy? Because we are up to now we are using the fossil fuel energy, and we know that that is very fast depleting. So we need some other alternative, and we have the many alternative, but hydrogen is perfect because of these reasons. So because it has the high energy density and it's abundant in inverse, as well as it if we will use it, the byproduct of this is harmful or harmless. So there is no carbon dioxide and carbon monoxide. Now, but there are two kinds of challenges. So one is the production as well as the storage. But here we will be dealing with only the storage part. So if we have the hydrogen, we can store it in 2 or 3 ways. Since it is the gas, we can just put in a cylinder. So, but we can also put some kind of pressure. So it will be some compressed gas, but it will be not efficient. Then we can so we need a large tank for that, and then we can also liquefy it, but it will require a low temperature, which will cost more money. And then we can go to next one is the solid state storage, which is most desirable. Now why carbon? So why carbon nanomaterial? So in general, so carbon, we are choosing the carbon nanomaterial because of the some reason. For example, lightweight and porosity, and it is the high surface material. In general, all the carbon nanomaterial interact very low and bind very weakly with the hydrogen. So it is not a very good idea to store. It will not store more hydrogen if we will use bare carbon nanomaterial. So we do some kind of decoration. So we do some kind of decoration, and so there is one transition metal and one sheet. So for my system, I have chosen the gamma graphene as a sheet and zirconium atom as a transition metal. So this is my computational step, or you can say content of the slide. So what I will do, I will just I will present this thing in every slide. So here we have created a structure and optimize it and match with the previous literature. So these are the matching perfectly, and you can see the there is a few state at the Fermi level, and there is a band gap 0.46, which tells that it is kind of semiconductor, and bond length is matching. So our initial step are good. Now we can go. Now what I have done. So I have chosen some site, for example, hexagonal and trigonal site, and dope the zirconium and try to find what is the binding with the zirconium to the seed. So we have found the binding energy more than -3.8 for in both cases. More than in one is -0.3 and one is the -5.6. So now, so what is the effect of zirconium when we are doping on the gamma graphene? So you can see from the upper level, there is a less number of state. Even you can say there is no state. That's why there is a gamma graphene is semiconductor. And when we dope the zirconium, it becomes conductor. It becomes actually metallic. Now, so what is going on? How this is becoming metallic? That can be explained here. In the first panel, which is in the top panel, A and B, if you compare the DAS, so you will find that if you will compare A and B, you will find that at the Fermi level in A figure, there is more state than B, which is B is the pure graphene, B is the pure graphene, and A is the graphene plus ZR. It means that it has gained some charges. Carbon has gained some charges. Similarly, in the figure C and D, we can see that C and D. So C has lose some charges. It means that zirconium is losing. From the bottom figure, we are seeing that zirconium is losing some charges, and from top plot A and B, we are seeing that the carbon is gaining some charges. Okay, so we can also visualize this by using the charge plot. So here I have plotted the chart, and red region is telling the charge depleted region, electron depletion region. It means that if you will see the both first figure is the top view and other is the side view. So if you will see around the zirconium atom, there is a red region. It means that from that region the charge has lost and gained up to the carbon, which is the nearest only 6 carbon. So those carbon are gaining. So this is pictorial diagram for the previous slide. And now, after getting the strongly bonded zirconium with the graphene layer, we started putting the hydrogen atom. So we have put the 1, 3, 5, 7, 9. But there is a criteria called DOE criteria. So we will find the binding energy after putting every time one hydrogen molecules and check whether that binding energy is coming in the range of the DOE criteria or not. If it is not, we will say that okay, it cannot go up to we cannot go more than that. So from graphene, I have observed that up to 7 molecules it can absorb. Now, so this is the binding energy table for the same. So when I was putting 1 hydrogen, 3 hydrogen, 5 hydrogen, 7 hydrogen, this is the binding energy, and you can see the DFT binding energy as well as I also corrected the van der Waals, which is the van der Waals D2 correction. So you can see that the binding energy is decreasing as we are increasing the number of hydrogen, more hydrogen. But there, so the same pattern is following with the DFT as well as the corrected. So because the van der Waals correction is contribute very less. And now since we are doping the hydrogen, on zirconium plus graphene, we also want to understand what is the mechanism going on between the hydrogen molecules and zirconium plus gamma graphene. So that mechanism can also be seen by using the DAS plot. And from the A and B, you can see there is a less charge gained by the hydrogen, and similarly from C and D, you can see that there is some charges lost by the graphene plus ZR system. It means that hydrogen molecules has gained some charge. Actually, what is happening here? So zirconium is giving some charges to hydrogen molecules, and it also back donating. So that's why there is a very small small charge donated to hydrogen molecules. So this kind of interaction is called the Couvage kind of interaction. Now we have now we can, since we have observed up to 7 hydrogen molecules, 1 zirconium can attach. So what we have done, so because since there are many hexagon site. So we put on every hexagon site 1 zirconium molecules and compute what is the weight percentage. By using this formula, we calculate the weight percentage. If we are calculating the weight percentage by using one side, it will come out to be 5.6, and if we will do the both sided, it will turn out to be 7.9%. Which is remember, which is more than that, because the DOE criteria is only 6.5%. Yeah. Okay. Now, since we have got the result, okay, that's very good. Okay, so we have got this, but the problem is that all those DFT calculation is done on the 0 Kelvin. So how to ensure that this will be the practical feasible? So for that we do two things. One is the diffusion, kind of clustering things, and then also we have to do the stability. So we do the first one for the diffusion. So we try to make sure that our system is not diffusing. And so for here, what I have done, so I consider the one is the hexagon, center of the hexagon, and other is the nearing hexagon, which is the most probable diffusion position. So we do the SCF calculation at each point, and then plot the what is the energy. We have found that there is a huge energy barrier. It means that if we will put the zirconium atom at hexagon site, it will not go to the another site. It will not. It means that it will not diffuse, or it means that it will also not cluster. Now, since of course now the temperature remains as, so we also have to check the temperature. So for temperature we do the MD calculation, but here, since of course here we are doing AIMD, ab initio molecular dynamics, and what we have found. So A figure is the initial result from which we are starting, and B is the final result. What is the initial and final? So initially we started with we raised the temperature from 0 to 600 degree. And then for 3 PS, and then for the second time for 5 PS second at the 600 degree temperature, we have checked the system. So for that, how for 600, so for 5 picosecond, what I have done.
To the conclusion.
Yeah, ma'am, this is the conclusion. Just one slide is left. Okay, so what we are saying that what is the vibration, what is the position of zirconium atom is changing. So we can see that the vibration zirconium atom is changing very slow. It means that it's not almost negligible, because at this temperature there would be some kind of vibration. So this vibration is of course 0.6. It means that both result as well as our practical feasibility condition ensure that lead to our conclusions that the gamma graphene, zirconium doped gamma graphene can absorb hydrogen up to 7.9 weight percentage according to the first principle DFT, and the average, of course, average binding energy was 0.26 electron volt. And thank you. If you have question, please feel free to ask.
Thank you, Mukesh, for a nice presentation. Any question from audience?
Hello, Mukesh.
Yes, sir.
So you have shown the weight percentage. Have you calculated it through experimentally?
Professor Brahmanandji, your voice is not audible to us.
No, sir. What we are doing here?
Is it not audible?
Sir, it is audible to me. So the question he was asking about the weight percentage, I believe. Okay, so what I am doing here, so let's say this is our supercell. Let's go in the unit cell. So here is the unit cell. Okay, you can, if you will consider the unit cell, because this is the first figure, A is the supercell of 2x2, and if you will consider the unit cell, it will come out to be only 12 carbon atom. And actually, when we are doping the 1 zirconium atom here, you can, if you will look at the clearly, you will find that 1 zirconium atom is coming to 12 carbon atom. Then 1 zirconium at 12 carbon atom, and then we are using this formula. So H by M is the representing number of hydrogen atom per doped zirconium atom. So by using this formula, we can calculate, because we just need to know 1 zirconium atom and 12 carbon atom, and how many hydrogen atom or molecules have been absorbed by that. So this formula can tell you.
Okay, thank you, Mukesh.
Okay, thank you, sir.
Yeah, before we move to the next participant, the Jeet Sharma wants to ask one question to previous speaker Harsh. So Jeet Sharma, please ask your question.
Thank you very much, sir. My simple question was that when when the RGO was incorporated in the polymer matrix, the hydrogen permeability was increasing. So I was wondering that if we are increasing the heterogeneity in the system, how the permeability is increasing? Because in general, in proton exchange membrane fuel cell, the composites are generally introduced in the membrane to reduce the hydrogen permeability, so that the oxidative degradation is reducing. So I was wondering that how the RGO was increasing the permeability of hydrogen.
Okay, Jeet Sharma and Harsh Patel. Now we'll move to the next speaker. So next speaker is Niyanta Datta. So Niyanta, please share your screen. Niyanta, you are there?
Niyanta Datta. Okay, then we will jump to the next presenter, sir.
Yeah. So next presenter is Robin Saini. So Robin, you please share your screen.
Robin Saini.
Robin Saini, you are there? Robin, you are there? Okay, so then we'll move to the next speaker. Next speaker is Anita Mina. Anita Mina, you are present?
Yes, sir. Yes, sir.
Yeah, so you please share your screen.
Okay, sir. Okay, sir, I am sharing.
Sanita, log in from only one device.
To go. Okay. Delete करना पड़ेगा. Ma'am, it's not sharing in mobile phone.
Okay.
I have to use laptop. Give me 5 minutes.
Whichever device you want to use, you can, but log in from only one device because it's creating an sound echo.
But ma'am, I have only one device I am logging.
Now it's fine.
Okay.
Go ahead and start to showcase your slides. Anita,
ma'am, please give me 5 minutes, and you can.
Can't give this much of time.
Ma'am, you can call next participant, and then I will.
We are gonna call participant. Till that, arrange your slides. Our next Krishna.
Okay, so next participant is Krishna Paswal.
Yes, sir.
Okay, you share your screen.
Okay, sir. Sir, my slide is visible?
Yes, it's visible.
Yeah, visible.
1 second, please. Yeah. Sir, myself Krishna Poswal. I am pursuing PhD in Department of Chemistry, University of Rajasthan, Jaipur. And now I am representing oral presentation on fabrication of graphitic nitride zinc oxide hybrid nanostructures by novel method for effective degradation of brilliant crystal blue dye under visible light irradiation. I have done this job under my esteemed guide, Dr. Parmeshwar Lal Meena, sir. Now the presentation focus. The presentation focus is introduction, methodology, characterization, application, conclusion, list of publication by me, and references. Now next, introduction. In the last few years, the extensive growth in industry, specifically in the textile, dyeing, organic chemical, petrochemical, etc., has significantly contributed the organic contaminants to the water resources on the Earth planet. To overcome these global concerns, the semiconducting metal oxide nanoparticles photocatalysts have been considered the potential candidates for environment remediation and has wide range of catalytic potential towards the degradation of pollutants. In current study, we have synthesized the graphitic carbon nitride zinc oxide hybrid nanocomposite using a simple, cost-efficient in situ single-step pyrolysis method in which the precursor of zinc oxide and graphitic carbon nitride were mixed together in pastel dish, dehydrated by microwave heating, and finally calcined in muffle furnace. And the prepared samples were characterized by FTIR, UV visible, FESAM, XRD analysis, and were investigated through the photo degradation of dye, which is brilliant crystal blue, under visible light irradiation. Now the methodology. We have synthesized the bare graphitic nitride, bare ZNO, and the all ratio of nanocomposites, and the optimized composite ratio was ratio 4. For the preparation of ratio 4, we have used the simple wet chemical precipitation method, in which the 10 gram of urea with 2.5 gram of zinc acetate was grinded well in pestle and mortar for 30 minutes and then dried in microwave for 6.5 minutes. Furthermore, obtained mass calcinated at 550 Celsius for 30 hours in a muffle furnace. Then obtained yellow-brown color powder of graphitic nitride zinc oxide was grinded to a fine powder. Then it was washed with 0.1 m nitric acid, deionized water, and finally with ethyl alcohol. And at last, the obtained light yellow-brown colored powder was further heated at 85 degrees Celsius for 3 hours in oven. The diagram represents the preparation method for the synthesis of optimized nanocomposite, which is the graphitic nitride zinc oxide 4%. Now, these were the characterization techniques, and these was XRD, these were XRD, FESAM, UV visible, FTIR spectra. Yeah. Now we will move to the FTIR spectra. Figure 2 represent the FTIR spectra of bare graphitic nitride, zinc oxide, and all of the hybrid nanocomposites. The peak at the left side, this is at 525 for zinc single bond oxygen, and the peak at 812 for S-triazine group in graphitic nitride, which confirms the triazine ring in the graphitic nitride. The peak at around 3700 is for OH molecules, which represents the adsorbed water molecules. And the figure 3A represent the UV absorption spectra, and B, C, and D represent the top plot for ZNO, bare graphitic nitride, and the composite respectively. As it is shown in the B, the band gap of ZNO was 3.18 electron volt, and when we dose it with graphitic nitride, the band gap decreases and it reaches to the 2.9 electron volt. It is indicate that there is a decrement in the band gap while doping it with the graphitic nitride. Next, the FESAM spectra. In the left side, the FESAM spectra in A and B was for graphitic nitride, B and C and D for the bare ZNO, and in the right side, sorry, in the right side, this is the FESAM spectra for graphitic nitride zinc oxide nanocomposite, and there in the bottom it is the PDS spectra. analysis. XRD patterns, the XRD results analyze the phase purity and crystalline nature of the fabricated samples. And these are the XRD patterns for graphitic nitride, zinc oxide, and all of the four composite. These are 2, 4, 6, and 8. The each peak represents the each plane of the crystallographic substance. Now next, the application part. The as prepared samples were investigated through the photo degradation of brilliant crystal blue dye under the exposure of visible light effectively. As shown in the diagram figure 10, in the presence of light, the conduction band and the electron present in the conduction band fall into the conduction band of zinc oxide and convert the molecular oxygen to the superoxide radicals. And the valence band, the holes present in the valence band in presence of light goes excited to the valence band of the graphitic nitride and convert the water into the hydroxide radicals. These hydroxide radicals and superoxide radicals are the exact species which are responsible for the dye degradation process. In the figure 11, this is the pseudo first order kinetic plot for the photodegradation of BCB dye over the bare ZNO, graphitic nitride, and hybrid nanocomposites under visible light irradiation. It is clearly shown that for the ratio of 4 nanocomposites show maximum degradation, and hence it has the greater kinetic rate constant value. Next, the conclusion. The conclusion of my work is the hybrid nanostructures photocatalyzed with different ratio of urea and zinc acetate have been successfully fabricated and analyzed using XRD, FTIR, FSM, EDS, and UV visible spectra. And the photocatalytic performance of the fabricated structures are examined against the photodegradation of BCB dye, and the degradation was 99.80% in 60 minutes of visible light irradiation. The graphitic nitride hybrid nanocomposite fabricated from 4:1 of urea and zinc acetate has demonstrated the superior catalytic performance against the BCB dye compared to the bare zinc oxide and graphitic nitride. The result of the kinetic rate constant for the BCB dye was 3.61, and moreover the nanocomposite has shown good reusability and photostability over 5 Brunov cycles. The decrease in the catalytic performance even after 5 repeated cycles is approximately 5% for BCB dye. The present will provide an efficient and facile synthetic approach for constructing of graphitic nitride zinc oxide hybrid nanostructure for photocatalytic degradation of organic pollutants and environmental remediation. Now these are the list of my publications. References.
Yeah. Thank you, Krishna Paswal, for giving a nice presentation.
Yes, sir.
So your graphitic nitride is triazine based or heptazine based?
Triazine based, sir. Triazine based.
Triazine based. And
yes,
how it is better than instead of graphitic carbon, if you take just graphene oxide and ZNO hybridization, how it differs?
Yes, sir. The nanocomposite of graphitic nitride and zinc oxide is can degrade the dye more effectively than the bare ZNO or graphitic nitride, because in the nanocomposite the band gap of the conduction band and valence band is decreased, and due to the decrement of band gap, the recombination rate of hole and electrons decreased, so they can degrade the dye effectively.
Okay, thank you. So is there any question from the audience? Any question from audience? Okay, so if there is no question, we again thank Krishna Paswal. And Anita Meena, are you ready now for your presentation?
Yes, sir, I'm ready.
Okay, so you please share your slides.
Okay. Is it visible, sir? Is it visible, sir?
Yes, it is visible. Start.
Good afternoon, sir. My name is Anita Meena, research scholar at Janaranath University, Jodhpur. My topic is diversification of cell fabrication variables for the improvement of photogalvanic cells. Photogalvanic cells are based on the photogalvanic effect. The term photogalvanic effect was first time used by Robinovich in 1839. And the solar energy is the one of the most attractive renewable energy resources because of its flexibility and availability. The conversion of solar energy into electronic energy can be achieved by many techniques like solid phase photovoltaic cells, dye-sensitized solar cells, polymer solar cells, and photogalvanic cells, etc. Among these techniques, the photogalvanic cell, which work on the photogalvanic effect, has the potential for the both solar energy conservation and storage. So in this photogalvanic cell, I use phosgene as photosensitizer, fructose as reductant, and NaOH as alkali medium. So for this cell, photogalvanic chemical system, the maximum potential is observed, that is Vmax is 1083 microvolt. Short circuit current is 380 microampere, and power at power point is 138 microwatt, and conversion efficiency is 1.33%, and storage capacity, that is half time, is 70 minutes. And okay, thank you, sir.
Okay, thank you for finishing in time. So any question from audience? Is there any question from audience? Okay, so if there is no question, we thank the speaker and we'll move to the next presenter. So the next presenter is Ajit Kumar Singh.
Yes, sir.
You please share your slides.
Okay, sir. Wait 1 minute, sir. Okay, sir. It is visible?
No, yet not. Yeah, now it is visible.
Okay. Thank you, sir. So, hello everyone. My name is Vineet, and I'm speaking from DDU Gorakhpur University, Gorakhpur. And today I'm going to present my work, simulation work based on the tungsten disulfide WS2 especially. So the aim of my work is So here the aim of my work is, so here I have simulated two structures. One is the titanium dioxide and copper oxide, and second is the titanium dioxide or tungsten disulfide and copper dioxide based heterojunction solar cell. And for this simulation, I have used ESCAP one-dimensional simulator, which is freely available, and it is written by Dr. M. Bergman, University of Ghent, Belgium. Okay, so let me come to the first structure, titanium dioxide and copper oxide based heterojunction solar cell. So the top figure is the cross-sectional view of the cell. So top side is the front electrode, then FTO glass, and then NTIO2, then PCO2, and back side is the back electrode. And the bottom side, we can see the energy band diagram of this cross-sectional view. So in energy band diagram, we can say this is in non-equilibrium condition because Fermi level is not in align, and both are splitted. And ABC, the motion of the photogenerated charge carriers. So hole must move towards the back electrode because of the, if we draw in equilibrium, then we can see the direction of the electric field using the slope of this energy band diagram. And here, if photogenerated holes move, if it will try to move towards the front electrode due to presence of this energy barrier in between the titanium dioxide and the CO2, which is present because of the electron affinity and band gap difference of both the materials. So it will reflect back the photogenerated holes towards the back electrode, and there is a least chance to recombine these photogenerated holes towards the front electrode. While in the case of electron, as there is no any energy barrier in between the back electrode and copper oxide, so there is still possibility that few of photogenerated electrons can move towards the back electrode and they can recombine there, and they can reduce the open circuit voltage and hence the performance of the solar cell. So for this particular particular structure, I have simulated two variables. First input variable is the thickness of the absorber layer, and here we can see the different effect of output parameters on the thickness as we change the thickness. So at 0.05 micrometer thickness of absorber layer, that is here copper oxide, the available short circuit current density is only 1.46 milliamp per centimeter square, and efficiency is less than 1%, while in the case of the 10 micrometer, it improves till 10.19 milliamp per centimeter square, and efficiency stretches to 7.33%. And beyond 10 micrometer, if we see, there is not significant change in the performance of this particular heterojunction solar cell. So we can say, okay, close to 10 micrometer, we can move further simulation, and we can explain the changes in the short circuit current using this quantum efficiency curve. In quantum efficiency curve for the thinner layer, we can see the blue photons are closely, we can say the nearly 40% are absorbed by this particular device. However, for higher wavelength like 500 nanometer, these are poorly absorbed by the device when the absorber layer is very thin. However, when we increase the thickness of the absorber layer, the absorption of this longer wavelength becomes good, and that's why its performance becomes better. So second parameter is the impact of interface defect density. So how this interface defect density introduces. So when we put two different materials layer one by one, so mismatch of lattice constant, this thermal expansion coefficient and doping concentration will occur there, and due to these differences there will be some interface defect density. So here we started, so maximum possible interface defect density is 10 to the power 14 per centimeter square. This is not bulk defect, which we measured in per centimeter cube. It is per centimeter square. So it is for maximum 10 to the power 14. The efficiency is only 7.62%, while when we improve its reduce it 10 to the power 9, efficiency boost from 7.62% to 11.73%. And in the second structure, this is the second structure of TiO2. This is the second structure which I have simulated here based on the tungsten disulfide. So top side is the cross-sectional view, bottom side is the this energy band diagram, and in energy band diagram here we can see that photo-generated electrons can move only towards the front electrode, because there is a energy barrier in between the tungsten disulfide and copper oxide, while photo-generated holes move towards the back electrode only, because there is again an energy barrier in between the titanium dioxide and tungsten disulfide. Okay, and next I have used again the impact of WS2 layer thickness, and when we vary the WS2 layer thickness, we can see for a thinner layer the performance is only 9.19%. However, when we used 1 micrometer thick WS2 layer, this efficiency improves from 9.19% to 19.03%. This can be further explained on the basis of the quantum efficiency, which I have discussed earlier slide. Next, here I have again used the interface defect density. So here we have the two interfaces. First, the top interface in between the ETL or electron transport layer, titanium dioxide and WS2, and second interface is the in between the WS2 and copper oxide, this layer. So here we have discussed, we have simulated the impact of this front side interface defect density on the performance of the solar cell. So when the interface defect concentration is very high, it's order of 10 to the 14 per centimeter square, efficiency is only 19.03%. And when we reduce this interface defect density from 10 to the 14 to 10 to the 9 per centimeter square, efficiency improves from 19% to 27.67%. And to further improve this efficiency, we reduce the interface defect concentration from the bottom side, and further we reduce from 10 to the 14 to 10 to the power 9 for bottom interface, and here efficiency improves from 27 to 29.77%. And sorry. Okay, so this is the conclusion. In conclusion, we have simulated two structures. In the first structure, the best simulated titanium dioxide, copper oxide heterojunction solar cell has efficiency of 11.73% with open circuit voltage of 1.33 volt, short circuit current density of 10.58 milliamp per centimeter square, and fill factor of 83%. While in the second structure, based on the tungsten disulfide, we are getting nearly 29.77% efficiency. At this stage, I want to acknowledge UGC India for providing fellowship and Dr. M. Bergman, University of Ghent, Belgium. I also want to just provide my sincerely thanks to the organizing committee who has given me an opportunity to work to present my work in this conference. Thank you.
Thank you, Vinit Kumar Singh, for giving a nice presentation. So is there any question from the audience?
In second structure,
Yes, sir.
that is TiO2, WS2, and CO2, why the efficiency increases almost 2.5 times? What is
Okay,
the
sir.
basic?
So actually, when we are using this CO2O material, so CO2O material has the band gap. We have taken 2.17 electron volt. So if we see the absorption is using H nu is equal to H E is equal to H nu is equal to HC upon lambda. So we can calculate lambda is equal to H nu upon Eg. So due to higher band gap, absorption is falls close to 580 nanometer. So in solar spectrum 1.5 for G, above 580 nanometer photons will not absorbed by the copper oxide. That's why it will not generate sufficient short circuit current density. While in the case of WS2, it has the smaller band gap. So it will absorb more than, it will comes approximately 980 or 950 nanometer. So it will absorb more photon. That's why it will produce more short circuit current density and hence the efficiency.
You
Sir,
have
any
checked
more query?
experimentally also?
Yes, sir. No, sir. No, sir. Experimentally, I didn't do.
Okay. Thank you. Is there any question? Okay, then we again thank the speaker and we'll move to the next speaker, Subhash Chandir.
Thank you, sir. Thank you.
Subhash Chandir, you are there?
Next presenter is Jamin Rai. So Chandar is not present, I think.
Okay, so Jamin, you please share your slides.
Jamin Rai, are you there?
Jamin, you are there?
I think he is not there. So the next presenter is MS Shamna.
Yes, ma'am. I'm present.
You there? Okay,
Yes,
you.
yes.
Please make it sure that you finish the presentation within 5 minutes.
Okay, okay, sure. Good evening, everyone. Am I visible? Is my presentation visible? Is my presentation visible?
Yeah, visible.
Okay, okay. Good evening, everyone. I am Shamna, research scholar from Christ College in Nalakoda. The topic of my presentation is device modeling of a novel CS2P6 based perovskite solar cell with diverse transport materials and contact metal electrodes, a comprehensive simulation study using CATS. First of all, what is a perovskite solar cell? It is the perovskite, the solar cell in which the perovskite structured compound is used as the light harvesting material. And the main parts of the solar cells are generally there will be one absorber layer which has the role of converting the incident photons to electrons and holes, and Hall transport layer for capturing the holes and transport electrons, and electron transport layer for capturing the electrons and transport to electrodes, and the metal contacts. Coming to the proposed work in detail, in this work CS2P6 is used as the absorber layer, which is rarely studied and lead-free all-inorganic candidate in the field of perovskite solar cell. It is the double perovskite that exhibits greater stability than organic inorganic hybrid perovskites. In this work, the aim is to develop a non-toxic, reasonably stable and highly efficient perovskite solar cell. The study includes a comprehensive analysis of the photovoltaic performance of CS2P6-based perovskite solar cell. For that, we are using a solar cell simulation software CAPS 1D. The comprehensive study encompasses the effect of different electron transport material. We are taking about 6 electron transport material and 10 Hall transport material, and about 10 metal contacts are used for the simulation purpose. First of all, for validating the simulation, an already reported work is simulated using the SCAP software. In this work, cadmium sulfide is the electron transport layer, and the CS2P diasis is the perovskite active layer. Carbon is the hot transport layer. This graph shows the comparison between simulated and experimental CS2PT acid-based perovskite solar cell. In this post, it is depicting the experimentally measured photovoltaic performance parameters and simulated performance parameters. We can see that there is close matching between the experimentally measured values and simulated values, which validates the simulation. These are the electron transport materials used and Hall transport materials used for the simulation. This is electron transport material, and these 10 Hall transport materials were used. Coming to the simulation part, by fixing this cadmium sulfide as the electron transport material, these 10 hot transport materials were tried with the copper as the contact metal electrode. And on simulating that, we got this kind of result. That means the efficiency of efficiency is marking in this table. And when along with the CDS as ETL, when CUI as the hot transport layer is used, we got highest efficiency of about 12.14%. And when changing the ETL as SNO2, again with the CUI as hot transport material, getting highest efficiency of 9.36%. To the third ETM, that is zinc oxide, is when using zinc oxide as ETM. When hot transport material MOO3 is used as a hot transport material, getting highest efficiency of 12.914%. In the same manner, when NB2O5 and Fe2O3 is used as the electron transport material, getting the efficiency of 9.41 and 9.71% of efficiency. At last, when IN2O3 is used as the electron transport material, when the hot transport material Cu2O comes, it gives highest efficiency of 10.08%. On comparing all these, when zinc oxide is coming as the ETL and MOO3, molybdenum trioxide as the hot transport layer, the device gives highest efficiency of 12.914%. And next part is the optimization of the different parameters of the device. First, the first optimization is for the thickness of the active layer. The thickness of the active layer has varied from 10 to 100 to 1000 nanometer, and highest power conversion efficiency is obtained at 300 nanometer of thickness. In the same manner, optimization of defect density of active layer is done, and the optimization of the doping concentration of the active layer is done, and the performance parameter, that is the thickness and doping concentration of both ETL and HTL is varied, and figured out which is the best parameter for working the device. At last, the variation in performance parameter with both interface layers. There are two interface layers for this device, that is ETL perovskite layer, perovskite interface, and perovskite hot transport layer interface. On optimizing these two interface also, optimized parameters are listing in this table. So for thickness 120 nanometer, ETL thickness of 120 nanometer, it is giving highest efficiency. The same manner, all the parameters are optimized, and it is depicting in this particular table. After optimization, the back metal contact was changed. The back metal contact currently was copper, and changed this 10 back metal contact, and it was found that on increasing the metal work function, it is the power conversion efficiency of the device is increasing. On higher metal work function, the power conversion efficiency is almost a constant. So when silicon is taken as the back metal contact, the device gives highest power conversion efficiency of 20.45%. So before optimization, we got 12.91% of power conversion efficiency. After optimization, it becomes 16.85. And when changing the metal contact from copper to silicon, its power conversion efficiency becomes 20.45%. After optimizing the complete device, on analyzing the effect of temperature on the performance of the perovskite solar cell, it is found that at 300 Kelvin, the device shows highest power conversion efficiency. On higher temperature, the performance is decreasing or increasing the temperature. This is the table which compares the existing CS2
Your time is up. Can you finish quickly?
Okay, perovskite solar cell with the existing work, which is giving 20.45% of efficiency. These are the conclusion which is already mentioned. 10 HTLs and 6 ETLs are used, and the power conversion efficiency obtained is 20.45%, and 300 Kelvin is the most suitable working temperature for this particular device. And these are the references. Thank you, sir.
Okay, thank you very much So is there any question from the audience? Is there any question? Okay, so we thank again the speaker and we'll move to the next speaker. Next speaker is Richa Tiwari. So Richa, you are there?
And I am there. Is it my screen is visible?
Yes, visible.
Good evening, everyone. Myself Sakshi Baba, and today I'm representing my presentation on the topic formulation of bioagrease derived from mahua and karanjal. In introduction, the bioagrease is prepared from the bioagrease is a solid or semi-solid lubricant formed by the soap emulsified with mineral oil or vegetable oil. It has various functions. It is generally used to reduce friction and wear property. It has many toxic effects, that is that grease obtained from the mineral oil, because it contaminates the groundwater and also affect aquatic life. Because of these toxic effects, there is a need of lubricant. There is need of bioagrease obtained from the biodegradable material. That's why we use mahua and karanjal oil. Mahua and karanjal oil is selected because of the ease availability of these oils in our area. These have various functional characteristics, and also they have many industrial applications. We use mahua and karanjal oil. Mahua and karanjal oil has a high acid value. Therefore, we firstly treat it with a esterification, and after to lower the acid value, and after it we use transesterification method to prepare FAME, that is fatty acid methyl ester, and by the use of fatty acid methyl ester we also prepare triesters. And by the use of mahua and karanjal oil, we prepare soap with different metal based, that is sodium, potassium, and also we use calcium. By this formation of soap, we make bioagrease in 70-30 ratio, 80-20 ratio, and 90-10 ratio. 80-20 ratio gives better result. Therefore, we also made bioagrease from the FAME with the soap and triester with the soap. These are the FTI NMR by which we characterize by triester, which comes out to be 1740 at peak at 1740 and 1739 with the mahua and karanjal, which is nearby the carbonyl peak of ester. These are the properties that we determine with the different oil. Firstly, density, viscosity index, 4 point, flash point, 5 points, fornication value, acid value. Of all these, mahua oil, karanjal oil, mahua methyl ester, karanjal methyl ester, and mahua triester. These are the various bioagrease properties, that is appearance, cone penetration index, NLGI grade, dropping point, water washout resistance. 80-20.
Sakshi, your slides are not moving.
This is moving from my side.
I think please check your network. Sakshi.
Is it moving now, sir?
Now it is moving.
Yeah, now it is moving.
Okay, sir.
Okay, so you start from where you was there instead of the beginning.
So these are the properties that we determine, that is density, viscosity index, 4 point, flash point for the journal oils, that is mahua and karanjal, and after the preparation of FAME and after the preparation of triester, these all properties are determined. And after then the properties of bioagrease, that is appearance, cone penetration index, and LGI grade, dropping point, and water washout resistance are also calculated. And 80-20 ratio gives better result. That's why we also prepare bioagrease from with the FAME and the triester. This also gives better result. That is the result of all by the use of sodium salt. And these are the graphs First graph is the cone penetration index graph by the Mohu and Karanjoy biograph, and second one is the dropping point graph that is by the Mohu and Karanjoy. Well, it gives better result at 80-20 ratio. I again saying that is 172, 176 degrees Celsius of the dropping point, and also we calculate also determine the result with the potassium based soap and also with the calcium based soap, and calcium based soap give better result as compared to other, but these is costlier, that's why we check the sodium as a conclusion. After these biogrease prepared by all these are non-toxic and biodegradable, and due to water washout resistant, it has various application in that is in marine life, marine machines and the sector, and due to dropping point that is comparable to the commercial biogrease, and the NLG grade that is come out to be 2, which is comparable to the commercial biogrease. These are the references which I have used, and thank you.
Okay, thank you for finishing in time. So any question from the audience? Okay, if there is no question, we thank again the speaker and we'll move to the next speaker, Sanjukta Devi. Sanjukta, you are there?
Yes, sir, I'm present.
Yeah.
Sir, is my screen visible?
Yes, it is visible.
A warm good evening to all the chairpersons and the respected everyone present here today. Today I'll be talking on the experimental study on the impact of porous materials on the performance of a porous burner. The organization of my presentation is as follows. Now I'll begin with a brief introduction on what is a porous burner and what are the different parameters that I have varied here in order to do this study. So my study here in this topic is on a double-layered porous burner, and the materials used as the combustion zone and preheat zone in this porous burner were varied. Different materials having different porosity, having different thickness, and having different shapes were used, and the burner was the in-house developed for the operating power input power range of 5 to 10 kilowatt. Now, these parameters, the effect of this change in parameters were analyzed on the basis of or on the parameters of stability of the combustion flame and temperature measurements, and then emission study was done. Now, let me give a brief introduction on what is conventional combustion and what is porous media combustion. So as we can see in this picture that conventional combustion, we can see in our day-to-day life in our cooking stove or in a candle. So that is a conventional combustion. And while in porous media combustion, the combustion takes place inside the whole porous matrix. So it can be submerged or it can be partly submerged inside the porous matrix. So that is the basic physical difference that we can see between conventional combustion and porous media combustion. And porous media combustion is basically based on the concept of excess enthalpy, while conventional combustion is based on the concept of free flame combustion. This is a schematic diagram of how different both the combustions are. Now, let me explain what is the basic principle of how combustion in porous media works. So it is based on a concept of excess enthalpy, which was first given by Winberg. Now, if we consider that the air fuel, if we consider this as a burner and the air fuel mixture is entering into the preheating zone, first it enters into the preheating zone and then it reaches the combustion zone where the air fuel mixture combusts. So after combustion, a part of the heat of combustion is recirculated back into the preheating zone. So because of this recirculation through this porous media into this zone, what happens is that the incoming fresh fuel air mixture gets preheated and the temperature of the air fuel mixture before combustion is increased. So that is why we can achieve higher level of temperatures. I mean, quite higher level of temperatures as compared to conventional combustion. Some of the advantages of combustion in porous media are we can get lean combustion, low pollutant emission, and then also combustion of low calorific value gases is possible. Now, these are the various type of porous media burners which can be used. In this study, I have worked on a double layer, or I had developed a double layered porous burner, a matrix stabilized double layered porous burner. Now, this work had been attempted because earlier the work that has been done on, particularly in combustion in porous media, had been focused on LPG or higher calorific value gases, and particularly the biogas, which is locally available, or raw biogas, had not been tested, or had not been the characteristics and the combustion characteristic of biogas combustion, raw biogas combustion had not been checked or studied in the porous media burner. This is the schematic view of the whole setup. These are the properties of the biogas which was locally available. And these are the various cases. As you can see in the table, in the right-hand side table, these are the various cases. There are 5 cases that had been undertaken with varying parameters of thickness, material, porosity, and shape. So the materials that were basically used are alumina, zirconia, and silicon carbide, and also perforated mild steel sheets. This is a pictorial view of the stabilized porous media burner with silicon carbide as combustion zone. Okay, as we can see this burner, this outside layer that we can see from here is the combustion zone, and there is another layer inside which is the preheat zone. So these two materials had been varied during the whole studies. These two materials plus their characteristics like porosity, thickness, and shape had been varied during this study. Now, in order to do stability analysis, the 2 main parameters in combustion for doing stability study is flashback and blow off. Now, what is flashback is that when the velocity of air fuel mixture is lower than the velocity of the combusted mixture, then the flame tries to go downwards. I mean, it tries to go down upstream. So what happens is that flashback, that phenomenon is called flashback, when flame is unstable and tries to go upstream. And the another phenomenon which may occur when the flame is unstable is that the air fuel mixture velocity is higher than the combustion flame velocity, combusted mixture velocity. So what may happen is that the then instability may occur in this region.
Can you finish quickly?
Okay, sir, I'll finish in 2 minutes, sir. So these 2 parameters, flashback and blow off, were studied for all these 5 cases. So in this case, in the first case, when these combustion zone was zirconia and porous zone was alumina, perforated sheet, and then straight hole, and then mild steel sheets, in all these cases, the combustion was unstable. And after that, due to that case, we had shifted to the circular based porous medias. Now, while out of all these cases, we can see here that in this input power range of 5 to 10 kilowatt, case 5 provides lean combustion in equivalence ratio range of 0.75 to 0.97. So as compared to all the other cases. And in case 5, this silicon carbide was used as combustion zone, and alumina was used as preheat zone. Now, when the axial temperature distribution was done, axial temperature means the temperature inside the burner in these locations. So through axial temperature, the temperature of the base of the preheater was recorded, and temperature inside this burner was recorded. So from this temperature distribution, I got to know that at the base region, the temperature was always in this range. So there was no case of flashback because the autoinclination temperature of biogas is 650 degrees centigrade. And here also in this case, in this study of axial temperature, case 5 showed the highest temperature range out of all the cases. Now, at last, when the emission study was done, these are the various emission of CO and NOx for these four cases, case 2, case 3, case 4, and case 5. Here also, it was seen that some of the results are highlighted here, that both the CO and NOx concentrations increased with increase in input load or input power, and also equivalence ratio, as we can see here in this slide. And also here, in case 5, although in all these cases, the emission was low as compared to conventional burners, but in case 5, it offered the lowest values amongst all, like CO in the range of 37 to 165 ppm, and NOx was as low as 1.3 to 8.2 ppm. Now, in this is my last slide. I could conclude that like unlike square-shaped porous media, circular ones provided more stable and sustained combustion. And in the axial temperature measurement, it was seen that the stable region of the combustion flame occurred between the interface of the preheat zone and the combustion zone. And moreover, we could achieve very low values of CO and NOx emission in case number 5, where the also we got lean combustion, very lean stable combustion in case number 5, with combustion zone as silicon carbide and the preheat zone as alumina. So thank you, everyone.
Okay, thank you, Dr. Sangeeta, for nice presentation. Is there any question from the audience? Is there any question? Okay, if there is no question, we again thank the speaker, and we'll move to the next participant. The next participant is Pradeep Kumar. So Pradeep, you are there?
Yes, sir. Yes.
Yeah. So please share your slides.
Sir, my screen is visible to all.
Yes, yes, visible. Go ahead.
Okay, thank you. Good evening to all. My name is Pradeep Kumar, research scholar in the Department of HPKV Business School, School of Commerce and Management Studies, Central University of Himachal Pradesh, Dharamshala. I am presenting on the topic that is related to the determinants of non-residential rooftop solar photovoltaic adoption. The topic is not related to hardcore science and not based on experiment. Rather, it is related to social science and based on survey research related to the perceptions of adopters or users of non-residential rooftop solar photovoltaic adoptions. These are the contents of the study: introduction, objectives, methodology, analysis, findings. I'm directly coming to my objective because lots have been discussed about the introduction. My objective of this study is to find out the factors that influence the adoption of non-residential rooftop solar photovoltaic system adoption in Chandigarh, India. This is the research framework that has been used in the present research. We have used one endogenous construct, that is adoption, represented by AD in this diagram, and 7 exogenous constructs, that is perceived, initial cost, environmental concern, relative advantage, compatibility, complexity, observability, and trialability. We have used this relative advantage construct as a higher order construct, which is represented by 4 lower order construct, that is environmental benefits, economic profits, immediacy of rewards, and incentives. This is the research framework. These are the hypotheses we have framed for the research. That is, a relative advantage has a positive effect on the adoption of rooftop solar photovoltaic system. The compatibility of rooftop solar photovoltaic system has a positive effect on the adoption of rooftop solar photovoltaic system. Complexity of the rooftop solar photovoltaic system has a negative effect on the adoption. The trialability of the rooftop solar photovoltaic system has a positive effect on the adoption of rooftop solar system. The observability of rooftop solar photovoltaic system has positive effect on the adoption of rooftop solar photovoltaic system. Environmental concern has positive effect on the adoption, and perceived initial cost has a negative effect on the adoption of rooftop solar photovoltaic system. Actually, these hypotheses have been framed based on previous literatures and result, and the study is guided by the theory of diffusion of innovation that is given by Rogers in 1962. This is the methodology we have used in the study. The target population is concerned with Chandigarh UT, that is related to time period from 2010 to April 2019 of rooftop capacity of 1 kilowatt to 500 kilowatt. The data and the list of the adopter has been obtained from the nodal agency, that is CREST, that is nodal agency in the Chandigarh UT. The target sample size we have used in the present research is 200. Sampling technique we have used purposive and snowball sampling because we do not have sampling frame of private stakeholders and private adopters of non-residential rooftop solar system. Head of the organization was the sampling unit. Data was collected with the help of questionnaire. A scale has been developed to measure the latent construct with the help of pilot survey and experts' opinions. Data has been analyzed with the help of partial least square structure equation modeling that is done in smart PLS software. This is the you can see distribution of demographic variables. Almost 85% are male. Majority of the respondents were postgraduate and having professional degree or diploma. Majority of the decisions were taken by authoritative, that is 57%, that are the government organizations who have adopted rooftop solar photovoltaic system on their roof, on the building of their roof, and 41% respondents are concerned with individual or private organizations that they have adopted rooftop solar system on their buildings. The capacity of the rooftop solar photovoltaic system was in between 1 kilowatt to 500 kilowatt. We have divided in 3 categories. These are the validity assessment measurement of the this, research model or measurement model. Although this PLS structure question modeling is distributional, free and non-parametric methods of analyzing data, still we have used skewness and kurtosis to check the normal distribution of the data. We have checked skewness and kurtosis for in between +1 and -1. Common method wise in the instrument has been checked by Herman's single factor test that was conducted in SPSS software. Internal consistency and reliability of the scale has been measured with these measurements, Cronbach's alpha. We have checked value for more than 0.7. Composite reliability, we have checked value for 0.7 and in between 0.7 and 0.9. Convergent validity has been assessed by outer loadings that is checked for greater than 0.7. Average variance expected has been checked for greater than 0.5. Discriminant validity of the scale has been checked by Forner, Larker criteria, and HTMT ratio. We have satisfied all the validity criteria. These are the tables and data related to the assessment of validity, Cronbach's alpha values, composite reliability values, average variance expected. This is the table of discriminant validity, Forner and Larker criteria. This is the HTMT ratio. I'm skipping this part. I'm directly coming to the assessment of structural model, steps used in the assessment of structural model. These are the steps. First, we have analyzed multi-collinearity issue in the structure model. Then we have analyzed the significance and the relevance of the structural path or hypothesized path. Assessment of the explanation power of the model. effect size. We have also checked effect size of the predictors. We have also examined the predictive power of the model, that is out of sample prediction power. These are the multicollinearity tables. All the values are less than 5. That ensure that there is no issue of multicollinearity in the data. These are the results of the hypothesis.
You need to finish quickly. Your time is almost up.
Okay. This is the table of hypothesis tested. We have these relative advantage has been found significant in effecting adoption, followed by compatibility, reliability, and environmental concern. The perceived initial cost has also been found significant, but they are negative beta coefficient. They are negatively influencing the adoption of rooftop solar photovoltaic system. And this is the structural diagram, and this is the explanation power of the model R square. This is the 70%. Predictors are explaining 70% to the dependent variable adoption. Effect size small to medium. All the predictors have small to medium effect size. This is the out of sample prediction power. Q square value more than 0.35 ensures that high predicting power of the data. This is the final conclusion. Environmental concern is found to be major factor that influence the adoption, followed by compatibility, relative advantage, reliability. Perceived initial cost, immediacy of rewards, and economic profits are found to be the negatively influencing the adoption and found to be barrier for the adoption. Thank you so much.
Okay, thank you for nice presentation. Is there any question from the audience? Is there any question from the audience? Okay, so if there is no question, we thank again the speaker. So we have completed all the oral presentation in this session. Is there anyone whose oral presentation was scheduled in this session and missed and wants to present? Is there anyone?
Participants, the session is open for queries now. If you have any query or you want to have any interaction, then you are most welcomed. Okay, as I think there are no more queries, I want to thank you from our team to our honored chairpersons who chaired this session, Dr. Brahmanand Chakravarti and Professor Ghanshyam Sarma. Sir, thank you so much for giving your valuable time to us. And I also want to thank all the participants who showed your zeal and efforts and made this session very successful. Now moving forward, we are going.
Yeah, thank you all the speaker and audience, and as well as the organizer for giving this opportunity to chairing this session. I'll leave now, and I think we are supposed to submit the marks. Yeah. Is it?
You have to submit the marks. Directly you can contact to our convener of this conference, Dr. Chhagan Lal.
Okay. Okay. Thank you. We can email the marks.
Yes, sir. You can email.
Yeah. Okay. Thank you.
Thank you so much, everyone.
Thank you. Good day.
Ladies and gentlemen, we are going to have a keynote lecture from Professor William Sheffield. It was scheduled earlier on first day of conference, but due to some reasons, we rescheduled it today at this time from Professor John William Sheffield, Purdue Polytechnic Institute, Indiana, USA.
I have served as an editor of the International Journal of Hydrogen Energy since 1978. I'm excited to share with you some of my personal insights on green hydrogen, a global perspective of technologies. You might ask the question, why hydrogen? Well, the answer is clear. Hydrogen offers a unique cross-system opportunities for fundamental changes in the energy industry. What are the three key objectives for a global perspective of green hydrogen technologies? First, a change in mindset. Because of the global shift in the mindset of regulators, investors, consumers towards decarbonization, hydrogen projects are receiving unprecedented investments. Total cost of ownership analysis. The total cost of ownership analysis shows the cost competitiveness of large-scale applications of hydrogen energy technologies. And finally, gigawatt scale with correct regulatory framework. At scale, deployment of renewable hydrogen will require the development of gigawatt scale hydrogen production projects, for example, permitting an overbuilding of renewable energy supply with green hydrogen production capacity via water electrolysis. What are some of the learning outcomes for you from this lecture? Learn which countries are developing the hydrogen economy. Learn about the types of projects that are being developed and the volume of hydrogen produced and consumed in the world. Identify where the hydrogen energy technologies are being developed and what are the international outlooks for 2030 and 2050. So I'll start out with an introduction of the International Journal of Hydrogen Energy and some of the metrics we use to evaluate its performance. The International Journal of Hydrogen Energy is published by Elsevier and is our official journal of the International Association for Hydrogen Energy and was established in 1976. I joined 2 years later as the first assistant editor. 4 years later, it became monthly, bi-weekly in 2008, weekly in 2015, and today we're producing 80 issues for the year 2021 and beyond. For example, we published 40,312 pages and 80 issues in 2021. Now let's look at the journal metrics, which provide valuable insight into three aspects of the journal: impact, speed, and reach. These metrics help authors select the best journal for the publication of their research findings. First, we'll look at impact factor. As you can see here, from 2016 through 2020, which is our latest year of data collection, is an impact factor of 5.816. The review speed is important too, to determine the time required from the date of submission to the decision and to the date of final decision. So we can see here in the green graph, the submission, the time period from the submission to the first decision. Maybe the paper needs revision and it might require a couple of more weeks. So we can see that the date for the first decision is less than 6 weeks. And the time period from the date of submission to the final decision, say acceptance, is less than 9 weeks. Now we talk about the reach and global reach. Shown here in this map is the downloads indicating of the worldwide usage of this journal at the country or region level over the last 5 years. The big blue dot over China shows that there were more than 6 million downloads in that 5-year period. Looking at it a different way in terms of reach is the number of corresponding authors. The size of the balls here indicating the number of corresponding authors over the last 5 years, with over 5,000 authors from China. But the takeaway on both of those maps is the reach is global. Now, let's look at another aspect, and that is the Hydrogen Council. This is a global CEO-led initiative. The Hydrogen Council is a global CEO-led initiative of leading companies with a united vision, a long-term ambition for hydrogen to foster the clean energy transition for a better, more resilient future, using its global reach to promote collaboration between governments, industry, and investors. The Council provides guidance on accelerating the deployment of hydrogen solutions around the world. It also acts as a business marketplace, bringing together a diverse group of over 120 plus companies based in 20 plus countries across the entire hydrogen value chain, including multinational, innovative, small, mid-size, and so on. Now, I'd like to share with you that this coalition met at COP26 with the leaders in the hydrogen, contributed to over 20% of the global carbon abatement by 2050, with strong public-private collaboration required to make it a reality. This is November 2021. To show you some of the companies that are involved in the Hydrogen Council, you can see many well-known companies worldwide involved in this major global CEO-led initiative. Now, let's look at a policy toolbox for low carbon and renewable hydrogen. This is a publication of the Hydrogen Council. This publication released in November 3rd, 2021 by the Hydrogen Council at the time of the COP26 in Glasgow, Scotland. In this document, it shows 6 pillars of efficient policy design for low carbon and renewable hydrogen. First, to make use of the local strengths and benefits from cross-border cooperation. Create certainty through target and commitments. Provide hydrogen-specific support across the value chain. Support robust carbon pricing. Adopt harmonized certification of systems. And 6, factor in societal values and other aspects. So in this policy toolbox, the deployment from financial barriers are concentrated in the first 2 market maturity phases. The time frame for this enabling policies is the market creation, the market growth, and the market maturity. Along with that, the deployment of financial barriers are concentrated in the first 2 market phases. The other thing is in the value chain for hydrogen is upstream supplies. For example, in the market growth, we might look at the limited ability to recoup production cost on certain volumes and prices. Following that, we go on down the value chain and look at the midstream transmission and distribution and storage infrastructure and downstream demand, of course. If we look at the electrolyzer as a key component to scaling to the gigawatt scale, the capital expenditures, or the so-called CapEx, and demand by sectors in terms of, say, US dollars per kilowatt is referenced here. So what we have is the hydrogen deployed in ammonia and refining, road transport, steel, methane, power, maritime aviation, electrolysis deployed. Now, let's look at another policy opportunity that gives us a global perspective of the technologies, and that is hydrogen for net zero. Hydrogen for net zero. A report from the Hydrogen Council helped with McKinsey & Company. This report then looks at the challenge of reaching net zero by 2050 and how hydrogen plays into that in terms of this global perspective. Hydrogen has a central role in keeping or helping the world reach the net zero emissions by 2050 and limit the global warming to 1.5 degrees Celsius. Complementing renewable energy technologies and enhanced energy efficiency improvements, clean hydrogen, specifically green hydrogen, offers the only long-term, scalable, cost-effective option for deep decarbonization in sectors such as steel, maritime, aviation, and ammonia. Scaling through the year 2030 is critical for meeting the long-term targets of 2050 and unlocking cost-effective, efficient decarbonization opportunities. So in the report, the comment was made, setting our energy system on a trajectory to net zero requires firm commitment and rapid acceleration. Let me repeat that, firm commitment and rapid acceleration. Those are the imperatives. It is estimated the deployment of 75 million metric tons of green hydrogen is needed by 2030, an ambitious yet achievable target. Focus is on green hydrogen, hydrogen made from excess renewable electricity. Green hydrogen, again, is made by electrolysis of water from excess renewable electricity. That is our goal. The strong momentum, but a 540 billion capital gap remains until 2030. 2030 is the important inflection point to reach net zero by 2050. The hydrogen industry shows strong momentum around the globe, with more than 520 projects announced in 2021, up 100% compared to 2020. These projects will produce 18 million metric tons of clean hydrogen supply infrastructure in use. Considering investment to achieve government targets and support equipment, the value change in the total sum of estimated spending will grow to more than $60 billion by 2030. Framing for the hydrogen for the net zero by 2030 onto the developing the ambitious. Now, let's look at the pathways in the energy system. And importantly, the hydrogen energy, and particularly the green hydrogen, has the capability for sectoring or sector coupling. Sector coupling, what does that mean? Well, we saw earlier that the hydrogen produced goes for fuel for ground mobility. We also might have that as a syn fuel for aviation. And as we discussed, heating what we saw in the previous bar charts was the green heating. In the normal energy system, we would think mainstream into the power grid, the utility size grid. And in that might go to a variety of other applications. And in the feedstock, hydrogen as a feedstock to green the industry, the ammonia, iron, and refining. So in cracking of hydrocarbons, if we use a clean hydrogen, that allows the refining to be cleaner. But clearly that is not our objective. The objective is not to have refining. The refining should be decreasing. And so, yes, we could invest and putting hydrogen, clean hydrogen into the refinery to clean the refinery, but that's the delaying the inevitable. So the top of the chart here in the sector coupling is ground mobility. Now, hydrogen in use demand by region and of the world. So in North America, we see from 2030 to 2050, this large growth in mobility, the dark blue part of the bar chart. Similarly, in Europe, it has a similar trend. And in that case, new industry use may have a growth in the 2030 to 2050 period, more predominant in Europe. Now in China, as we saw in the hydrogen journal, as a key player where there is in reach of the number of authors, of the readership, we see mobility is important. We see that the power is important, and the new industry uses as a large growth. In addition, we see existing industry in China, where because of the heavy use of coal without much clean infrastructures to provide cleaner. If we go to Japan in the sort of the Pacific region of Japan and Korea, the important part for hydrogen play is in power. Mobility, because those are small nations and much of mobility is already efficient, we see a proportional important component, but the power is the critical. Now, in the industry, there's a role for that. Heating is as well. And the existing industry is not much change. Now, where's the rest of the world? If we combine the rest of the world, we would see that the mobility continues to play the dominance, the dark blue. The heating has the potential from 2030 to 2050 to have a large growth, new industry, and so on. So again, our priority is green hydrogen made from excess renewable electricity as a fuel for direct energy conversion devices, such as a fuel cell in the vehicle to extend the range of the vehicle and as an energy storage component. Now, hydrogen supply mix by production method in million tons per year. And what we see here is that the inflection point, as we mentioned earlier, is clearly seen the year 2030. And going out from 2030, we see a growth in the low carbon, a rapid growth, similar growth in the renewable, the green hydrogen, and the diminishing gray hydrogen. That is hydrogen, say, made from methane, from steam methane reforming or auto reforming, which is currently the larger component, and will, and by 2030 will become the less dominant. In 2030, we see where the low carbon, where we have carbon capture and storage systems, that the blue carbon may be in parity with the gray hydrogen, and the green hydrogen begins to play its role. So as we see between the blue and the green out by 2050, there's quite a fuzzy region where there's diffusion. And again, I strongly urge and suggest that the green hydrogen needs to be the dominant by 2030. We need the scale up, we need the policies. Those are the perspectives of the technology. If we do not, if we continue to extract oil and coal, we will not reach our 2050. In fact, 2030, the inflection point will be the determination of our failure. So it's imperative that when we talk about clean hydrogen, it is not made from fossil fuels. It is not made from fossil fuels. The hydrogen project announcements here, we see over 520 projects at the megawatt scale. At the gigawatt scale, 43 projects If we look around the world, we see in the country of Chile, 3 projects out of that, about 7% of the world's gigawatt scales in Chile. Chile is a small country in South America, but it's important in the mining industry. And in those cases, the large open pit surface mine where we're using large mining haul trucks that have a capacity of reaching over 400 metric tons per haul. Those trucks have converted 100% to green hydrogen, are those that we need the gigawatt scale productions. Now, we're maybe surprised in some countries that the deficit where there's not. So for example, in India, there's a couple of projects and part of the 221s that are large scale industry usage, refinery, ammonia, methanol, steel, and industry feedstock. That needs to change. And clearly the lack of transport projects in India, none, absolutely none. So out of the 133 projects worldwide, none of those in the transport. Why the transport? That was the mobility, the largest part of playing to reach our inflection point of 2030 and the critical component that leads us into the 2050 net zero. Without the transport, we have to have a major challenge. Without the large scale industrial projects going to the gigawatt scale, we have a problem. We need to also integrate the hydrogen economy across industry projects and different types of end uses. The sector coupling, no sector coupling projects in India. And finally, there was, in the last category, there was no projects, only a couple of projects in the large scale industrial use. So clearly that's a challenge that you as students and faculty and researchers need to work quickly and effectively. So let's look at the investment gap. That is, we have to finance these projects, and it can't be just from government policies because we know those are slow and not effective. We need announced and required direct investments into hydrogen. We look at those, the gap between what is needed and what's planned is we need in the production. And again, the gigawatt scale electrolyzer is the key link. The transmission and distribution is important and the end use are important. And as we go to beyond to achieve the investment of over 700 billion US dollars in 2030, it is in the gigawatt scale electrolyzer. That is, again, the requirements to fill that. So hydrogen must be unlocked and scaled. Unlocked, that is to say, we have to have the production from electrolysis from excess renewable electricity, and we have to do it at scale, not just at megawatt, but at gigawatt scale. We create demand, incentivize the decarbonization through clean hydrogen. Probably we should change that to incentivize decarbonization through green hydrogen. We need to ensure access, and we have lower cost. Make hydrogen accessible through the right infrastructure. Create economies of scale to reduce cost and open new markets. And in that currency or that economy, we need to always be looking at the total cost of ownership, not the initial capital expenditures, not the CapEx. We need to look at the OpEx, the operating and maintenance expenditures. So thank you for your attention. Mark your calendars, attend online. You can attend online. The 23rd World Hydrogen Energy Conference to be held on site and online in Istanbul, Turkey, June 26th through the 30th, 2022. The website here is at whecistanbul.org. Mark your calendars and attend. With that, I thank you very much for your attention, and please feel free to contact me if you have specific questions relating to this presentation or any other questions. And please consider when you finish your research that you might be conducting to consider publishing in the International Journal of Hydrogen Energy. Thank you, and best wishes for the rest of this conference.
बोलो तो क्या
Dear audience, Professor John William Sheffield is from USA. So there is a time difference between USA and India. Therefore, we had a recorded lecture. So if you have any queries regarding this session, you can text us, email us, or you can write in chat box also. We will reply you or answer you back within 1 or 2 days. I repeat again, if you have any queries, then you can write in the chat box. We will answer you in a while. Thank you, everyone. It was a pleasure being with you all today. We have come to the end of our second day of conference. I would like to thank everyone who has joined us today. And I also want to thank the eminent speakers and all presenters. We appreciate your being. Thank you again. And we will see you tomorrow. So stay tuned. And we'll be back at 9 a.m. in the morning tomorrow. Thank you.